In these first few videos, I want to lay the foundation of some core concepts you will need throughout these video tutorials. Let's get started with the basics. So what is a data structure? One definition that I really like is a data structure is a way of organizing data so that it can be used efficiently. And that's all a data structure really is. It is a way of organizing data in some fashion so that later on it can be accessed, queried, or perhaps even updated quickly and easily. So why data structures? Why are they important? Well, they are essential ingredients in creating fast and powerful algorithms. Another good reason might be that they help us manage and organize our data in a very natural way. And this last point is more of my own making, and it's that it makes code cleaner and easier to understand. As a side note, one of the major distinctions that I have noticed from bad, mediocre to excellent programmers is that the ones who really excel are the ones who fundamentally understand how and when to use the appropriate data structure for the task they're trying to finish. Data structures can make the difference between having an okay product and an outstanding one. It's no wonder that every computer science undergraduate student is required to take a course in data structures. It is strange that before we even begin talking about data structures, that we need to talk about the abstraction of data structures. What I'm talking about is the concept of an abstract data type. What is an abstract data type and how does it differ from a data structure? Well, the answer is that an abstract data type is an abstraction of a data structure which provides only the interface to which that data structure must adhere to. The interface does not give any specific details on how a specific data structure should be implemented or in what programming language. One particular example I like to give is to suppose that your abstract data type is for a mode of transportation to get from point A to point B. Well, as we both know, there are many modes of transportation to get from one place to another. So which one do you choose? Some specific modes of transportation might be walking or biking, perhaps even taking a train, and so on. These specific modes of transportation would be analogous to the data structures themselves. We wanted to get from one place to another through some mode of transportation. That was our abstract data type. How did we do that exactly? Well, that is the data structure. Here are some examples of abstract data types on the left and some possible underlying implementation on the right-hand side. As you can see, a list can be implemented in two ways. You can have a dynamic array or a linked list. They both provide ways of adding, removing, and indexing elements in the list. Next, we have a queue and the map, abstract data types, which themselves can be implemented in a variety of ways. Notice that under the implementation for a queue, I put a stack-based queue because, yes, you can have a queue which is implemented using only stacks. This may not be the most efficient way of implementing a queue, but it does work and it is possible. The point here is that the abstract data type only defines how a data structure should behave and what methods it should have, but not the details surrounding how those methods are implemented. Alright, now that we're done with abstract data types, we need to have a quick look at the wild world of computational complexity to understand the performance that our data structures are providing. So as programmers, we often find ourselves asking the same two questions over and over and over again. That is, how much time does this algorithm need to finish, and also how much space does this algorithm need for my computation? So if your program takes a lifetime of the universe to finish, then it's no good. Similarly, if your program runs in constant time but requires a space equal to the sum of all the bytes of all the files on the internet, your algorithm is also useless. So to standardize a way of talking about how much time and how much space is required for an algorithm to run, theoretical computer scientists have invented Big O notation, amongst other things like big theta, big omega, and so on. But we're interested in Big O because it tells us about the worst case. Big O notation only cares about the worst case. So if your algorithm sorts numbers, imagine the input is the worst possible arrangement of numbers for your particular sorting algorithm. Or as a concrete example, suppose you have an unordered list of unique numbers, and you're searching for the number 7, or the position where 7 occurs in your list. Then the worst case isn't when 7 is at the beginning or in the middle of the list. It's when 7 is the very last element of the list. For that particular example, the time complexity would be linear with respect to the number of elements and the size of your list, because you have to traverse every single element until you find 7. The same concept applies to space. You could just consider the worst possible amount of space your algorithm is going to need for that particular input. There's also the fact that Big O really only cares about what happens when your input becomes arbitrarily large. We're not interested in what happens when the input is small. For this reason, you'll see that we ignore things like constants and multiplicative factors. So in our Big O notation, you'll often see these coming up again and again and again. So to clarify one thing, when I say n, n is usually always going to be the input size coming into your algorithm. There's always going to be some limitation of size n. So constant time we refer to as a 1 wrapped around a big O. If your algorithm takes a logarithmic amount of time to finish, we say that's big O of log of n. If it's linear, then we just say n. If it takes like quadratic time or cubic time, then we say that's n raised to that power. If it's exponential, usually this is going to be something like 2 to the n, 3 to the n, any number b greater than 1 to the n, and then we also have n factorial. But we also have things in between these, like square root of n, log of n, n to the 5th, and so on. Actually, almost any mathematical expression containing n can be wrapped around a big O, and is Big O notation valid. So now we want to talk about some properties of Big O. So to reiterate what we just saw in the last 2 slides, Big O only really cares about what happens when input becomes really big. So we're not interested when n is small, only what happens when n goes to infinity. So this is how and why we get the first 2 properties. The first, that we can simply remove constant values added to our Big O notation, because if you're adding a constant to infinity, well, that's just infinity. Or if you're multiplying a constant by infinity, yeah, that's still infinity. So we can ignore constants. But of course, this is all theoretical. In the real world, if your constant is of size 2 billion, yeah, probably that's going to have a substantial impact on the running time of your algorithm. However, let us look at a function f, which I've defined over some input size n. If f of n is 7 log of n cubed plus 15n squared plus 2n cubed plus 8, well, Big O of f of n is just n cubed, because n cubed is the biggest, most dominant term in this function. Alright, now let's look at some concrete examples of how big O is used. So both of the following run in constant time with respect to the input size n, because they don't depend on n at all. So on the left, when we're just adding or doing some mathematical formula, yes, that's constant time. And on the right, okay, we're doing a loop, but the loop itself doesn't depend on n, so it runs also in a constant amount of time. So as our input size gets arbitrarily large, well, that loop is still going to run in the same amount of time, regardless. Now let's look at a linear example. So both the following actually run in linear time with respect to the input size n, because we do a constant amount of work n times. So on the left, we're incrementing the counter I by 1 each time. So f of n is n, and clearly when we wrap this in a big O, we get a big O of n. On the right, a little bit more complicated. We're not incrementing by 1, we're incrementing by 3. So we're going to finish that loop 3 times faster, so f of n is n over 3. So our second example is two algorithms that run in quadratic time. So the first one seems obvious. We do n work n times, so n times n is big O of n squared. But observe the second one. I changed the 0 with an I. So pause the video and try to figure out maybe why that's big O of n squared. Okay, let's go over the solution. So first, just focus on the second loop. The first loop isn't as important. So since I goes from 0 to n, the amount of looping done is going to be directly related to what I is. And remember, I is changing from the outer loop. So if we fix I to be 0, we do n work. If we fix I to be 1, we do n minus 1 work. If we fix I to be 2, we do n minus 2 work, and etc. So the question then becomes, what is n plus n minus 1 plus n minus 2 plus n minus 3 and so on? Well, this is a well-known identity, and it turns out to be n times n plus 1 divided by 2. So if we wrap this in a big O, we split our equation, we can see that this is big O of n squared. Now let's look at perhaps a more complicated example. Earlier you may have wondering, how do we ever get these logarithmics or linear rhythmic time complexities? So here's a classic algorithm of doing a binary search, which yields actually a logarithmic time complexity. So what this algorithm does is it starts by making 2 point errors. One at the very start and one at the very end of the array. Then it selects a midpoint between the two and checks if the value we're looking for was found at the midpoint. And then it has either found it or not. If it has found it, it stops. Otherwise, it discards one half of the array and adjusts either the high or the low pointer. Remark that even in the worst case, we're still discarding half of the array each iteration. So very, very quickly, we're going to run out of array to check. So if you do the math, the worst case is you will do exactly log base 2 of n iterations, meaning that the binary search runs in logarithmic time. A very cool algorithm, a very powerful algorithm. Here's a slightly different example worth going over. So first, notice that there is an outer loop with a counter I that does n work. Then notice that there are 2 inner loops, one that does 3n work and another one that does 2n work. So the rule we use to determine the complexity of this algorithm is to multiply loops on different levels and add those that are on the same, generally speaking. So using the rule above, we can see that it takes n work to do the outer loop, multiplied by 3n plus 2n for both inner loops, which gives us 5n squared, which is big O of n squared. Alright, so this next one looks very similar, but it's actually quite different. So on the outer loop with I, we have I going from 0 to 3n. So there's 3n work done on the outside. But we have to multiply that by what's going on the inside. So on the inside, j goes from 10 to 50. So that does 40 loops exactly, every loop. So that's a constant 40 amount of work. Plus, however, the second loop. So j is less than n cubed, but j equals j plus 2, so it's accelerated a little. So we're going to finish that loop a little faster. So we're going to get, on the inside, 40 plus n cubed divided by 2, but we have to multiply that by 3n. So if we wrap that in a big O, so big O of f of n, is going to give us big O of n to the fourth, because n to the fourth is the dominant term in our function f of n. There's some other classic examples of big O. So if we have to find all the subsets of a set, that takes an exponential amount of time because there are 2 to the n subsets. Finding all permutations of a string takes big O of n factorial. Another classic one is merge sort. So if we have n times log n for your merge sort. And if we have to iterate over all the cells of an array of size n by m, we have big O of nm time. Alright, let's talk about arrays. Probably the most used data structure. This is part 1 of 2 in the array videos. The reason the array is used so much is because it forms a fundamental building block for all other data structures. So we end up seeing it everywhere. With arrays and pointers alone, I'm pretty sure we can construct just about any data structure. So an outline for today's video. First, we're going to begin by having a discussion about arrays and answer some fundamental questions such as what, where, and how are arrays used. Next, I will explain the basic structure of an array and the common operations we are able to perform on them. Lastly, we will go over some complexity analysis and look at some source code on how to construct a dynamic array using only static arrays. Discussion and examples. So what is a static array? So a static array is a fixed length container containing n elements which are indexable, usually on the range of 0 inclusive to n minus 1 also inclusive. So a follow-up question is, well, what is meant by being indexable? So answer to this means that each slot or index in the array can be referenced with a number. Furthermore, I would like to add that static arrays are given as contiguous chunks of memory, meaning that your chunk of memory doesn't look like a piece of Swiss cheese with a bunch of holes and gaps. It's contiguous. All the addresses are adjacent in your static array. Okay, so when and where is a static array used? Well, they're used everywhere, absolutely everywhere. It's hard to make a program that doesn't use them, in fact. Here are a few places you may or may not know that do use arrays. So, of course, the first simple example is to temporarily store objects. This is the most common use of arrays that you are probably familiar with. Next is that we use arrays as buffers to store information from an input or an output stream. Suppose you have a really large file, for instance, that you need to process, but that file is so big it doesn't fit in all in memory. So we use a buffer to read small chunks of the file into the buffer or the array one at a time, and so eventually we're able to read the entire file. I also like to use arrays as lookup tables because of their indexing property. So this is a really easy way to retrieve data from a lookup table if you know where everything is and it's supposed to be and at what offset. Next, we can also use arrays as a workaround in a programming language that only allows one return value. So the hack we use then is to return a pointer or a reference to an array which then contains all the return values that we want. This last example is a bit more advanced, but arrays are heavily used in a programming technique called dynamic programming, with tabulation to cache already computed subproblems. So a classic example of this might be the knapsack problem or the coin change problem. Alright, time to talk about some complexity. So the access time for a static array and a dynamic array is constant because of the property that arrays are indexable. So searching, however, can take up to linear time because we potentially have to traverse all the elements in the array in the worst case, such as if the element you're looking for does not exist. Inserting, appending, and deletion from a static array doesn't really make sense. The static array is a fixed size container. It cannot grow larger or smaller. When inserting with a dynamic array, this operation can cost up to linear time because you potentially have to shift all the elements to the right and recopy all the elements into the new static array. This is assuming we're implementing a dynamic array using static arrays, however. Appending, though, is constant. Doesn't that seem a little strange? Well, when we append elements to a dynamic array, we have to resize the internal static array containing all those elements. But this happens so rarely that appending becomes constant time. Deletions are linear for the same reasons that insertions are linear. You have to shift all the elements over and potentially recopy everything into your static array. Okay, so we have a static array A I've defined at the top. So A contains the values 44, 12, minus 5, 17, 6, 0, 3, 9, 100. Currently all the elements are distinct, but this is not a requirement of an array. Also remark that the very first element, 44, has index or position 0 in the array. Not 1, this confuses many intro computer science students who have no idea. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 1. Now, if we look at A, you can see that it contains the values 44, 12, minus 5, 17, 6, 0, 3, 9, and 100. Currently, all the elements are distinct. However, this is not at all a requirement of the array. Also remark that the very first element, 44, is indexed or positioned at index of 0 in the array. Not 1, 0. This confuses a lot of intro computer science students. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 0-based. This is what causes the confusion. But worst of all is quantum computing. I did research one summer in quantum computing during my undergrad, and the field is a mess. It tries to please mathematicians, computer scientists, and physicists all at the same time. And indexing just doesn't work well. Anyways, back to arrays. I should also note that the elements can be iterated over using a for each loop, something that's offered in some programming languages. It doesn't require you to explicitly reference the indices of your array, although the indexing is done internally, behind the scenes. The notation of the square brackets denotes indexing. So array A, square bracket 0, close square bracket is equal to 44, meaning A at position 0 is equal to the value 44. Similarly, A at position 1 is 12, A at 4 is 6, A at 7 is 9. But A at index 9 is out of bounds, and our program will throw an exception. Unless you're in C, it doesn't always throw an exception, unfortunately. Okay, now if we assign position 0 to be -1, that happens. If we assign index 5 to be 18, and if we assign index 6 to be 25. Let's look at operations on dynamic arrays. So dynamic arrays can grow and shrink in size as needed. So the dynamic array can do all similar get, set operations static arrays can do, but unlike the static array, it grows in size dynamically as needed. So if we have A containing 34 and 4, then if we add -7, it gets appended to the end. If we add 34 again, then it'll add it to the end. And we can also remove elements. So you see here our dynamic array shrank in size. Pretty cool, eh? Okay, so we already talked about this a little bit, but how do we formally implement a dynamic array? Well, the answer is typically this is done with a static array, but this is not the only way, of course. So first we create a static array with some initial capacity, usually non-zero. So as we add elements to the underlying static array, keeping track of the number of elements added. Once we have to add an element which exceeds the capacity of our internal static array, what we can do is we can double the size, copy all the elements into this new static array, and add the new element we need to add. Let's see an example. So suppose we create a dynamic array with an initial capacity of 2. Then we begin adding elements to it. So the little circle with the slash through it is a placeholder for an empty position. Okay, so we add 7, everything's fine. We add 9, everything's fine. But once we add 3, it doesn't fit in our internal static array. So we double the size of the array, copy all the elements in, and now we can add 3. Now if we add 12, everything's still okay, we're doing good. And if we add 5, okay, we have to do a resize again. So double the size of the container, copy all the old elements into this new larger array, and then finish off by adding 5. And similarly, we can add 6 without any issues. Alright, time to look at the dynamic array source code. This is part 2 of 2 in the array series. So the source code for this video can be found at the following link: github.com/myusername/data-structures. Also make sure you saw the last video so you know what's going on with this array implementation. Alright, here we are in the array class. So I've designed an array class to support generics of type T. So whatever type of data we want to put in this array, that's fine. So here are our 3 instance variables that we care about. R, which is our internal static array. Len, which is the length the user thinks the array is. And capacity is the length of the actual array. Because sometimes our array might have more free slots, and we don't want to tell the user that there's extra free slots that are available. That's just our internal knowledge. So there's 2 constructors. The first one will initialize the array to be of size 16. The other one, you give it a capacity. The capacity, of course, has to be greater than or equal to 0. And then we initialize our array and cast it to a type T. Also notice that I need to put this suppress warnings unchecked just because of annoying generics in Java. So here are two simple methods: size, get the size of the array, and check if the array is empty. Pretty self-explanatory. Similarly, for get and set, we just index into the array if we want the value, or set it if we want to set the value. Technically, I should be doing a bounds check for both of these, but I'm not, apparently. Okay, clear. So here we just remove all the data in our array and reset the length. Simple. This next one is the add method, where things actually get a little bit more complicated. So this condition says, hey, if the length plus 1 is greater than or equal to the capacity, then it's time to resize my array. The way I'm resizing is I'm doubling the size of the static array. You don't have to double the size, but I've decided that doubling the size is convenient. So when I double the size, I have to create a new array with the new capacity, copy everything in. This is what this line or these lines are doing. It's copying the old values back into this new array, and then it sets the old array to be the new array. And lastly, here we just copy the new value into our array. So this remove as method will remove a particular value at a given index. First, we check if the index is valid. If it's not, throw an index out of bounds exception. Otherwise, grab the data at the remove index, initialize a new array of size length -1. Now copy everything into the new array except for when it's at that remove index. Now I'm sure there's easier ways to do this, but I decided to do the following. Maintain two indices, I and j. Increment I and j as you go, but when I is equal to the remove index, then we skip over the remove index by fixing j temporarily and using j to lag behind, if you will, while I is still in the original array. So I guess pretty clever overall. And then set the array to be the new array we just generated, reset the capacity, and return the data we have just removed. So this next one, remove, we scan through the array. If we find the object we're looking for, remove it at the index and return true, otherwise return false. Index of is very similar. If you find it, return I, otherwise return -1. Contains just checks if index of is not equal to -1. Alright, this next one, I return an iterator for the array. So an iterator allows us to iterate over the array, providing an abstraction for it. So I need to override two methods, and this is hasNext. So there exists a next element in our array if the index is less than the length of the array. I should also be checking for concurrent modification here, just in case someone decides to change the array for some reason while we're modifying it. Might add that later, might not. Also, there's the next method, which just returns the next element in the array relative to the iterator. Okay, and lastly is the toString to get a string representation of this array. Nothing too complicated. Alright, so this is a very simple data structure, it's just a dynamic array. If you look at Java's array list, it looks very, very similar to this. Today we're going to talk about singly and doubly linked lists, one of the most useful data structures out there. This is part 1 of 2. In the second part, we will be looking at some source code on how to implement a doubly linked list. So for today's outline, in the first section, we're going to answer some basic questions concerning singly and doubly linked lists, namely what are they and where are they used. Next, we're going to cover some terminology concerning linked lists so everyone knows what I mean when I say the head of the linked list versus the tail of the linked list. Then last in the discussion, we'll talk about the pros and cons of using singly and doubly linked lists. Then how to insert and remove elements from both singly and doubly linked lists, as well as some source code, so stay tuned. Alright, discussion. So what is a linked list? Linked list is a sequential list of nodes that hold data which point to other nodes also containing data. So below is an example of a singly linked list containing some arbitrary data. Notice that every node has a pointer to the next node. Also notice that the last node points to null, meaning that there are no more nodes at this point. The last node always has a null reference to the next node. For simplicity, I will omit this in the following slides. Okay, so where are linked lists used? One of the places they get used the most is actually in the abstract data type implementation of lists, stacks, and queues because of their great time complexity for adding and removing elements. You also see linked lists in things like circular lists, making the pointer of the last node point to the first node. So circular linked lists are used to model repeating event cycles, maybe like having a round-robin ordering on a bunch of elements or representing corners of a polygon. So definitely a lot of uses there. Linked lists can also be used to model real-world objects, such as a line of train carts. That could be useful. And moving on to some more advanced examples, we also heavily use linked lists in hash table separate chaining and for adjacency lists and graphs. We'll get to those in a later video. Okay, a bit of terminology surrounding linked lists. First thing you need to know when creating a linked list is that we always maintain a reference to the head of the linked list. This is because we need somewhere to start when traversing our list. We give a name to the last element of the linked list also. This is called the tail of the list. Then there are also the nodes themselves, which contain pointers. Pointers are also sometimes called references, and these pointers always point to the next node. You should also know that the nodes themselves are usually represented as structs or classes when actually implemented. We'll get to this when we look at the source code. Okay, singly versus doubly linked lists. So concerning the kinds of linked lists that there are two types, singly linked and doubly linked. Singly linked lists only contain a pointer to the next node, while doubly linked lists not only contain a pointer to the next node, but also to the previous node, which makes it quite useful sometimes. This is not to say we cannot have triply or quadruply linked lists, I just wouldn't know where to place the additional pointers. Pros and cons of doubly linked lists. So there are trade-offs between picking a singly and a doubly linked list. What are they? If we look at the singly linked list, we observe that it uses less memory. Why? Well, pointers to nodes can actually take up a lot of memory. If you're running on a 64-bit machine, references use 8 bytes. On a 32-bit machine, 4 bytes each. So having a singly linked list means you only need one pointer for each node, hence twice as much memory is saved. A downside, however, is that you cannot access previous elements because you don't have access to them. You would need to traverse from the head of the linked list all the way up to the previous node to find it. Now concerning doubly linked lists, well, a great pro is that having access to the tail, we can easily traverse the list backwards, something we can't do with a singly linked list. Also, having a reference to a node you want to remove, you can remove it in constant time and patch the hole you just created, because you have, again, access to both the previous and the next nodes. This is something you cannot do with a singly linked list. You would leave the list severed in two. A downside, however, to the doubly linked list is it does use up twice as much memory. Okay, let's go into some implementation details on how we can create linked lists and remove elements from linked lists. Starting with singly linked lists. So here is a singly linked list. I've outlined where the head and the tail is. Now we want to insert 11 at the third position where 7 is currently. Let's walk through an example. So the first thing we do is we create a new pointer which points to the head. This is almost always the first step in all linked list operations. Now what we're going to do is seek up to, but not including, the node we want to remove. So if we seek ahead, we advance our traversor pointer, setting it equal to 5's next node, which is now 23. And now we're actually already where we need to be to insert the next node. So we create the next node, that's the green node, 11. And we make 11's next pointer point to 7. And the next step is to change 23's next pointer to be 11. Remember, we have access to 23's next pointer because we have a reference to it with the traversor. Okay, and now if we flatten out the list, we can see that we've correctly inserted 11 at the right position. And we're done. Okay, alright, time to insert with a doubly linked list. This is much trickier because of all the pointers flying around, but it's the exact same concept. Notice that the doubly linked list not only has pointers to the next node, but also to the previous node. We also have to change those in the insertion phase. Okay, create a traversor pointer which points to where the head is and advance it until you are just before the insertion position. So we advance the traversor by 1 and now we're just before the node, so we stop traversing. Let's create the new node, which is node 11. Point 11's next pointer to equal 7. Also point 11's previous pointer to be 23, which we have a handle on because of the traversor. Now we make 7's previous pointer equal to 11, so we can go backwards from 7 to 11. And the last step, make 23's next pointer equal to 11. This is so that we can go forwards from 23 to 11. So in total, remark that we changed exactly 4 pointers. So if we flatten out the list, you can see that 11 has been inserted in the correct position. Alright, now how to remove elements from a singly linked list. So suppose we want to remove the node with a value 9. How do we do this? Well, the trick we're going to use is not to use one pointer, but 2. You can use one, but for visual effects it's easier to show you how it is done by using 2. So we create pointers trav1 and trav2 for traversor 1 and traversor 2 respectively. So traversor 1 points to the head. Traversor 2 points to the head's next node. Now we're going to do is advance trav2 until we find the node we want to remove, while also advancing trav1. Okay, we have found node 9, so this is the stopping point. I'm going to create another pointer to the node we wish to remove, so we can deallocate its memory later. Okay, so now I had to have advanced trav2 to the next node. And node 9 has turned red. I've done this to indicate that at this point, node 9 is ready to be removed. I'm just keeping it around for the visual effect. Okay, so now set trav1's next pointer to be equal to trav2. And now it is an appropriate time to remove the temporary pointer because we're doing nothing with it. And there, temp has been deallocated. Make sure you always clean up your memory to avoid memory leaks. This is especially important in C and C++ and other programming languages where you manage your memory. Now you can see that 9 is gone and our singly linked list is shorter. Okay, now for the last bit of implementation, let's look at how to remove nodes from a doubly linked list, which is actually easier in my opinion to removing from singly linked lists. The idea is the same. We seek up to the node we wish to remove, but this time we only need one pointer. One traverser pointer, because each node in the singly linked list has a reference to the last node, so we don't need to manually maintain it like we did with the singly linked list. So let's start trav at the very beginning and seek until we hit 9. Okay, we've reached 9 and we want to remove it from the list. To do this, set 4's pointer to be equal to 15. We have access to 4 and 15 because they are trav's previous and next pointer, respectively. Similarly, set 15's previous pointer to equal 4. Notice that trav is now red, meaning it is ready to be removed. So we get rid of trav, and now if we flatten out the doubly linked list, we see that it no longer contains 9. Let's do a bit of complexity analysis on linked lists. How good actually are linked lists? On the left column, we have singly linked lists, and on the right, doubly linked lists. The complexity for searching in a linked list is linear, in the worst case, because if the element we're looking for is not there, we have to traverse all of the n elements. Inserting at the head, though, is constant time, because we always maintain a pointer to the head for a linked list, and hence we can add it in constant time. Similarly for the tail. To remove the head of a singly linked list and a doubly linked list is also constant time. Again, because we have a reference to it, so we can just remove it and advance the head by 1. However, removing from the tail is another story. It takes linear time to remove elements from a singly linked list. Can you think of why? Well, even if we do have a reference to the tail in a singly linked list, we can remove it, but only once, because we can't reset the value of what the tail is. So we had to seek to the end of the list and find out what the new tail is equal to. Doubly linked lists, however, do not have this problem, since they have a pointer to the previous node, so we can continually remove nodes from the tail. And finally, removing somewhere in the middle is also linear time, because in the worst case, we would need to seek through n-1 elements, which is linear. Alright, time to look at some doubly linked list source code. This is part 2 of 2 in the linked list series. So the link for the source code can be found on GitHub at github.com/williamfize/data-structures. Please star this repository if you find the source code helpful so that others may also find it. And also make sure you watch the first part of the linked list series before continuing. here we are in the source code. We're looking at the implementation of a doubly linked list in Java. So first, notice that I have declared a few instance variables. So we are keeping track of the size of the linked list, as well as what the head and the tail currently are. To begin with, the head and the tail are null, meaning linked list is empty. Furthermore, we will be using this internal node class quite excessively because it contains the data for our nodes, and it also contains the previous and next pointers for each node, since this is a doubly linked list. So we have one constructor for the node, namely the data and the previous and the next pointers themselves. We need both, otherwise we can't do much. So this first method I have declared here is to clear the list. It does so in linear time by going through all the elements and deallocating them one at a time. It deallocates them by setting them equal to null. So we start a traversor at the head, we loop while the traversor is not equal to null, meaning there are still elements in the list, and then we do our deallocation business. And at the end, we set the size equal to 0 and reset the head and the tail. Perfect. These size and empty methods are pretty self-explanatory. Get the size and check if the size of our linked list is empty. Okay, so here I have a public method to add an element. By default, we're going to append to the end of the linked list or at the tail. But I also support adding to the beginning of the linked list. So how we do this, if this is the first element, aka the list is empty, then we set the head and the tail to be equal to the new node, which has, as you can see here, both previous and next pointers set to null. Otherwise, if the list is not empty, then we say the head's previous pointer is equal to this new node, and then we set the head pointer to be whatever head's previous is. So we back up the pointer in a sense, and we also don't forget to increment the size. A very similar thing is done when we want to add to the tail of the linked list, except we're moving the tail pointer around. Okay, let's move to peek. So peeking is just looking at either the element at the beginning of the linked list or at the end of the linked list. And we throw a runtime exception if the list is empty, because it doesn't make sense to peek an empty list. Okay, now we get to the first more complex method, which is remove first. So this is if we want to remove the head of the linked list. So we can't do much if the list is empty. Otherwise, we get the data, we extract the data at the head, and then move the head pointer forward. We decrease the size by 1. So if the list is empty, we set the tail to be null as well. So both the head and the tail are now null. Otherwise, we deallocate the memory of the previous node that we just removed. This is especially important if you're in C or C++. Make sure to free or delete your pointers. Then at the end we return the data. A very similar thing is done for last, except we're using the tail this time to remove from the tail of the linked list and not the head. Okay, and here's a generic method to remove an arbitrary node. Remark that I set this to private because the node class itself is private, so the user shouldn't have access to the node. That's just something we're using internally inside the linked list data structure to manage the list. So if the node that we're removing is either at the head or the tail, detect that and call our methods either remove first or remove last. Otherwise, we know we're somewhere in the middle of the linked list. And if we are, we make the pointers adjacent to our current node equal to each other. So we're effectively skipping over the current node. And then, of course, don't forget to clean up your memory and return the data. So we have to temporarily store the data, of course, before we delete the node. Otherwise, we've deleted the node and the data is already gone. Now, suppose we want to remove a node at a particular index in our linked list. Yes, we can do this. Even though our nodes are not explicitly indexed, we can pretend that they are. So first check that the index is valid, otherwise throw in a legal argument exception. So here we are trying to be a bit smarter than just naively going through the linked list. Either we're going to start searching from the front of the linked list to find our index, or from the back, depending on if the index is closer to the front or to the back, although this method remains linear. So for the remove method, we want to be able to remove an arbitrary value from our linked list, which is object. So we're going to also support searching for null values in case someone decided that the value of the node should be null. That's fine. So we check that special case. Otherwise, we traverse through the linked list until we find a null element and then remove that node and return true. We return true if we've actually found the element we want to remove. Otherwise, we return false down here. In this else statement, we search for the element we want to remove. We use the dot equals method to check if we found the element. If so, remove that node and return true. Okay, here we have a related method, which is index of. So this is not remove at an index or remove a value, but get whatever index this object is at. Again, support searching for null, so even if our value is null, we'll just return the first place we find a null element. So again, traverse the linked list. Otherwise, search for a non-null element, and also increment the index as we go. We can use the index of for our method contains to check if an element is contained within a linked list, because we return -1 if the element is not found. Something that's useful sometimes is to have an iterator for a linked list. This is also trivial to implement. Just start a pointer, traverse at the head, and traverse until you reach the end. Notice I'm not checking for concurrent modification error, but if you want to, it's pretty easy to do that. And lastly, at the very bottom, we have the toString method to print a string, or to get rather a string representation of our linked list. May I begin by saying that the stack is a remarkable, absolutely remarkable data structure. One of my favorites, in fact. This is part 1 of 3 in the stack videos. Part 2 will consist of looking at a stack implementation, and part 3 will be some source code for how a stack is implemented using a linked list. So here are the topics that we'll be covering in this video, as well as the others. First, we will answer the question about what is a stack and where is it used. Then we will see some really cool examples of how to solve problems using stacks. Afterwards, we will briefly look at how stacks are implemented internally and the time complexity associated with the stack's operation. And lastly, of course, some source code. Moving on to the discussion about stacks. So what is a stack? A stack is a one-ended linear data structure which models a real-world stack by having 2 primary operations, namely push and pop. Below you can see an image of a stack I have constructed. there is one data member getting popped off the top of the stack and another data member getting added to the stack. Notice that there is a top pointer pointing to the block at the top of the stack. This is because elements in a stack always get removed and added to the top of the pile. This behavior is commonly known as LIFO, or last in, first out. Let's look at a more detailed example on how a stack works and how things are added and removed from a stack. So let's walk through an example. On the left side, I have some instructions on what we need to add and remove to the stack. So the first operation is a pop. So we remove the top element from the stack, which is apple. So boom, apple is gone. Now we push onion onto the stack. So we add onion to the top of the stack. Next instruction says to push celery onto the stack. Next is watermelon, which we put on top of the stack. Next operation says to pop, so we remove the element at the top of the stack. This is the watermelon we just added. The next operation, also a pop, so we remove from the top of the stack. This is celery. And the last operation, push lettuce onto the stack. So we add lettuce on the very top of the stack. So as you can see, everything operates on the top of the stack. We don't have access to anything else but the top of the stack. This is critical in our understanding of how a stack works. So when and where is a stack used? Stacks are surprisingly used absolutely everywhere. They're used in text editors to undo text you've written, in browsers to navigate backwards and forwards. They're used in compilers to make sure you have the correct number of matching braces and in the right order. Stacks are used to model real-world stacks such as books, plates, and even games like the Tower of Hanoi, which we'll get to shortly. Stacks are also used behind the scenes to support recursion by keeping track of previous function calls. When a function returns, it pops the current stack frame off the stack and rewinds to the next function that is on the stack. It's rather remarkable that we use stacks all the time in programming and never even notice it. Something else you can use stacks for is to perform a depth-first search on a graph. A depth-first search can be done manually by maintaining your own stack or by using recursion. Well, guess what? Both use stacks, as we have just discussed. Complexity analysis. So, the following complexity table assumes that you implemented a stack using a linked list. Pushing takes constant time because we have a reference to the top of the stack at all times. Well, the same argument goes for popping and peeking. Searching, however, still takes linear time. The element we're searching for isn't necessarily at the top of the stack, so we may need to scan all the elements in the stack, hence requiring linear amount of work. Now, here's a cool example of a problem using stacks. Problem. So given a string made up of the following brackets, round brackets, square brackets, curly brackets, determine whether the brackets properly match. So analyze the examples below to understand what type of bracket sequence is valid and which ones are invalid. So before I show you the solution, try and come up with a solution yourself. Hint, use a stack. Okay. In this first example, consider the following bracket sequence. As we are processing the string from left to right, I will be displaying the current bracket and the associated reversed bracket. So let's begin. For every left bracket we encounter, we simply push those on the stack. So this is a left square bracket that I've highlighted in light blue. So we push this one on the stack. Same goes for the next left square bracket and for this left curly bracket. Okay, this is a right square bracket. So we encountered a right square bracket. So we need to do two checks. First, we check if the stack is empty. If so, the bracket sequence is invalid. But if there are still things in the stack, then we pop the top element and check if its value is equal to the reversed current bracket. Right now, the top element is equal to the reversed bracket, so we are good. Next is a right square bracket again. So is the stack empty? No, it isn't, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, it is, so let's keep going. A round left bracket. Let's push it onto the stack. A right bracket. Is the stack empty? No? Okay, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, okay, so we're good. Another right bracket. Is the stack empty? No, okay, good. And is the top element of the stack equal to the reverse bracket? Yes, okay, good. And now we're done processing the string. We need to make sure the stack is empty now. Why is that? Well, in case the last few characters in the bracket sequence were left brackets, they would still be in the stack, right? But our stack is empty, so we can conclude that this bracket sequence is indeed valid. Alright, let's do another example with another bracket sequence. So try and work this one out. So the first bracket is a left bracket, so we push on to the stack. The second bracket is also a left bracket, so we push on to the stack. This next bracket is a right bracket, so let's check if the stack is empty. No, it's good. And is the top element of the stack equal to the reverse bracket? Yes, it is. This next bracket is a right bracket. Is the stack empty? No, so we're good. And is the reverse bracket equal to the bracket at the top of the stack? No, it isn't. So this bracket sequence is invalid. So here's the pseudocode of the algorithm we just ran through. So if we let S be a stack, then for every bracket in our bracket string, we can get the reversed bracket for that current bracket easily. So if our bracket is a left bracket, push it onto the stack. Otherwise, we check if the stack is empty and if the element at the top of the stack is not equal to the reversed. If either of those conditions are true, then we return false. Otherwise, we return whether the stack is empty or not. And if it is empty, then we have a valid bracket sequence. Otherwise, we do not. I want to take a moment and look at the Tower of Hanoi, a very popular game amongst mathematicians and computer scientists, to see how it relates with stacks. The game is played as follows. You start with a pile of disks on the first peg on the left, and the objective of the game is to move all the disks to the rightmost disk pile. At each move, you can move the top disk of any pile to any other pile with a restriction that no disk be placed on top of a smaller disk. So we can think of each peg as a stack, because we're always moving the top element in a peg and placing it on another peg. So shall we play? I will let the animation run and you will see how each peg acts like a stack. It's pretty cool. So you just saw how transferring elements from one peg to another is exactly the same as popping a disk from one stack and pushing that same disk onto another stack, given that the disk you're placing on top is smaller. So that's really cool. Welcome to part 2 of 3 in the stack series. This is going to be a short video on one way to implement a stack. So stacks are often implemented as either arrays, singly linked lists, or even sometimes doubly linked lists. Here I will cover how to push nodes onto a stack with a singly linked list. Later on, we will look at the source code, which is actually written using a doubly linked list. Okay, to begin with, we need somewhere to start to be in our linked list. So we're going to point the head to a null node. This means that the stack is initially empty. Then the trick to creating a stack using a singly linked list is to insert the new elements before the head and not at the tail of the list. This way, we have pointers pointing in the correct direction when we need to pop elements off of the stack. As we will soon see, the next element, however, we need to push onto the stack is at 2, so let's do that. So we create a new node, adjust the head pointer to be the newest node, and then hook on the node's next pointer to where the head was before. And we use the same idea for 5 and also 13. Now let's have a look at popping elements. This isn't too hard either. Just move the head pointer to the next node and deallocate the last node. So here we pop the first node off the stack and set the node's reference to be null, so that it will be picked up by the garbage collector if you're coding in Java, and it will since there are no other references pointing to it. If you're in another programming language that requires you to explicitly deallocate and free memory yourself, like C or C++, now is the time to do that, or you will get memory leaks. Getting a memory leak in a data structure is one of the worst kinds of memory leaks, especially if it's a custom data structure that you intend on reusing. So keep watching out for that, not only in this video, but in all the data structures that we will be covering. If you see in an implementation that I'm not correctly cleaning up my memory, please point it out to me, or send a pull request to the GitHub repository so we can patch that. Okay, so we keep proceeding by removing the head and advancing the head pointer down to the next node. Pop again, and pop again. There we go, we've stopped popping, we've reached the last node, and the stack is now empty. Welcome to part 3 of 3 in the Stack series videos. Today we'll be looking at some source code for a very simple stack. So the source code can be found at github.com/williamfizet/data-structures. Make sure you understood part 1 and 2 of the Stack series before continuing, so you actually know how we implement a stack using a linked list. Also, if you like this video series and the implementation of the stack data structure I'm about to present to you, then please start this repository on GitHub so that others can have an easier time finding it as well. Here we are in the stack source code. This is an implementation in the Java programming language. So the first thing you may notice is here I have an instance variable of a linked list. This is the linked list provided by Java. In fact, it's a doubly linked list provided by Java. This is the linked list they provide in their package java.util that I will be using today instead of the one that I created in the linked list videos. This is just for portability in case you want to use this stack for whatever reason. So we have two constructors. We can create an empty stack, or we can create a stack with one initial element. This is occasionally useful. This first method, we can get the size of the stack. So to do that, we return the size of the internal linked list with all the elements of our stack. Easy. We can also check if the stack is empty by checking if the size is 0. So this next one is just push. So to push an element onto the stack, we just append that element as the last element in our internal linked list. Easy enough. We can also pop an element off the stack. So to do this, we check if the stack is empty. If it is, then we throw an empty stack exception because we can't pop an element off of an empty stack. That doesn't make sense. Similarly, the same thing with peek. We can't observe what the top element of the stack is if the stack is empty. And if it's not, then we can peek the last element of our list. And lastly, we can return an iterator to allow the user to iterate through our stack. This iterator returns an iterator for our linked list, which supports concurrent modification errors. So this was a really quick implementation of the stack. It's only like 50 lines of code. Let's talk about queues, probably one of the most useful data structures in computer science. So this is going to be part 1 of 3 in the queue series. So the outline of things we'll be looking at. First, we're going to begin by talking about queues and what they are. Then we're going to go into some complexity analysis concerning queues. Then we'll discuss the implementation details of enqueuing and dequeuing elements from a queue, followed by some source code at the very end in the last video. So a discussion about queues. So what exactly is a queue? So below you can see an image of a queue, but a queue is just a linear data structure that models a real-world queue, having 2 primary operations we can do, which are enqueuing and dequeuing. So every queue has a front and a back end. We insert elements through the back and remove through the front. Adding elements to the back of the queue is called enqueuing, and removing elements from the front of the queue is called dequeuing. However, there's a bit of terminology surrounding queues because there's not really any consistency. When we refer to enqueuing and dequeuing, many people will use multiple different terms. So enqueuing is also called adding, but also offering. A similar type of thing happens when we're talking about dequeuing. So this is when we remove things from the front of the queue. This is also called polling elements. However, some people will also refer to this as removing an element from the queue. But the problem with saying that is that it can cause some ambiguity. Did they mean removing from the front of the queue specifically, or from the entire queue? Make note that if I say removing, I'm going to be referring to removing from the front of the queue unless I say otherwise. So let's look at an example of how a queue works in some detail. However, first notice that I have labeled the queue's front and back ends so you know where I'm going to be enqueuing and dequeuing from respectively to avoid confusion. First instruction says to enqueue 12, so we add 12 to the end of the queue. Then dequeue, so we remove the first element from the front of the queue, which is 55. Another dequeue operation, this time we remove -1 from the front of the queue. So next, enqueue 7, so add 7 to the back of the queue. Dequeue, so remove the front element being 33. And lastly, enqueue -6, so add it to the back of the queue, just like that. So now that we know what a queue is, where does this data structure actually get used? Well, a classic example of where a queue gets used is to model a real-world queue where you're waiting in a line at a movie theater or in a line at a restaurant. For instance, have you ever been to, say, McDonald's, where all the caches are full, and as soon as one of them gets free, the next person in line gets to order food? Well, that's a queue. So queues can also be really useful if you have a sequence of elements. coming in, but you only need to keep track of, say, the X most recent elements. Well, you can add those elements to your queue, and once your queue gets larger than X elements, just dequeue, essentially. Queues are also often used in server management. So suppose for a moment that you have a web server that's idly waiting for requests from people to use your website, that at any given moment you can simultaneously serve up to 5 people, but no more. If 12 requests come in a short amount of time, you're not going to be able to process all of them as new ones come in. So what you do is you process the 5 that you're able to, and the remaining 7 get to chill in a queue waiting to be served. And whenever you finish processing a request, you dequeue in the next request, and then you start processing it, and you do this until the queue is empty. While you're doing this, if more requests come in to access your web page, well, you just add them to the end of the queue. Queues are also used in graph theory to perform a breadth-first search traversal on a graph, which is actually really useful. We're going to see this example in the next video. Alright, now concerning complexity analysis of a queue. So as we've seen, it's pretty obvious that enqueuing and dequeuing operations are constant time. There's also another operation on a queue I have not mentioned yet, and this is peaking. Peaking means that we're looking at the value at the front of the queue without removing it. This is also constant time. However, checking if an element is contained within the queue is linear time, since we would potentially need to scan through all of the elements. There's also element removal, not in the sense of dequeuing or polling, but in actually removing an element from the queue internally. This also requires linear time, since we would have to scan through all elements in the worst case. In this video, we're going to have a look at how queues are used to do a breadth-first search, and then we're going to look at the actual implementation details of how enqueuing and dequeuing elements works. Okay, on to the breadth-first search example. So a breadth-first search is an operation we can do on the graph to do a graph traversal. If you don't know what I mean when I say graph, I mean a network, not a bar graph or a line graph or anything like that. But first I should explain the breadth-first search. In the breadth-first search, the objective is to start at a node and traverse the entire graph. First by visiting all the neighbors of the starting node, and then visiting all the neighbors of the first node you visited, and then all the neighbors of the second node you visited, and so on and so forth, expanding through all the neighbors as you go. So you can think of each iteration of the breadth-first search as expanding the frontier from one node outwards at each iteration as you go on. So let's begin our breadth-first search at node 0. So I'm going to label node 0 as yellow and put it in the frontier, or the visiting group. And now I'm going to visit all the neighbors of 0, being 1 and 9, and add those to the frontier. And then I'm going to visit all the neighbors of 1 and 9, being only 8. Similarly for 8, so 7, then visit all the neighbors of 7. So I added a bunch of elements to my frontier. And now visit all the neighbors of the yellow nodes. And now we're done our breadth-first search because we no longer have any elements on the frontier. Notice that there's 12 that is still unvisited because 12 is a loner node on an island all by itself, so we're not able to reach it via breadth-first search, which is fine. So suppose we wanted to actually code a breadth-first search, how would that be done? Well, the idea is to use a queue. So first we add the starting node to our queue, and then we mark the starting node as visited, And while our queue is not empty, we pull an element from our queue, or dequeuing, and then for every neighbor of this node we just dequeued, if the neighbor has not been visited yet, mark the neighbor as visited and add it to the queue. So now we have a way of processing all the nodes in our graph in a breadth first search order. Really, really useful. A very, very popular graph traversal algorithm. So now let's look at implementation of queues. So let's begin with enqueuing. So it turns out that you can implement the queue abstract data type in multiple different ways. But the most popular methods are to either use arrays, singly linked lists, or doubly linked lists. If you're using an array, you have to make sure your array is going to be big enough if it's a static array. If it's a dynamic array, then you'll be fine. But here I'm going to show you how to do it with a singly linked list, but in the source code we're using a doubly linked list, so stay tuned for that. In a singly linked list, we're going to have a head pointer and a tail pointer. So initially they're both null. But as we enqueue, we just add the first node, so nothing really interesting is going on right now. But as we enqueue more elements, you can see that we're pushing the tail pointer forward, so we're adding a node and then getting the tail pointer to point to the next node. Now dequeuing is a bit of the opposite. Instead of pushing the tail forward, we're going to be pushing the head forward. So push the head forward one, and then the element that was left over was the one we wanted to dequeue and return to the user. So when we push the head pointer forward, we set the last node to null so that it can be picked up by the garbage collector if you're in Java. If you're in another programming language which requires you to explicitly deallocate or free memory yourself, like C or C++, now is the time to do that. So you see, as we keep dequeuing, we're just pushing the head forward and forward again. And at the very end, if we add a bunch of elements and then remove them all, then the head and the tail again point to null, which is where we started. Alright, now it's time to have a look at some source code for a queue. So I implemented a queue, and you can find the source code at the following link on github.com/myusername/data-structures. Also make sure you have watched and understood parts 1 and 2 from the queue series before continuing. Alright, here we are looking at some source code for a queue. So this source code is in the Java programming language, although you can probably translate it into any programming language that you need. So the first thing to remark is I have an instance variable here of a linked list. So this is Java's implementation of a doubly linked list. We also use this in the stack implementation. As you'll see, the queue and the stack implementations are very, very similar. So here I have two constructors, one that'll create just an empty queue and another optional one which will create a queue but with a first element. In fact, I should probably check if this is null, but we might want to allow null elements, so let's just leave it like that. So the next method is the size. It just gets the size of the linked list. And similarly, this checks if the linked list is empty. Those are both pretty self-explanatory. Okay, next interesting method is the peek method. The peek method returns the element that's at the front of the queue, but it will throw an error if your queue is empty, because you can't peek anything when your queue is empty. Similarly for poll, this will poll the element at the front of the queue, but unlike peek, will actually remove the element from the queue. So next, we scroll down a little bit, I have offer, which adds an element to the back of the queue. I guess I am allowing for null elements, so if you don't want null elements, just put an if statement and throw an error or something. So the poll removed from the front, and you can see offer adds to the back. So remove first and add last. And the last method in here is an iterator in case you want to be able to iterate through all the elements in your queue. Very short and very simple implementation, just under 50 lines of code. You can create a queue. Although there are faster ways of creating queues, especially with arrays. The idea with arrays, especially static arrays, if you know the maximum amount of elements that will be in your queue at any given time, then you can create an array of that maximum size and have pointers to the front and the back positions in your queue, and add and remove elements based on the relative position of those pointers. If you ever get to a position where you're running off the edge of your array, then you can loop around to the front of the array and keep processing elements like that. This is a lot faster than having to maintain references to the next node, such as in a linked list. So I guess I'll say that's your homework, is to create a static array based queue. Today we're going to talk about everything to do with priority queues, from where they're used to how they're implemented, and towards the end we'll also have a look at some source code. Along with all the priority queue stuff, we're also going to talk about heaps, since both topics are closely related, although not the same. So the outline for the priority queue series is we're going to start with the basics, talking about what are priority queues and why they're useful. Then we'll move on to some common operations we do on priority queues, and also discuss how we can turn min priority queues into max priority queues, followed by some complexity analysis. Then we'll talk about common ways we implement priority queues. Most people think heaps are the only way we can implement a priority queue, or that priority queues somehow are heaps. I want to dispel that confusion. Next, we're going to go into some great detail about how to implement the priority queue using a binary heap. There we'll look at methods of syncing and swimming nodes up and down our heap. These terms are used to, again, shuffle around elements in a binary heap. As part of the implementation explanation, I also go over how to poll and add elements. So there's a lot to cover, so let's get started. Discussion and examples. This is going to be part 1 of 5 in the priority queue series. So what is a priority queue? A priority queue is an abstract data type that operates similar to a normal queue, except for the fact that every element has a certain priority. So elements with a higher priority come out of the priority queue first. As a side note, I would like to remark that priority queues only support elements that are comparable, meaning that the data we insert into the priority queue must be ordered in some way, either from least to greatest or greatest to least. This is so we can assign relative priorities between elements. Okay, let's go into an example. So suppose we have all these values that we inserted into our priority queue on the right, and that we imposed an ordering on the numbers such that we want to order them from least to greatest. So the smaller numbers have a higher priority than the bigger ones. So they will be removed from the priority queue first. Suppose we have now a list of instructions. So what the poll operation means is remove the element that has the highest priority in our priority queue. So let's see how this works. So if I say poll, then I remove the element with the highest priority, which happened to be 1. Now I say add 2, so we add 2 to our priority queue, and poll. So next we poll the smallest element in our priority queue, and that happened to be the 2 we just added. Next we add 4, poll the smallest, this is 3, add 5, also add 9, and then poll the rest. So as I pull the rest, I'm continuously grabbing the smallest element in the priority queue. So it turns out that as we added and pulled numbers, we got an ordered sequence. This is a coincidence, actually. As we add and pull numbers from the priority queue, we do not necessarily end up getting an ordered sequence. We are only guaranteed that the next number that is removed from the priority queue is the smallest number that was currently in the priority queue. So how does the priority queue know which is the next smallest number to remove? As humans, we could see the numbers visually inside the priority queue and look and know what one was the smallest the poll operation was going to return. But fundamentally, how does the machine know this? Does it resort all the elements inside the priority queue before each poll operation? No, in fact, that would be highly ineffective. Instead, it uses what is called a heap. So the next big question then is, what is a heap? Usually I make up my own definitions, but I really like this one from Wiki. A heap is a tree-based data structure that satisfies the heap invariant, also called the heap property. If A is a parent node of B, then A is ordered with respect to B for all nodes A and B in the heap. What this means is the value of the parent node is always greater than or equal to the value of the child node for all nodes, or the other way around, that the value of the parent node is less than or equal to the value of the child node for all nodes. This means we end up getting 2 types of heaps, max heaps and min heaps. So max heaps are the one where the parent node is always greater than its children, and the min heap is the opposite. So both of the following are actually binary heaps. Binary because every node has exactly 2 children. And the children you cannot see are null values I have not drawn in. So why are we interested in heaps? Well, heaps form the canonical underlying data structure for priority queues. So much so that priority queues are sometimes called heaps, although this isn't technically correct, since the priority queue again is an abstract data type, meaning it can be implemented with other data structures also. Okay, we're going to play a little game. I'm going to give you some structures, and you need to tell me whether it is a heap or not. So inspect the following structure and try to determine whether it's a heap or not. You can pause the video if you like, but I'm just going to give you a short moment here. No, we have a violation of the heap invariant in this tree, so it's not a heap. Is this structure a heap? Yes, it is a heap because it satisfies the heap invariant and it is a tree. So we often see heaps like these in what are called binomial heaps. Note that heaps aren't necessarily binary heaps, they can have any number of branches. On to our next one. So is this a valid heap? Yeah, it's a valid heap, because even though this one is strangely structured, we're free to move around the visual representation of the nodes as we please. So yeah, it's a valid heap. How about this one? No, this structure is actually not even a tree because it contains the cycles. All heaps must be trees. What about this one? Yeah, it's a heap. What about this one? Also a heap, because it satisfies the heap invariant that all nodes are less than or equal to or greater than or equal to its parent. How about this one? No, it's not a heap because it does not satisfy the heap invariant. However, if we do change the root to be 10, then we can satisfy the heap invariant via a min heap. Or rather, sorry, a max heap. So when and where is a priority queue and a heap used? Probably one of the most popular places we see priority queues is in Dijkstra's shortest path algorithm to fetch the next nodes we explore. Priority queues are really handy anytime you also need a behavior in which you need to dynamically fetch the next best or the next worst element. They're also used in Huffman encoding, which is often used for lossless data compression. Many best first search algorithms use priority queues in their implementation to continuously, again, grab the next most promising node in the graph as it's being traversed. And finally, we also see priority queues in Prim's minimum spanning tree algorithm on directed graphs. So it seems priority queues are really important, especially for graph theory algorithms, which is where we see them often. Okay, on to some complexity with priority queues implemented as a binary heap. So to begin with, there exists a method to construct a binary heap from an unordered array in linear time. We're not going to cover this algorithm, but it's pretty cool, and it forms the basis for the sorting algorithm heap sort. Next is pulling or removing an element from the root of the heap. This takes logarithmic time because you need to restore the heap invariant, which can take up to logarithmic time. So peeking or seeing the value at the top of our heap can take constant time, which is really nice. Adding an element to our heap takes logarithmic time, again because we possibly have to reshuffle the heap by bubbling up the value, as we will see in a later video. Then there are a few more operations we can do on priority queues. So removing an element which is not the root element. So the naive way of removing an element in a heap is to do a linear scan to find the item's position and then remove it. Well, the problem with this is it can be extremely slow in some situations, especially if you're removing a lot. But generally you don't do this and it's not a problem, which is why most implementations are just, I guess, lazy and do the linear scan solution. However, there does exist a way to reduce the removing time complexity, which I will go over later in a later video in great detail in this video series, so stay tuned for that. This method uses a hash table to reduce the removing time complexity to be logarithmic, which is super critical actually if you're removing as much as you are adding. Now the naive method to check containment within a heap, a binary heap, is linear. Again, you just scan through all the elements, but with the help of a hash table, we can reduce this to be a constant time, which is super neat, especially if we use the hash table implementation for the removing speed up. We get that as a free bonus. The downside, however, to using the hash table implementation is that it does require an extra linear space factor, and it does add some constant overhead because you're accessing your table a lot during swaps. Today we're going to talk about turning min priority queues into max priority queues. This is part 2 of 5 in the priority queue series. So you may already be asking yourself, why is it important that I know how to convert a min priority queue into a max priority queue? Well, here's the problem. Often in the standard library of most programming languages, they will only provide you with either a max priority queue or a min priority queue. Usually it's a min priority queue, which sorts elements by the smallest element first, but sometimes we need the max priority queue depending on what we're programming. So how do we do this? How do we convert one type of priority queue into another type? Well, a hack we can use is to abuse the fact that all elements in a priority queue must implement some sort of comparable interface, which we can simply negate or invert to get the other type of heap. Let's look at some examples. Suppose for a moment that we have a priority queue consisting of elements that are on the right side of this screen, and that these are in a min priority queue. So if x and y are numbers in the priority queue, and x is less than or equal to y, then x will come out of the priority queue before y. The negation of this is x is greater than or equal to y, and so y then comes out before x, because all these elements are still in the priority queue. Wait a moment, you say. Isn't the negation of x is less than or equal to y just x greater than y, and not x is greater than or equal to y? Well, not for comparators. You see, if x is equal to y, whether or not the comparator is negated, x should still equal y. So now let's see what happens when we pull all these elements out of the priority queue with our negated comparator. So first we would get 13 because it's the greatest, and next comes 11, 7, 5, 3, and 2. An alternative method for numbers is to negate the number before you insert it and negate it again when it comes out. This is a hack specific to numbers, but it's pretty nice. So let's see how that works. So let's negate all the numbers inside our priority queue. And now we can see that definitely minus 13 is the smallest, so it should come out first. So minus 13 indeed comes out first, but now we have to negate it and we get 13. Everything is good so far. Next is minus 11, so really positive 11, and so on, minus 7, 7, and so on. Just so keep polling and then renegate the value to get it out of the priority queue. It's a pretty neat hack. Okay, now let's look at another examples using strings. So suppose lex is a comparator for strings, which sorts strings in lexicographic order. This is the default for most programming languages. Then let's call nlex be the negation of lex. And also let's assign s1 and s2 to be some non-null strings. So below you can see that our comparator assigns minus 1 if s1 is less than s2 lexicographically, 0 if they're equal lexicographically, and plus 1 if s1 is greater than s2 lexicographically. And then nlex is just the negation of that. So just to break it down, lex sorts strings lexicographically, but we're interested in negating lex so that longer strings appear before shorter strings, and also that strings with letters at the end of the alphabet appear before those containing letters at the beginning of the alphabet. I think I said that right. This would in effect turn a min heap into a max heap. Let's look at a concrete example. So by adding all the numbers on the right to our priority queue with a lexicographic comparator, here's the ordering we should expect. First we get A because it's the shortest string that has characters appearing closest to the start of the alphabet. Then it comes out B, then FZ, then X, then XR, and XX. So now let's do the same thing but with nlex. And we should hopefully obtain the opposite sequence in reverse order. And then we get XX, XR, X, F, Z, B, and A. So it did exactly what we intended it to do. Today we're going to talk about adding elements to a binary heap. This is part 3 of 5 in the priority queue series. We'll get to adding elements to our binary heap shortly, but first there's some important terminology and concepts leading to that, which we need to go over prior to add elements effectively to our priority queue. Okay, so a very popular way to implement a priority queue is to use some kind of heap. This is because heaps are the data structure which give us the best possible time complexity for the operations we need to perform with a priority queue. However, I want to make this clear. A priority queue is not a heap. A priority queue is an abstract data type that defines the behavior a priority queue should have. The heap just lets us actually implement that behavior. As an example, we could use an unordered list to achieve the same behavior we want for a priority queue, but this would not give us the best possible time complexity. So concerning heaps, there are many different types of heaps, including binary heaps, Fibonacci heaps, binomial heaps, pairing heaps, and so on and so on. But for simplicity, we're just going to use the binary heap. A binary heap is a binary tree that supports the heap invariant. In a binary tree, every node has exactly 2 children. So the following structure is a binary heap, which satisfies the heap property that every parent's value is greater than or equal to that of the child, that every node has exactly 2 children. Well, no, you may be thinking, the bottom nodes, also known as leaves, don't have children. Well, actually, yes they do. Here they are. They're the null children in gray, but for simplicity I won't draw those because they're annoying to draw. Okay. The next important bit of terminology we need to understand is the complete binary tree property. The complete binary tree property means that at every level, except possibly the last, is completely filled, and that all the nodes are as far left as possible in the binary tree. As you will see, when we insert nodes, we always insert them at the bottom row, as far left to meet this complete binary tree property. Maintaining the complete binary tree property is very, very important because it gives us an insertion point no matter what the heap looks like or what values are in it. The next node we insert will go into the hollow circle, and the next one will go to the right of it, and so on until eventually we fill up the row, at which point we need to start a new row. So the insertion point is very important. One last thing before we actually get into how to add values into our binary heap is we need to understand how to represent one of these binary heaps. And there is a canonical way of doing this, which is to use an array actually. So using an array is very convenient actually because when we're maintaining this complete tree property, the insertion position is just the last position in our array. However, this isn't the only way we can represent a heap. We can also represent a heap using objects and pointers and recursively add and remove nodes as needed, but the array construction is very elegant and also very, very fast. So on the left is the index tree, just to help you visualize the position of each node in the array, and on the right is the actual tree. Remark that as you read elements in the array from left to right, it's as though you're pacing through the heap one layer at a time. So if we're at node 9, which is index 0, we're at the top. If we're at node 8, we're at position 1. Then as I keep moving along, you can see that we're just pacing through the array going from left to right. So it's very convenient that way. And also, another interesting property of storing a binary heap in an array is that you can easily access all the children and parent nodes. So suppose I is the index of a parent node. Then the left child is going to be at index 2 times I plus 1. And the right child of that node is going to be at 2i plus 2. This is 0 base. If it's 1 base, then you would just subtract 1. So suppose we have node 7, which is highlighted in purple. Well, its index is 2, so by our formula, the left child of 7 should be located at 2 times 2 plus 1, or 5. And if we look at index 5, we expect to get 1, and if we look at the right child, we should expect to get 2 times 2 plus 2, or 6. If we look in our array, this gives us the value of 2. So using this technique, we have all we need to manipulate the nodes in our array. In the source code I will be presenting in part 5 of the series, we will see that I use this representation for simplicity. Alright, so now we want to know, how do I add nodes to a binary heap and maintain the heap invariant? Because if we add nodes to our binary tree and we don't maintain the heap property, well, the binary heap is useless. We'll do some examples. On the left I have some instructions which tell us what values we need to insert into the heap. The first value is a 1, which we can see, which should actually appear at the root since we're dealing with a min heap. But instead of inserting 1 at the root directly, what we do is we put 1 at the bottom left of the tree in the insertion position I was talking about and perform what's called bubbling up, as my undergrad prof loved to say. This is sometimes called swimming or even sifting up. All really cool names for a really neat operation. So we insert 1 in the insertion position, but now we're in violation of the heap invariant, since 1 is less than 7, but 1 is found below 7. So what do? What we do is we swap 1 and 7, like so. But now we're still in violation of the heap property, since 1 is a child of 6, but 1 is less than 6. So what do? We swap them. But yet again, in violation of the heap property, so we swap, and now 1 is at the root, where it should be, and now the heap invariant is satisfied, and we can stop swimming or bubbling up or whatever you want to call it. So the next one is 13, so as usual, begin by putting it in the insertion position, and now we need to satisfy the heap invariant, so bubble up 13. Notice that we're no longer in violation of the heap property since 14 is less than 13 and 13 is less than 12, so 13 is actually in its correct position. Sometimes we don't have to bubble up our elements that much. The next values we need to insert are 4, 0, and 10. Try seeing where these end up. Pause the video if you need. It's a good little exercise. But I will keep going for now. So 4 goes in the insertion spot left of all the nodes on its layer, and we bubble it up until we can't anymore. And we stop, the heap property is satisfied. Next is 0, my favorite number. Of course I've arranged that 0 be at the top of the tree, as you will see. So right now we're in violation of the heap invariant, so let us bubble up. And like magic, 0 is at the top of the tree. Next is to insert 10. The next number is 10, so we put it at insertion position. And however, this does not violate the heap invariant, so we do nothing. Today we're going to be looking at how to remove elements from a binary heap. This is part 4 of 5 in the priority queue series. Make sure you watch the last video so you understand the underlying structure of the binary heap. So let's get started. In general, with heaps, we always want to remove the root value because it's the node of interest. It's the one with the highest priority because it's the smallest or the largest value. When we remove the root, we call it polling. A special thing about removing the root is that we don't need to search for its index, because in an array implementation, it has position or index 0. So when I say poll, in red we have the node we want to remove, and in purple is the one we're going to swap it with. So the node in purple is always going to be the one at the end of our array, which we also have its index. So we swap them, we get rid of the 1, and now, since 10 is at the top, well, we're not satisfying the heap invariant. So we need to make sure that the heap invariant is satisfied. So we need to do what's called bubbling down now instead of bubbling up. So what we do is we look at 10's children, 5 and 1, and we select the smallest, and we swap with the smallest. So 10 would go to 1. So make sure you default selecting the left node in case there was a tie. So as you can see, 10's children are 2 and 2. They're both equal, so we're going to select the left node to break the tie. And now we bubble down 10 again, and now the heap invariant is satisfied. Now we want to remove the value 12. So polling was removing the element at the root, but 12 is not at the root. However, we still want to be able to remove 12. So what we do is we have to search for 12 in our tree, even though we don't know its position yet. So we start at 1, and we do a linear scan through all our elements until we find 12. So 5 is not 12, 2 is not 12, and so on until find 12. And now we found 12, and now we know where its position is, so we can mark it as the node we want to remove, and also swap it with the purple node being the last node in our tree. Swap them, remove the 12, and now we're in violation of the heap invariant. So now we want to bubble up 3 until the heap invariant is satisfied. And now we've satisfied the heap invariant, so we can stop. Now we want to remove 3, same thing as last time, search for 3 in the tree. 3 wasn't far, it was just 2 nodes away. So now, to remove an element, again, swap it with the last node in the tree, drop it. But now the question is, do we bubble up or bubble down the value? Because you don't really know what the value of the node in the last position is when you're swapping it in. So do we bubble up or bubble down? Well, we already satisfied the heap invariant from above, so we need to bubble down 15. So 5 was smaller, so we swapped it with 5. Now 8 is smaller, so we swap it with 8. And again, the heap invariant is satisfied. Now we want to poll, so mark the root node red, swap it, remove the 1, and now we would want to bubble down, and the heap invariant is satisfied. Now we want to remove 6, so search for 6 in our tree. Okay, we have found 6, and do the swap, remove 6. Now do we bubble up or bubble down? The answer is neither, the heap invariant is already satisfied, so we don't even need to touch our node. We got lucky. Okay, so from all this polling and removing, we can conclude the following. That polling takes logarithmic time, since we're removing the root and we already know where to find it, and also that removing a random node can take up to linear time, since we have to actually find the index of that node we want to remove before removing it. However, if you're as dissatisfied with this linear removal as I am, you'd figure out that there has to be a better way. And indeed there is, and I'm about to show you a hack to improve this complexity to be logarithmic in the general case. So stay tuned. Okay, so now we're going to look at how to remove nodes from a heap with the improved time complexity. To do this, we'll need to make use of a hash table, a data structure I have not yet covered, so buckle up, things are about to get a little wild. I promise I'll cover the hash table thoroughly in a later video, but right now it's going to look like magic. Back to the central issue, we have a bunch of nodes scattered across our heap at some positions, and instead of doing a linear scan to find out where the node we want to remove is, we just want to be able to do a lookup and figure that out. The way we're going to do this is that every node is going to be mapped to the index it's found at. So when we want to remove a particular node, we just look up its index instead of doing a linear scan. Sounds good, right? That sounds great, except for one caveat or two. What about if the heap has multiple nodes with the same value? What problems would that cause? Well, just a few, but nothing we can't handle. To begin with, let's talk about how we can deal with the multiple value problem. Well, instead of mapping one value to one position, we will map one value to multiple positions. And we can do this by maintaining a set or a tree set of indices for which a particular node value or key, if you want, maps to. Let's look at an example. Okay, so observe the blue heap. Remark that it has repeated values. Namely, we can see that the 2 is there 3 times, 7 is there twice, 11 and 13 once. Below I have drawn the index tree, a tree which can help us determine the index position of a node in the tree. 11, for example, is at index 3, 13 at index 5, and the first 2 at index 0. On the left is the hash table with the key value pairs. Notice that 2 is found in 3 positions, 0, 2, and 6, while 7 is found in 2 positions, 1 and 4, and so on. So this is how we're going to keep track of the positions of the values in the tree. If nodes start moving in the tree, we also need to keep track of that. For example, if a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. And that's it. Okay, so this all sounds great. We keep track of repeated values by maintaining a set of indices a particular node with a particular value is found at. But now let's ask a further question. If we want to remove a repeated node in our heap, which node do we remove, and does it matter? Because if we look in our heap right here, there's 3 possible 2 values we could remove. Does it matter which one we remove? The answer is no, it does not matter. As long as, in the end, we satisfy the heap invariant. That's the most important thing. So let's look at an example, not just of removing, but also of adding and pulling elements with this new scheme I just proposed. It's not that hard, trust me. So first one, we want to insert 3. So we need to place 3 at the bottom of the heap in the insertion position. We also need to track where the new node is, so we add 3 to our table, along with its position, which happens to be at index 7. Look at the index tree in gray to confirm this. Now that 3 has been inserted, we need to make sure the heap invariant is satisfied. Currently it is not. So what we do is we bubble up 3. The parent of 3 is 11, which is greater than 3, so we need to swap those two nodes. I've highlighted the 7 in the index tree because it maps to 3 in the heap and 3 in the index tree because it maps to the value 11. Now swap those both in the tree and in the table. Awesome. Now the heap variant is still not satisfied, so do a similar thing for the node above. We grab the parent and do a swap in the tree and the table. And now the heap invariant is satisfied. So 3 has been inserted successfully. The next instruction is to remove 2 from the heap. So which 2 should we remove? Well, as I said, it doesn't matter as long as we satisfy the heap invariant in the end. If we remove the last 2, we can immediately satisfy the heap invariant with one swap. But for learning purposes, I will simply remove the first one found in our set, which happens to be located at index 0. So we want to remove the 2 at position 0. So how do we remove a node again? So we did a lookup, so we didn't have to do that linear scan, which was nice. And now we swap it with the last node, which happens to be 11. We remove the last node. Now we need to satisfy the heap invariant. So we need to bubble down 11. So we look at 11's children, which happens to be 3 and 2. 2 is smaller, so it's the one we're going to swap with. So swap it in the table and in the tree. Now we are still not in satisfaction of the heap invariant, so look at 11's children being 13 and 2. 2 is smaller, so swap it with 2. And that's it, we're done. The last instruction says to pull, so get the value at the root, which is 2, and swap it with 11. Get rid of the 2, and bubble down 11. So as you can see, we're constantly updating our table, but still doing the same operations. This is part 5 of 5 in the priority queue series, and we're going to have a look at some source code for the priority queue today. So if you want the source code, here's a GitHub link with all the data structures in this series. The priority queue is one of them. Also make sure you've watched parts 1 to 4 so you can actually understand what's going on. Alright, let's dive into the code. Alright, here we are inside the source code. So notice that inside my priority queue, the types of elements I'm allowing inside my priority queue have to be comparable elements, as we talked about. So if they implement the comparable interface, then we are going to allow them inside our queue. So this is anything like strings, integers, anything with a comparable interface. So let's have a look at some of the instance variables. So I have the heap size, so this is the number of elements currently inside the heap. But then I also have another instance variable, which is the heap capacity. So this is going to be the size of the list that we have for our elements, which may be larger than the heap size is. And this is the actual heap, and we're going to be maintaining it as a dynamic list of elements using Java's list. Next, for our log of n removals, I'm also going to keep track of this map. and it's going to map an element to a tree set of integers. So these are going to be all the positions inside our heap, which we can find this element t. Alright, next I've got a few different constructors for our priority queue. We can just create a priority queue, and by default I'm creating an initially empty priority queue with a capacity of 1. But I also allow you to create a priority queue with a defined initial capacity, which actually is more useful, because then we don't have to keep expanding our dynamic list every time. So I would recommend this. But also, even better, is if you know all the elements that are going to be inside your heap, you can actually construct the priority queue in linear time using an operation called heapify, which I didn't talk about in the slides, but can be very, very useful. So this just has all the usual setup stuff. Here I'm adding all the elements to the map, but also to the heap. And then here's the heapify process. So we start at about halfway through the heap size, and then we start decreasing, and then we sync all the elements. And you're like, wait a second, isn't this sync a logarithmic removal? Well, yes it is in the general case, but not if we're doing it in this fashion. I put a link to this paper up here just because the heapify operation isn't quite intuitive why it has this linear complexity. And if you look at the analysis in the paper, you will end up seeing that the complexity boils down to a convergent series, and that's why we get a constant and can say it's linear time. But in general, this isn't what you might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just use our add method to add the elements one at a time. And this will give you an n-log n bound. But definitely use the heapify whenever possible. Okay, now some pretty simple methods. We have isEmpty, just returns true or false if the heap is empty or not. Then clear, so when we clear the heap, we remove all the elements inside our heap array, but also inside our map. So that's why I call map.clear. Size returns a size, it's pretty simple. Peek, the first really useful method, just looks at the top of our priority queue, and if it's empty, returns null. Otherwise, we do a lookup at the first index inside our heap and return it, because it's the root node. Poll, similar to peek, except that we're going to remove the very first element, and we're also going to return it, because we want that information. Next, contains. So because we have a map with all our elements, we can do a map lookup to see if our elements inside the heap. And this reduces our complexity from linear, in which case we have to do a linear scan through all elements to check containment, to constant time, which is remarkable. But in the general case, people don't usually maintain this map. I just wanted to do it just to show you guys that it is possible. Although the map does add a lot of constant overhead you may or may not want. I personally find that the overhead is quite a lot, and I usually don't really remove things very frequently from maps, so it might not be entirely worth it. But it's up to you. If you're doing as many additions as you are removals, then definitely worth it. Alright, now let's have a look at the add method. So this method adds an element to the priority queue, and that element cannot be null. So what we do is, first we check if our heap size is less than capacity. Otherwise, we have to expand our capacity of the heap. Next, we make sure we add it to the map so we keep track of it, and then we swim it up. Remember that we have to swim a node up because we add it to the very end of our list, and so we have to adjust where it goes inside our heap by swimming upwards. This next method, called less, is a helper method which helps me check if node I is less than or equal to node j, and this uses the fact that both elements, node 1 and node 2, are comparable, so we can invoke the compare to method. If we go back up, that comes from this interface, the comparable interface, which we needed. So let's scroll back down. Alright. So it returns true if I is less than or equal to j. Awesome. So next, this is the bottom up node swim. So we are going to try to swim node k. So first we grab the parent of node k, and we can do that by solving for the parent. So remember that I'm working in, I'm starting at 0. Some people like to start their heaps indexed at 1. I like everything 0 based. So I get the parent, which is at this position, k minus 1 divided by 2, because we're going upwards. And while k is still greater than 0, so we're not at the root, and we are less than our parent, then we want to swim upwards. So we're going to swap the nodes, parent and k, and then k is going to become the new parent. And then we have to get the parent of k once more. And then we keep doing this, going up our heap and swapping nodes. So that's how you do the swim. So the sink is similar, but a little different. So this is a top-down node sink. And here we want to sink node k, and what we do is I grab the left node, but I also grab the right node. Remember, we're working 0 based, so plus 1 plus 2 instead of plus 0 and plus 1. And then I need to figure out which is less. Either it's going to be the left one or the right one. And I assume to start with that the left one is going to be smaller than the right one. And here I correct that hypothesis in case it was false. So I check that the right node is within the size of the heap, and if the right node is less than the left node, then the smallest one is going to be the right node. And our stopping condition is that we are outside the bounds of the tree, or we can't sink any more. And we kind of do a similar thing, we swap, and then k is the next smallest. Kind of like we did in the last method also. So the swap method, I made an explicit method to swap because I also have to swap things inside the map and then set the values also. And this is really what adds a lot of the overhead for the map, is the fact that every time we call the swap method, we also have to swap things inside the map, which can be a lot of overhead, really. Technically, maps are constant lookup times, but the fact that you're doing all this internal hashing and collisions and whatnot, it can get costly. So remove. So if the element is null, return false, so we know we don't have any null elements inside our heap. So this is how you would do a linear removal in linear time. I commented out in case you want to revert back and remove the map and whatnot. Is you would scan through all the elements, and once you find the element you were looking for, just remove it at that index and return true. Otherwise, we're going to use our map. So get the index of wherever one of the elements are, and if it exists, then remove it at the index. Okay, now let's have a look at the remove at method. So this is what I covered in the last video. So if our heap is empty, well, can't really remove anything. Otherwise, we're going to swap the index of what we want to remove with the last element, which is going to be at heap size. And then we're going to kill off that node and also remove it from our map. So if it so happened that I was equal to the heap size, meaning we just removed the very last element in our heap, just return the removed data. Otherwise, when we did the swap, we have to either sync that node up or down. And I'm kind of too lazy to check whether I need to sync or swim, so I just try both. So first I try syncing, and then if nothing happened, then I try swimming downwards. And in either case, return the removed data. Perfect. So this just readjusts where the swapped node position goes, either bubble up or bubble down. This method is just a method I use in my testing framework to make sure everything is good. So it checks essentially the integrity of the minimum heap. So initially you call this method with k equals 0, and that starts at the root, and it's going to recursively go down the tree and check, are we maintaining the heap invariant property, which we need. So our base case is going to be that k is outside the heap size, and if so, we're just going to return true. Otherwise, get our children left and right, and now we're going to make sure that k is less than both our children, and if that's not the case, return false. And if we ever return false, because we have an AND statement when we're recursing right here, that gets propagated throughout the recursion, and this whole method will return false. Otherwise, if everything returns true and hits the base case, then we know for sure it's in a minimum heap. Okay, these last few methods are just map helper methods, so things to add things into the map, how to remove elements from the map, and so on. And what I'm doing here is I'm using a tree set to add and remove elements, because I know the tree set implementation in Java is a balanced binary search tree, so all operations on tree sets are logarithmic, which is really nice. So you guys can have a look at those in more detail. It just gets values, removes values, and lastly do a map swap. So yeah, it swaps values in the heap, or in the map rather. So you guys can have a look at those in more detail. But I pretty much covered everything about the priority queue. Alright, time to talk about the union find, also sometimes called the disjoint set. This is my favorite data structure. So let's get started. So an outline of things we'll be covering about the union find. First I'll be going over a motivating example, magnets, just to illustrate how useful the union find can be. Then we'll go over a classic example of an algorithm which uses the union find, specifically Kruskal's minimum spanning tree algorithm, which is very elegant, and you'll see why it needs the union find to get the complexity it has. Then we're going to go into some detail concerning the find and the union operations, the two core operations the union find uses. And finally, we'll have a look at path compression, what gives us the really nice amortized constant time the union find provides. Okay, let's dive into some discussion examples concerning the union find. So what is a union find? So the union find is a data structure that tracks elements which are split into one or more disjoint sets. And the union find has two primary operations, find and union. What find does is, given an element, the union find will tell you what group that element belongs to. And union merges two groups together. So if we have this example with magnets, suppose all these gray rectangles you see on the screen are magnets. And also suppose that the magnets have a very high attraction to each other, meaning they want to merge together to form some sort of configuration. So if I label all the magnets and give them numbers, and we start merging the magnets with the highest attraction, first we're going to merge 6 and 8 together since they're the closest. So in our union find, we would say union 6 and 8. And when we do a lookup to find out which groups 6 and 8 belong to, they would belong to the blue group. Now perhaps 2, 3 and 4 are highly attracted to each other, so they would form a group. So they would form the yellow group. And perhaps 10, 13, and 14 would also form a group. And this keeps on going, and we unify magnets into groups. And perhaps we merge some magnets onto already existing groups, so we unify a gray magnet, which is just a magnet in its own group, to an already existing group. But also we can unify groups of magnets which are different colors, and then we assign it an arbitrary color, so blue, so suddenly everything in the yellow group went into the blue group. And now when we would do a lookup in our union find to determine which group say 2, 3, or 4 are, now we would say, you're in the blue group. And the union find does all this merging and finding in a very efficient manner, which is why it's so handy to have around. I'm not explaining currently how that works, we'll get into that in a later video. This is just a motivating example. So where are other places that the union find is used? Well, we see the union find again in Kruskal's minimum spanning tree algorithm. In another problem called grid percolation, where there's a bunch of dots on a grid and we're trying to see if there's a path from the bottom of the grid to the top of the grid or vice versa, then the union find lets us do that efficiently by merging together paths. Also, similar kind of problem in network connectivity are two vertices in a graph connected to each other through a series of edges. And also, perhaps in some more advanced examples like the least common ancestor in a tree, and also in image processing. So what kind of complexity can we attribute to the union find? The complexity is excellent. So its construction is linear time, which isn't actually bad at all. Then the union, find, get component, and check if connected operations all happened in what's called amortized constant time. So almost constant time, although not quite constant time. And finally, count components. Well, we can determine how many components, or in our magnet examples, how many different groups of magnets we have, and we can do that in constant time, which is really, really great. Okay, let's talk about a really neat application of the union find, which is Kruskal's minimum spanning tree algorithm. So you might be asking yourself, what is a minimum spanning tree? So if we're given some graph with some vertices and some edges, the minimum spanning tree is a subset of the edges which connects to all the vertices and does so at a minimal cost. So if this is our graph with some edges and some vertices, then a possible minimum spanning tree is the following and has edge weight 14, well, total edge weight 14. Note that the minimum spanning tree is not necessarily unique, so if there is another minimum spanning tree, it will also have a total weight of 14. So how does it work? So we can break it up into 3 steps essentially. So the first step is easy. Just take all our edges and sort them by ascending edge weight. Next thing we want to do is we want to walk through the sorted edges and compare the 2 nodes that the edge belongs to. And if the nodes already belong to the same group, then we want to ignore it because it'll create a cycle in our minimum spanning tree, which we don't want. Otherwise, we want to unify the 2 groups those nodes belong to and keep going. And we keep doing this process until either we run out of edges or all the vertices have been unified into one big group. And you'll soon see what I mean by a group, which is when our union-find data structure is going to come into play. So if this is our graph, then to run Kruskal's algorithm on it, first let's scale the edges and sort them. So on the left side, you see I have all the edges and their edge weights sorted in ascending order. So next we're going to start processing the edges one at a time, starting with the top, so I to j. So I've highlighted the edge I to j in orange, and you can see that it connects nodes I and j. I and j currently don't belong to any group, so I'm going to unify them together into group orange. Next is edge A to E. So A to E don't belong to any group, so I'm going to unify them together into group purple. Next is C to I. So I belongs to group orange, but C doesn't have a group yet, so C can go into group orange. Alright, E to F. F doesn't belong to a group, so F can go to group purple. Next, H and G. Neither H nor G belong to a group, so I'm going to say you guys belong to the red group. Next, we have D to B. They also don't belong to a group, so give them their own group. Let's say group green. Alright, and now I believe this is when things start to get interesting. Now we're trying to connect C to J, but notice that C and J already both belong to group orange, so we don't want to include that edge because it's going to create a cycle, so ignore it. And to check that they belong to the same group, we would use the find operation in our union find to check what group they belong to. So this is when the union find really comes into play. Next is edge D to E. So note that E belongs to group purple and D belongs to group green. So now we want to merge them together because they don't belong to the same group. So either the purple group is going to become the green group or the green group is going to become the purple group. It doesn't really matter. So now we would merge them, and this is when the union operation in our union find becomes useful. It allows us to merge groups of colors together very efficiently, and that's the important note. Next edge would be D to H. H belongs to group red, and D to purple, so merge the groups together. Let's say they both become group purple. Next up, we want to add edge A to D, but A to D already belong to the same group, so that would create a cycle. So we don't want to include that edge, so skip it. Next, we want to include edge B to C. B to C belong to different groups, so merge the 2 groups into one larger group. So we have found the minimum spanning tree using Kruskal's minimum spanning tree algorithm. Pretty neat, right? So the underlying data structure which allows us to do this is the union find. It allows us to merge groups of colors together efficiently, but also to find out which groups nodes belong to, so that we don't create a cycle. So that's Crusoe's algorithm. It's super simple, given that you know how the union find works. So I'm going to go into some detail in the next video explaining how the find and the union operations work internally and how we can actually implement it in some useful way. Okay, so now we're going to talk about the union and find operations we can do on the union find, or the disjoint set. This is the video where I demystify how those actually work internally. So to create our union find, the first thing we're going to do is we're going to construct a bijection, or simply a mapping between our objects and the integers in the range 0 inclusive to n non-inclusive, assuming we have n elements. So this step in general is actually not necessary, but it's going to allow us to create an array-based union find, which is very efficient and also very easy to work with. So if we have some random objects and we want to assign a mapping to them, then we can do so arbitrarily, as long as each element maps to exactly one number. So that is my random bijection, and we want to store these mappings perhaps in a hash table so we can do a lookup on them and determine what everything is mapped to. Next, we're going to construct an array, and each index is going to have an associated object, and this is possible through our mapping. So for instance, in the last slide, A was mapped to 5, so slot 5, or index 5, is going to be A's slot. So what you see in this picture is at the top is that array we just created, which contains our mapping. And in the center is just a visual representation of what's going on. The value in the array for each position is currently the index which it is at. This is because originally every node is a root node, meaning it maps to itself. But as we perform the instructions on the left of unifying groups together, or objects together into groups, we're going to find that we're going to change the values in our array to map to other letters. And specifically, the way we're going to do it is for some index I in our array, index i's parent is going to be whatever index is at position I. So, for instance, if we want to unify C and K, we look at C and K, and we discover that C has a root node of 4, and K has a root node of 9. So either C is going to become K's parent, or K is going to become C's parent. And I chose that K's parent is going to be C. So now at index 9, which is K's position, I'm going to put a 4, because I know that C is a 4. So next, F and E, we're going to do a similar type of thing, and I'm going to say that F's parent is going to be E. So at F's position, which is 1, I'm going to put a 0, because E is 0. Similar thing for A and J. But here's where things get a bit more interesting. So now we want to unify A and B. So if I look, A has a 6 in its cell, but 6 is J. So I know that A's root node for group green is J, and B is a single node because it's a self loop. And in general, I'm going to merge smaller components into the larger ones. So now B is going to point to J because the green group's root node was J. So now we want to merge C and D. So I find the root node of D, which is D, and find the root node of C, which is C, and I'm going to merge the smaller component, D, into the larger component, which is the orange group. So now D is going to be part of the orange group. Now I want to merge D and I, so a similar thing happens, and I now points to C. Now I want to merge L and F. So F's parent is E, so I'm going to merge L and to B into the red group. Now I want to merge C and A. So this is an interesting example. So I find C's root node, which happens to be C, and I find A's root node, which is J. So now component orange has 4 elements, but component green only has 3. So I'm going to merge the green component into the orange component. So now J is going to point to C. So I want to unify A and B. So if I go up and follow the parent nodes until I reach a root node, A's parent is J, J's parent is C. So I know that A belongs to the orange group, and if I do a similar thing with B, I also discover that B's parent is also C, which is the orange group. So I don't need to unify them, they're already unified together. So H and G, they currently don't have a group, so I'm going to arbitrarily merge them into a new group, which is going to be the blue group. So H and F. So if I look, H's parent is G, and F's parent is E. The red component is larger, so I'm going to merge the blue group into it. And now, since G was the root node, I make it point to E, which was also the root node. Now I want to merge H and B. So H's root node is E, if we follow up the chain from H to G to E, and B's root node is C, because we go from B to J to C. So now, since the orange component is larger than the red component, I'm going to point the root of the red component to the root of the orange component, so E now points to C. Okay, and note that in this example, I'm not using a technique called path compression. This is something we're going to look at in the next video, which is an optimization on the union find. To summarize, if we want to find out which component a particular element maps to, what we have to do is find the root of that component by following all the parent nodes until we reach a self loop, or a node whose parent is itself, and that will uniquely determine which component that element belongs to. And to unify two components together, what we do is we find the root nodes of each component, and then if the root nodes are different, because if they're the same, then they belong to the same component already, so if they're different, make one of the root nodes point to the become the parent of the other root node. So just some remarks about this union find data structure. So in general, we don't really ununion elements, just because this would be inefficient, as we'd have to update all the children which point to that node, and we don't have access to those. But we could probably, in theory, keep track of that. I just don't see any application currently, but there might be. Also, remark that the number of components in our union find is going to be equal to the number of root nodes remaining, because each root node is responsible for a component. And also remark that the number of root nodes never increases, it always decreases, because all we do is unify components, so components only get bigger and bigger and bigger. So now I want to talk about the complexity of the union find. So I said in the first video that the union find has an amortized time complexity. However, the implementation I just showed you does not have an amortized time complexity. Not yet. Not without the path compression, which is something we're going to look at in the next video, which is what makes the union find an absolute beast of a data structure. You must watch the next video. But just as an example, if we need to check if H and B belong to the same group or a different group, it's going to take 5 hops in the worst case, and, well, potentially much more. So H, we find the root node, which is C, and then we go from B, and then find the root node, which is also C. So this takes quite a few hops. Let's talk about path compression. Now, this operation is really what makes the union find one of the most remarkable data structures, because it's how the union find gets to boast in its efficiency. So let's dive right in. But before we get started, it's critical that you watch the last video so that you understand how the find and the union operation work. Otherwise, you won't understand what's going on and what's up with path compression and how we're going to get that really nice amortized constant time. Alright, suppose we have this hypothetical union find. I say hypothetical because with path compression, I'm almost certain it's impossible to achieve a data structure or a structure that looks like this. Nonetheless, it's a good example. So now suppose we want to unify nodes E and L, or just unify groups orange and blue, but we have access to E and L, and that's what we're calling the unify operation on. Well, we would have 2 pointers that start on E and L, and what we would want to do is find the root node of E and find the root node of L, and then get one of them to point to the other. But with path compression, we do that, but we're also going to do something else. So let's start by finding the parent node of E. So E's parent is D, and then D's is C, C to B, and B to A, and then A to F. So we found the root node of E, but with path compression, here's what we're going to do. Now that we have a reference to the root node, we're going to make E point to the root node. And similarly, D is going to point to the root node, and C, and B, and A. So now everything along the path got compressed and now points to that root node. And in doing so, every time we do a lookup on either A, B, C, D, or E in constant time, we will be able to find out what the parent or the root node is for that component, because we immediately point to it. We don't have to traverse a sequence of other nodes. And we can do this because in a union find, we're always unifying things together and making them more and more compressed. We're never ununifying things, if you will. So if we do the same thing for L, we find L's parent, so we traverse up all the parents until we find the root, and then we compress the path. So J points to G, I points to G, H points to G, and so we compress that path, but we also have found the parents now, so make one point to the other, and we've unified both groups. So now the group that was once with E and once with L have now been merged into one single group. But the only difference is we've compressed along the way as we've done this, and now it's so much more efficient. Now let's have a look at another example, and this one I want to compare and contrast the regular union find operations we were doing in the last video to the path compression version we now know. So if I run all those union instructions, this is what would happen. So I'd start by getting all these pairs of components, and then now I'm executing the instructions on the right. And this is the final state of our union find. And note that if I'm trying to determine what groups, say, A and J are in, then I have to traverse a whole bunch of different nodes. So J goes to I goes to H goes to E. But now if I include path compression, let's see what happens. So I still get all those components, but now as I execute the instruction on the right hand side, this is what happens. So I get the green group, but then because of path compression, that J merged into the H, so already that path is a little shorter. And then I keep executing more instructions, but as I'm doing it, the path gets compressed dynamically. So I'm getting more and more compression, and even up to the very end. So on the last example, we hadn't even finished all the instructions and we have reached the final state. But with path compression, as long as there's something compressed along our path, we get to compress the path along the way, pointing it to the root. So right now we only have one root, being E, and almost everything in constant time points to E. So we do a lookup on any of our nodes and we know that the root is E, so we know it belongs to that component. And this structure becomes very stable eventually because of this path compression. This is why the union find with path compression is so efficient. Let's have a look at some of the union find source code. So here's a link to the source code. You can find it on my GitHub repository at github.com/williamfizet/datastructures. I also have a bunch of other data structures from past videos. And before we dive into the code, make sure you watch the other videos pertaining to the union find, as I will be making some references to them. Okay, let's dig in. Here we are inside the code, and I have a class called UnionFind, and it's got a few instance variables, so let's go over them. The first is size, it's just how many elements we have in our UnionFind. Then I have these two arrays, one called ID and one called size. So the more interesting one is ID, and ID at I is that array I talked about, which at index I points to the parent node of I. And if ID at I is equal to I, then we know that I is a root node. So we're essentially keeping track of all of these tree-like structures right inside an array, which is practical. And also because we create a bijection between our elements and some numbers, this is how we're able to access them through this ID array. And just for convenience, I track the number of components. That's sometimes some useful information you might want. So if you create a union find, well, you need to know how many elements are going to be inside your union find. And I make sure that we have a positive number of elements, otherwise I throw an exception. Then I go ahead and initialize some instance variables, and I initialize ID to equal I. So initially everyone is a root node, and every component has a size of 1. So find is pretty simple. It's given a node, it finds which component it belongs to and also does path compression along the way. So if we're at P and we want to find the root node of P, what we're going to do is we're going to find the root node using this one while loop. So we initialize a new variable called root to P, And then we loop until the root is not equal to id at root. So aka this is a root node or a self loop that we found, and so we can stop, and the root is stored in, well, the variable called root. And then what we do is we do the path compression. This is what I talked about in the last video. So starting back at P, we assign everything from id at P to equal the root. And this is what compresses the path and gives us that nice amortized time complexity. You can also do this recursively, but I don't like having the overhead, and doing things iteratively can be slightly faster. Okay, so now we have these simple methods we can call. So if P and Q are inside the same component, this will return true because the root at P and the root at Q will be equal. Otherwise, this will return false. And just calling find will do path compression. So even if we're just checking if two components are connected, and it calls the find method, then we're compressing the path. Same thing here. If we decide to find the component size relative to some index P, then when we index into the size and call find, we'll find the root, but at the same time we'll also do path compression, which is nice. And I would just like to note that the root nodes are the ones who will always contain the size, because they're the ones that are found, well, if you want to think about it, like at the end of the chain. Size just returns the number of components in our unified disjoint set. Components, number of components, that's pretty self-explanatory. And the unify method is the last interesting method. So this is the one that unifies two components together. So first what we do is we find what the root node for P is and what the root node for Q is. And if the root nodes are equal, then they're already in the same group and we don't do anything. Otherwise, by convention, I just merge the smaller group into the larger group. Although, I know some people like to keep the theoretical largest path in a component and then merge according to that. That may be slightly more efficient, but it's more work. So I just like to merge the smaller group into the larger group. And also, since the roots are different and we're merging, we know that the number of components or sets must have decreased by 1. So that's why at the bottom here I say the number of components, subtract that by 1, because we know we're going to have one less component. So this whole time inside this class, I've been treating P and Q as integers and not as elements, like letters that we saw in the slides. And this is because of that bijection. I would do a lookup to find out what maps to the element P, and that should give me an integer, and what maps to the element Q, and then I could use those with this union find data structure I've created and turn everything into the realm of numbers instead of dealing with objects and having all this more complexity. It's much easier to have an array-based union find. You could also have a pointer-based union find with node objects, but this is really nice and it's a really clean implementation. Alright, I want to start talking about a very exciting topic, and that is trees. And you'll soon start to realize that there are tons and tons and tons of tree data structures. But today I want to focus on a very popular kind of tree, and that is binary trees. And with binary trees, we must talk about binary search trees as well. So today's tutorial is going to focus on binary trees, in binary search trees, where they're used, and what they are. And in later tutorials, we're going to cover how to insert nodes into binary search trees, remove nodes, and also do some of the more popular tree traversals, which can apply to other general trees also, not just binary trees. Okay, so I'm going to give you guys a quick crash course on trees before we get started. So we say a tree is an undirected graph, which can satisfy either of the following definitions. There are actually multiple definitions, but these are the most popular ones. So a tree is an undirected graph which is connected and acyclic. Acyclic means there are no cycles. Another definition is we have n nodes, but we have n minus 1 edges. And lastly, for any two vertices, there's only one path between those two vertices. You can't have two different paths. That would imply that we don't have a tree because there's another route to get to another node, and so we'd have a cycle. Okay, in the context of trees, we can have something called a rooted tree. Which is the topmost node of our tree. You can think of it that way. And if you're trying to root the tree and you don't have a root yet, it doesn't matter which node you pick to root the tree, because any node you pick can become the root node. Think of it as picking up the tree by that node and suddenly it's the new root. We have something called, or the concept of child and parent nodes. So a child node is a node that extends from another node. Think of it as going downwards, and a parent node is the inverse of this, so you're going like up towards the root. So we have an interesting question, and that is, what is the parent of the root node? The answer is that the root node has no parent, although sometimes it may be useful to say that the parent of the root node is itself. And we see this often when programming. For instance, a file system tree has this property. So if I open up the command line, I'm in some directory, so I can say pwd to get the current directory. So I'm somewhere in the file system tree, and if I want to go up to my parent, I can say cd ... and now I'm up in another directory, or into the parent directory. And I can keep doing this and going up and up in the file system tree directory system. But if I go directly to the root node, which is / and I see that I'm in the folder /, so the very top, at the root of the directory, then I say cd ... then if I check out where I am, I'm again at the root. So in this context, for a file system, the parent of the root is the root. Pretty cool. So just as an example, if we pick the node 0, it has two children, 3 and 2, and a parent 4. We also have the concept of something called a leaf node. This is a node which has no children, and these have been highlighted in orange. So they're just at the very bottom of your tree. Think of it that way. And there's also another term, which is a subtree. This is a tree entirely contained within another tree, and we usually use triangles to denote subtrees. And it's possible for a subtree to consist of only a single node, so that's fine. So if this is our tree with that circle node being the root, and we pick a particular subtree and look what's inside of it, then we get another tree, which contains nodes and more subtrees. Then we pick another subtree, we look what's inside of it, and then we get another tree. And eventually we're going to hit the bottom. So now we can pose the question, what is a binary tree? And this is just simple. This is a tree in which every node has at most 2 children. So both those trees below are binary trees because they have at most 2 children. You can see that the tree on the right, 8, has 1 child, and that's fine because the criteria is at most 2. So now we're going to play a game. I'm going to give you some various structures, and you're going to have to guess whether it is a binary tree or not. So is this a binary tree? Yes, yes it is. Every node has at most 2 children. How about this one? No, you can see that 7 has 3 children, so it's not a binary tree. How about this one? Let you guys think about it a bit more. Yes, this is a binary tree. It may be a degenerate one, but it's still a binary tree. Alright, let's move on to binary search trees. So what is a binary search tree? Well, first of all, it's a binary tree, but furthermore, it also satisfies what's called the binary search tree invariant. And that is that the left subtree has smaller elements than the value of the current node, and the right subtree has larger elements than that of the current node. So below are a few binary search trees. We're going to play the same type of game, and I'm going to give you some trees, and you're going to have to guess whether they're binary search trees or not. So what about this structure? And this one, we could say it depends on whether you want to allow duplicate values inside your tree. It so happens that binary search tree operations allow for duplicate values. There's nothing wrong with that. But most of the time we're only interested in having unique values inside our tree. So this particular tree depends on what your definition of a binary search tree is. How about this tree? Yes, this is a binary search tree. How about this tree? Notice I've only changed the elements within the tree. Yes, this is also a binary search tree. We're not limited to only having numbers within our binary search tree. We can place any type of data which is comparable and can be ordered. How about this tree? No, this is not a binary search tree. And the reason is the node 9 is in the wrong position. When we would be inserting 9, we would have to place it in the right subtree of 8 because 9 is larger than 8, so it belongs in its right subtree. How about this structure? This structure isn't even a tree actually, because it contains a cycle. And the requirement to be a binary search tree is that you must be a tree. And this last one, I'm going to give you a bit more time to look at this one, because it's not a regular type of structure you might think of as a binary search tree. And the answer is yes, this structure does satisfy the binary search tree invariant, that every right subtree contains larger elements. You'll see that that is true, and also every left subtree it contains smaller elements. It doesn't look like a tree, but it satisfies our definitions of a tree and a binary search tree. Okay, so we've been talking about binary trees, binary search trees. Where are they used? Why are they useful? So in particular, binary search trees are used in many implementations of abstract data types for sets and maps and so on. And they're also used to implement balanced binary search trees, which we'll probably get to in a later video. And you see binary trees and binary heaps. We've already seen this in priority queues when we were making a binary heap. But we also see binary trees in things like syntax trees. So you're parsing an arithmetic expression, then you place it in an abstract syntax tree, and then you can simplify your expression. Compilers and calculators use this to evaluate expressions. So whatever you punch in your calculator gets parsed into a binary tree and evaluated. And lastly, I just threw in a TREEP, which is another type of probabilistic data structure. So now let's look at the complexity of these binary search trees, because they looked very interesting and also very useful. And indeed they are. So in the average case, when you're just given some random data, the time complexity is going to be logarithmic, which is really good. So if you're inserting nodes, deleting nodes, removing nodes, searching for a value in a tree, whatever, the average time complexity is going to be logarithmic. And these binary trees, or binary search trees, are very easy to implement. So this is really good. However, in the worst case, if your tree degenerates to being a line, then we can have some linear behavior going on, which is really bad. So there's some trade-offs if you want to use just a pure binary search tree, that it's going to be easy to implement, and on average it's going to have this logarithmic behavior, but in the worst case, you might be looking at some linear stuff, which is not so good. Okay, let's have a look at how to insert some elements into a binary search tree. So let's dive right in. So first, to add elements to our binary search tree, we need to make sure that the elements we're adding are actually comparable, meaning that we can order them in some way inside the tree. Meaning at every step, we know whether we need to place the element in the left subtree or the right subtree. And we're going to encounter essentially 4 cases. So when inserting an element, we want to compare the value to the value of the current node we're considering to do one of the following things. Either we're going to recurse down the left subtree because our element is smaller than the current element, or we're going to recurse down the right subtree because our element is greater than the current element, or it might be the case that the current element has the same value as the one we're considering, and so we need to handle duplicate values if we're deciding to add duplicate values to our tree or just ignoring that. And lastly, we have the case that we've hit a null node, in which case it's time to create a new node and insert it in our tree. Let's look at some animation now. So on the left, I have a bunch of insert instructions. So we have all these values we want to insert into our binary search tree, and currently the search tree, or the binary search tree, is empty. So first we want to insert 7, so 7 becomes the root of the tree because it's the first node. Next we want to insert 20, so 20 is greater than 7, so we insert it to the right. Next we want to insert 5, so we always start at the root when we're inserting, and that's an important point. So you start at the root and then you move your way down the tree to figure out where you want to insert the node. So we start at the root and then we're like, oh, 5 is less than 7, so we're going to insert it to the left. Now 15, start at the root, go to the right because 15 is greater than 7, then to the left because 15 is less than 20. Now 10. Now 4, so 4 is less than 7, move left. 4 is less than 5, move left, create the new node. Now we have 4 again, so let's see what happens here. So we start at 7, we move to the left, we move to the left. Now we've encountered a value that already exists in our tree. So as I said before, if your tree supports duplicate values, now's the time to add another node. And you would either pick by convention if you want it on the left or on the right. Otherwise, you would do nothing, and I'm going to choose to do nothing. I want to insert 33. So start at the root, go to the right because 33 is greater, go to the right again. Now insert 2. So 2 is smaller than everything in our tree, so it would go all the way to the left. Now try and see where 25 would go. So 25 is going to go to the right, then we're going to go to the right again because it's greater than 20, but we're going to go left now because it's less than 33. And finally 6, so once left, once right, and we've inserted everything into our binary search tree. So on average, the insertion time is going to be logarithmic, but in the worst case, this behavior could degrade to linear time. Let's have a look at that. So if our instructions are the following, insert 1, 2, 3, 4, 5, and 6. So we start at 1, then we're going to insert 2, so that's going to go to the right. Okay, now let's insert 3. Well, 3 is greater than everything, so I have to place it to the right again. Now how about 4? Okay, 4 is also greater than everything. Oh, looks like we're creating this line now. And now 6 is still greater than everything. So as you can see, this type of linear behavior is really bad. And we don't want to create lines like this, because if we want to query where 6 is in the tree, or if we want to remove 5, or do anything on our binary search tree, we first need to find the node. That's going to take linear time, and this is bad. It's one of the reasons why people have invented things like balanced binary search trees, or self-balancing trees, which balance themselves as you insert nodes. We'll be getting to that later, but that's it for insertion. It's really simple. Don't overcomplicate it. Alright, now that we know how to insert elements into a binary search tree, we might also want to remove elements from a binary search tree. And this is slightly more complicated, but I'm going to make it very simple for you guys. So when we're removing elements from a binary search tree, you can think of it as a two-step process. First, we have to find the element we wish to remove within the binary search tree, if it exists at all. And in the second stage, we want to replace the node we're removing with its successor, if one exists, in order to maintain the binary search tree invariant. Now let me remind you what the binary search tree invariant is. It's that the left subtree has smaller elements than the current node, and the right subtree has larger elements than the current node. Okay. So let's dive into phase 1, the find phase. So if we're searching for an element inside our binary search tree, one of 4 things is going to happen. The first thing is we hit a null node, meaning we've went all the way down our binary search tree and have not found the value we want. So the value does not exist inside our binary search tree. Another thing that can happen is the comparator value is equal to 0. And what I mean by comparator is it's a function that will return -1 if it's less than, 0 if it's equal to, or 1 if it's greater than the current value. So it tells us essentially which subtree we need to go down, or if we found the value that we're looking for. So if it's equal to 0, then we found the value. If it's less than 0, the value might exist, and if it does, it's going to be in the left subtree. If our comparator returns a value greater than 0, then if the value exists, it's going to be in the right subtree. Okay, let's have an example with some animation. So suppose we have 4 find queries, find 14, 25, 37, and 17. And that's our binary search tree there on the right. So if we're trying to find 14, as usual, we need to start at the root, and 14 is less than, so go left. 14 is greater than 10, so go right. 14 is less than 15, go left. 14 is greater than 12, so go right again. And now we have found the value that we are looking for. Alright, move on to 25. 25 is greater than 20. Go right. 25 is less than 31. And now we found 25. See if you can do 37 on your own. Pause the video or something. Okay, here's how it go. Go right, go left, go right. Alright, now let's have a look at 17. So 17 should be on the left. Now we should go right. Then we should go right again. And, oh, we've hit a point where we know that 17 does not exist in our tree. So that's another possibility. The value simply doesn't exist. Because we would go to the left of 19, and the left of 19 is a null node, and a null node means we haven't found the value we're looking for. So now that we've found the value that we're looking for, we're at the remove phase. And in the remove phase, there are 4 cases, essentially. And the first case is that the node we want to remove is a leaf node, so it has no subtrees. Cases 2 and 3, as I like to call them, is there's only one subtree. Meaning there's a right subtree but no left subtree, or there's a left subtree and no right subtree. Or finally, case 4 is that we have both a left and a right subtree. So I'm going to show you guys how to handle each of these cases, and it's really not that hard. So case 1, we have a leaf node. So if you have a leaf node and you want to remove it, then you can do so without a side effect, which is really nice. So suppose we have the binary search tree on the right, and we want to remove 8. So we do phase 1, we find out where 8 is. Oh, and 8 is a case 1 because it's a leaf node, so we know we can remove it without a side effect, so we remove it. Perfect, that wasn't hard. Now let's look at cases 2 and 3, meaning that either the left or the right child is a subtree. In this case, the successor of the node we're trying to remove is going to be the root node of that left or right subtree. Let's look at an example. Suppose we want to remove 9. So first let's find 9. Okay, we found 9. Now we encounter a case 2 with a left subtree, because 9 doesn't have a right subtree. So the successor is going to be the root node of that left subtree, so 7. So now I can remove 9, and 7 becomes the successor of 9. Perfect. Now let's do another example where we want to remove 4. So first let's find 4. So we find 4, and this is our other case where we only have a left subtree but no right subtree. So what do? The successor of 4 is going to be the root node of that left subtree, so 3. So we can remove 4, and now 3 becomes the successor. Alright, that wasn't so bad, was it? Alright, so now for case 4, now we want to remove a node which has both a left subtree and a right subtree. Now the question is, in which subtree will the successor of the node we're trying to remove be? And the answer is both. The successor can either be the largest value in the left subtree or the smallest value in the right subtree. And here's perhaps some justification for why there can be 2 successors. So the largest value that we can find in that left subtree would satisfy the binary search tree invariant if it becomes a successor, because it would be larger than everything in the left subtree, and this is immediate from being the largest in the left subtree, and also it would be smaller than everything in the right subtree because we had found it in the left subtree. Similarly, if we find the smallest value in the right subtree, it would also satisfy the binary search tree invariant for the following reason. It would be smaller than everything in the right subtree, and this is immediate from being the smallest in the right subtree, and also larger than everything in the left subtree because it was found in the right subtree. And we know things in the right subtree are, well, greater than everything in the left subtree. So we come to this conclusion that, well, there must be two possible successors. So we can choose either or. Fantastic. So if we have this tree, and we want to remove 7, well, 7 is a case 4 because it has both a left subtree and a right subtree. So 7, so find 7, we've already found it. And now we get to either pick the successor in our left subtree or our right subtree. I'm going to find the smallest value in the right subtree. What we do is we go into the right subtree and then we dig as far left as possible. Go left and go left again, and now we don't have a left child, so we can stop, and this node is going to be the successor. It is the smallest node in the right subtree. And you can see that quite clearly. 11 is smaller than everything in that right subtree. So now what we want to do is we want to copy the value from the node we found in that right subtree, 11, into the node we wanted to originally remove, which is 7. So now I replace 7 with 11. Now we have a problem, which is we have 11 twice in our subtree, and we want to now remove that element 11, which is highlighted, because it is the successor. It shouldn't no longer be inside the tree. And luckily for us, the successor node we want to remove is always going to be either a case 1, 2, or 3 removal. So in this case, it would be the case where there's a right subtree but no left subtree. And you would just do this recursively, so it would just call itself and it would hit one of those 3 cases. Okay, so it's a right subtree, so what we want to do is swap it with the root node of that right subtree and then remove it. So remove 11, 14 becomes a successor, and now just going to rebalance the tree like that. Alright, now let's have a look at another case. In this example, let's remove 14. So first, let's find 14 if it exists within our tree. Go right. Alright, we found 14. Now we either want to find the smallest value in the right subtree, like we did last time, or the largest value in the left subtree. So now let's do the latter this time, and find the largest value in the left subtree. To do this, what we would do is we would go into the left subtree and dig as far right as possible this time. Go into the left subtree and dig as far right. 9, 13. Now 13 is the largest value in the left subtree. And now what we want to do, as per before, is we want to copy the value of the successor, 13, into the node we want to remove, which is 14. So now 14 becomes 13, and now we want to remove the remaining 13. So now just remove it and replace it with its successor. Perfect. Okay, I just want to go over some more examples, so just these 2 short examples, because removing is not quite so obvious. Alright, let's start with the one on the left. So let's see if we can remove 18 from this strange looking binary search tree. So start at the root, find 18, so dig all the way down. Okay, we found 18, and now we want to, it's one of those case 2 or 3s. It's the one where there's a left subtree, so the successor is just going to be the root node of that left subtree, or 17. So remove 18 and replace it with 17, so 17 is the new successor. Perfect. Now let's look at the other case where we want to remove -2. So now first find -2, so go to the left. Okay, we found it. Now there's 2 subtrees. Pick one of the 2 to find its successor. I'm going to go to the right. Alright, copy its value in, and now remove -1, and that's it. Okay, and that is removals in a nutshell. Alright, I want to finish off binary trees and binary search trees with some tree traversals, in particular pre-order, in-order, post-order, and level order. You see these tree traversals come up now and again, so they're good to know. I want to focus on pre-order, in-order, and post-order to begin with, because they're very similar. They're also naturally defined recursively, and you can sort of get a feel for why they have their certain names that they do. So pre-order prints before the 2 recursive calls. In-order will print between recursive calls, and post-order will print after the recursive calls. So if you look at the 3 functions on the left, the only thing that's different between them is where the print statement is. So let's go into some detail on how pre-order works. So on the right, I'm going to maintain a call stack of what gets called. So when we're recursing back up, we know what called us to know what node to go to. And what you need to know about pre-order is that we print the value of the current node, and then we traverse the left subtree followed by the right subtree. So for our order, what we're going to do is we're going to start A, print A, then we go left, go to B, then we go down to D, go down to H, and now we recurse back up, so we push node H off the call stack and go to D, and then we go to I, and then we explore I. Now we're at the bottom, so we recurse back up, so we push I off the call stack. We've already processed D, and go back to B. We've also already processed B, but now we have to do B's right subtree. So we go and explore E. Now we've explored E, so push the frame off the stack, explored B, push that off the stack, and now A. Now we need to explore the right subtree of A. So we would print C, then F, then J, and then we're at the bottom, so recurse, and then now K, and now we're at the bottom, so recurse, so push node K off the stack, push node F off the stack, and now explore node C's right subtree. So G, now L, and now we're done. We curse all the way back up, and we would exit our function. And at the bottom, you can see what the pre-order traversal is. Okay, now let's cover in-order traversal. So how in-order traversal works is we traverse the left subtree, then we print the value, and then we traverse the right subtree. And for this example, I'm going to be using a binary search tree and not just a generic binary tree. And you'll see something interesting happens. We push node 11 on the stack because it's our root. Then we go left. Then we go left again. Then we go left again. And notice as I was going left, I would push those on to the stack, but I'm not printing the value yet because when I call in order, the very first instruction in the in order is to go left. I only print once I've traversed the entire left subtree. If I'm a leaf node, like I am now, one is a leaf node, then I've already explored the left subtree, if you will. So I can print the current value, then I recurse, and then I print 3 because I've explored 3's left subtree. Now we go right now, and I've explored both subtrees, so I can print 5, and I recurse. Now I can print 6 because I've explored 6's left subtree. And I can go to 8, then recurse, and then print 11. Now I need to finish 11's right subtree. So go right, go left, now explore 12, recurse, and we're going to print 13, then go down to 14, print 14 also because 14 has no subtrees. Go up, so push 14 out the stack, push 13 out the stack, print 15 because we've explored 15's left subtree. Go right, and now the last thing we need to do is finish our function by just pushing everything off the stack. So go back up. And now, did you notice something interesting happened when we did our in-order traversal? Well, what happened was we printed the values of the nodes in increasing order, which is why it's called an in-order traversal if you do it on a binary search tree. It prints the values in increasing order, which is really neat. That's quite a nice property of the in-order traversal. Now let's look at the post-order traversal. And the post-order traversal says, okay, traverse the left subtree, then traverse the right subtree, and after you're done doing both of those, only then print the value of the node. So this means if you look at our tree right now, the last value we're going to print should be 11, because we need to process 11's entire left subtree and 11's entire right subtree. So let's start at 11 and explore its left subtree. So go all the way down, then print 1 because we've explored both its left and right subtree. Now don't print 3 because we haven't explored its right subtree yet. Print 5 because we've explored both its subtrees, which don't exist. Now we can print 3 because we've explored both of its subtrees. And then similarly go down to 8, print 8, recurse, and print 6. Don't print 11 because we still need to do its right subtree. Go to 15, 13, 12, print 12. Go up to 13, print 14, go back up to 13, and now we can print it. Don't print 15 yet because we haven't explored all of its right subtree. Then go to 17, 19, and then pop everything off the stack and print on the way back up. And you can see that 11 is indeed the last node we have visited. And that's pre-order, in-order, and post-order in a nutshell. Now I want to look at level order traversal, which is special. It's quite a bit different from the other two. A level order traversal is we want to print the nodes one layer at a time. So we start with 11, then we want to print 6 and 15, then 3, 8, 13, 17, and 1, 5, 12, 14, and 19. And you're like, oh, how am I going to do that? And the way we're going to obtain this ordering is by doing something called a breadth first search. From the root node all the way down to the leaf node. So if you know what a breadth first search is from graph theory, and this is the same thing. A tree is a type of graph. It's no different. So what we're going to do our breadth first search is we're going to maintain a queue of the nodes we have left to explore. And how this is going to work is our queue is originally going to contain only the root node. And we're going to keep processing by pulling out the first value in our queue until our queue is over. a bit more detail on that. So here you can see the queue on the right. I've inserted node 11, and so I would pull out node 11 and I would add 11's left child and 11's right child to the queue. So they would go at the end of the queue, and I've also removed 11. So the next node's process would be 6 followed by 15. And then I would keep adding children to the queue so that I reach them eventually. So let's have a look. So I've pulled 11 from the queue and now added 6 and 15 to the queue. Now the next thing on the top of the queue is 6, so I'd remove 6 and add 6's children 3 and 8 to the queue. Then 15's next up. Now I'd add 15's children, which are 13 and 17, to the queue. And next up in the queue is 3, so I would add 3's children to the queue, and then move on, explore 8. 8 has no children, so I can't add them. Next 13, and you can see that as I'm exploring nodes, I just add the children, but keep pulling the most recent thing in the queue. And this gives us the level order traversal that we want. And this is how you do a breadth first search in general. So not too complicated, except we had to use that special trick of using a queue instead of using a stack. So we don't do level order traversals recursively. We need to do them iteratively with a queue. Okay, finally time to look at some source code for a binary search tree. So the source code that I'm about to show you can be found at the following link. The link should also be in the description at the bottom of this video. Please like the repository so that other people can also find it more easily. And now let's dive in. Alright, here we are inside the source code for the binary search tree. This source code is written in Java. Okay, so first thing you will notice is I have a class representing a binary search tree, and it takes as a type anything that is comparable. We need things that are comparable so we know how to insert them accordingly within the binary search tree. So to start us off, I have a few instance variables. Actually, only 2 in fact. One to keep track of the number of nodes in the binary search tree, and another one which is the root of this binary search tree, because this binary search tree is a rooted tree. Next, I have a private node class, which contains a left node and a right node, as well as some data of type T. And that type T comes from here. So it's some comparable type T. Okay, next I have a method to check if our binary search tree is empty. It simply checks if the size is 0, and size simply returns the node count, which gets either incremented or decremented as we add or remove elements. Okay, here's the public method to add elements to this binary search tree. I also have a private method down here, as you will notice. And I use the private methods to do the recursive business, and the public method to just check if the element is already contained within the binary search tree. This insertion method will return true if we successfully insert a new element into the binary search tree, and it will return false if there's already something inside the binary search tree. So elements have to be unique inside this binary search tree. Okay, so supposing this branch doesn't get executed, meaning the element does not already exist in the tree, then we're looking at this branch. And I'm saying Okay, add this new element to the binary search tree recursively, and also up the node count by 1, and return true because, well, this element doesn't yet exist. So let's look at the recursive method now. So our base case is that we found the null leaf we want to insert our element at. So we would create a new node object with 2 null children, but with the value of the element we want insert. Otherwise, we're in this branch, and we choose which subtree we want to place our element inside. So either it's going to be the left subtree, the first branch, or the right subtree, the second branch. Okay, now let's look at removing. So here's the public method for removing, and I'm only going to remove the method if it exists within the tree. So I check if it's within the tree before, otherwise I'm just going to return false, meaning we have not removed anything from this binary search tree. And if it is contained, then I'm also going to decrement the node count. Now let's look at this recursive method to remove the node. So this recursive method simply has a normal base case. If it's null, return null. And in the first step to removing a node, we first have to find it. And we know it exists because of this check. We know that our element is within the tree, so we can remove it. And that is these two cases. So this is like the find phase I was talking about in the later video. So I get a comparator value and I check if it's less than, so we're going in the left subtree, or we're going inside the right subtree. It's going to be one of these two cases, otherwise we found the node we want to remove. So this finds the node, and here's where we do the actual removal. So I talked about 4 cases in my slides, but in fact you can think of it more or less as 3 cases, even 2 cases, because 2 of the cases are very similar. So the singleton case, where there's only one node, it's really that can also be thought of as a left subtree or a right subtree case. This case is the case where the left subtree is null, but the right subtree is not. And this case, the right subtree is null, but the left subtree isn't. And this case down here, which I'll get to later, we have both subtrees. So let's go to the very top. So if we only have a right subtree, then I'm going to say that the successor node is just going to be the root node of that right subtree. So node.right. And then I return that. And I also destroy the data within this node and the node itself. Similarly, for the other case where I only have a left subtree, what I'm going to do is I'm going to reach into that left subtree and grab the root node. And I'm going to return that node. And I'm also going to destroy this node because we know we don't want it anymore. So those 2 cases are fairly easy. Now let's look at the case where we have a left subtree and a right subtree. So as I mentioned in my slides, we can either find the largest node in the left subtree or the smallest node in the right subtree. And here I find the smallest node in the right subtree. So I go down to the right subtree, and I dig left. And this is the node, or the successor node, if you will. So we copy the data in it, and then we recurse and call ourselves to remove the successor node. If you wanted to find the largest value in the left subtree, then you could just uncomment this code, and it would do just that. So that's removing in a nutshell, and I also had these two helper methods to do a dig left and a dig right. Moving on, I also have this method that checks contains of an element. So given an element, it'll return true or false depending on if that element is within this binary subtree. And this is very simple. This is equivalent to the find phase. If we reach a null node, we definitely know that that element doesn't exist. Otherwise, get our comparator value, which is either going to be less than if we need to go to the left subtree, meaning this case, or greater than 0 if we need to go in the right subtree, or if we found the element, then that's the 0 case, and we're in this case. So pretty simple. Just as a bonus, I also threw in a height function. So this will calculate the height of the tree. It'll do so in linear time. Height we'll call the private recursive height method. And all this does is, it's fairly simple. So if we reach a leaf node, we're going to return 0. Otherwise, we're going to return the maximum height of the left subtree or the right subtree, because one of our subtrees might be greater than the other, and that's going to be the one that we want the height from. But every time we recurse, we add +1. So this corresponds to a depth. So the biggest depth is going to be whatever the height of the tree is, if you want to think of it that way. And now for our traversals, I have created this method called traverse, and what it does is it takes a tree traversal order, which is an enum type. I'm going to show you in a minute, and that's an order, and then I pick whichever order you give me, and I return an iterator for that particular order I want to traverse. So if you tell me I want to traverse this binary search tree in a pre-order fashion, then I'm going to return you this iterator, which is this method. If you want to traverse the tree in order, I'm going to return you this in order traversal iterator. Let's have a look at what this tree traversal order is. Let me open that up right here. So that is simply an enum type. You can see right here. So it's either one of these 4 things. It's pre-order, in-order, post-order. So nothing too crazy. And I decided to do these traversals iteratively so that you don't have to do them recursively, which would be slightly slower and perhaps less convenient. This is more flexible, although I don't really want to dive into the code because it is fairly nasty. If I just open up, say, the in-order traversal, then it does look pretty gross. I have to maintain a stack manually, and I have to check for concurrent modification errors, etc., etc., etc. These are actually great interview questions, like how do I do an in-order traversal iteratively, or how do I do a post-order traversal iteratively, and so on, so on. So those are definitely great to practice. If you want to actually see what's hidden inside these methods, just go on the GitHub repository and have a look. But I showed you guys how to do tree traversals in the last slides, so you should be good to do that. Most of the time you do it recursively anyways. I just want to be a bit more fancy and go all out iteratively. So this is about it for the binary search tree. Today we're going to be talking about hash tables, one of the most remarkable data structures of all times. If I had a subtitle, it would be one data structure to rule them all. So let's get started. There's going to be a lot of things to cover in the hash table series. We're going to start off with what's a hash table and what the heck is a hash function and why do we need one. Then we're going to talk about some popular collision resolution methods, in particular separate chaining, open addressing. Those are the two most popular ones, although there's a ton more. Then we're going to separate chaining with linked list, just because it's a really popular implementation. And there's a ton of stuff in open addressing that needs to get covered. So we're going to be talking about linear probing and quadratic probing, how that's done. I'm going to be giving lots and lots of examples for those, just because it's not super obvious how they work. And to finish off, we're going to be going over double hashing, and finally removing elements from the open addressing scheme, because that's not so obvious either. Alright, so to begin with, what is a hash table? So the hash table is a data structure that lets us construct a mapping from some keys to some values via a technique called hashing, which we'll talk about shortly. So the key could be any value, as long as it's unique, which maps to a value. So for instance, keys could be names, which are people names, and the value could be someone's favorite color. So William's favorite color is green, Micah's is purple, Catherine's is yellow, and so on. And we call these key value pairs. So each key is associated with a value. So all of the keys have to be unique, the values don't have to be unique. For example, Micah's favorite color is purple, but also Leah's favorite color is purple. We often use hash tables to track item frequencies. For example, below is a frequency table of the number of times a certain word appeared in Shakespeare's Hamlet, which I parsed and obtained this table. So you can see Hamlet appeared 114 times, the word Lord 223, but the word cabbage did not appear. So hash tables are often used to track frequencies, which is really handy. But you can really construct a mapping between any key value pairs, given that the keys are hashable. This is something we're going to talk about shortly. So to be able to understand how we construct the mapping within the hash table, we need to understand what a hash function is. So simply put, a hash function, which I will denote from now on as h of x for some key x, is a function that maps x to a whole number in some fixed range. So that's pretty simple. Let's have a look at an arbitrary hash function. So if our hash function is h of x equals some polynomial x squared minus 6x plus 9 modulo 10, well, all the integer keys get mapped to the range 0 to 9 inclusive. No matter what integer number I plug into h of x. So below I'm plugging in certain values or keys, if you will, into the hash function and getting an output. So notice that the output is not unique in that there could be two values that I plug into the hash function which yield the same value. For instance, h of 4 and h of 2 map to the same thing, and that's completely fine. So we can also define arbitrary hash functions, not just on integers, but on arbitrary objects, which makes this really powerful. For instance, suppose we have a string s, and we're going to say h of s be the hash function that I have defined below. So this hash function, all it does is it sums the ASCII values of the characters within the string, and then at the end says modulo 50. So that will, for any given string, just output a number, and that's a hash function. So for example, some simple inputs. So h of bb gets 66 plus 66, and then we mod that by 50, so we get 32. The empty string gets 0 because we don't even execute the loop, and so on. So we've effectively converted a string to a number. Great. All right, here's a mini challenge for you. Suppose we have a database of people below, and each person has 3 fields. They have an age, a name, and a sex. I want you to define a hash function, h of a person, where you're going to be given a person object as an argument. And I want you to create a hash function that's going to map a person to the set of values 0 through 5 inclusive. You can pause the video, just create any hash function that does this given the 3 fields. Alright, so here's my attempt at creating such a hash function. Turns out there is an infinite amount of possible hash functions we could have defined for the hash of the person. And here's a simple one. So I'm going to say, okay, first let's start with the age. So whatever there is, that's the starting value for the hash. Then I'm going to add on the length of the person's name. Again, an arbitrary choice. And I'm going to increment by 1 if they're males. And then mod by 6. So as you can see, hash functions are a bit arbitrarily defined at this point. We're going to get into some more sophisticated hash functions later. So this particular hash function yields those values. Alright, something very important, very, very important we need to talk about are properties of hash functions. So if we have a hash function and 2 objects, say x and y, and their hash values are equal, then those 2 objects might be equal. We don't know for sure. We have to explicitly check x against y, because the hash function tells us that there was a collision right there. But if the hash functions are not equal, then x and y are certainly not equal. Here's a good question. How can we use this to our advantage to speed up object comparisons? The answer is that instead of comparing x and y directly, if we've already computed their hash values, then first let's compare the hash values of x and y instead of comparing x and y explicitly. And in this next example, you'll see why that's important. Consider the problem of trying to determine if 2 very large files have the same contents. This is something you want to do in an operating system context all the time. So if we've computed the hash values for file 1 and file 2, first we should compare the hash values together to see if they match or don't match, because this requires constant time work, which is super fast. So if possible, we don't want to open the files at all. This would be comparing x and y directly, or file 1 against file 2. But we will have to compare them byte per byte if their hash values are equal. So actually, hash functions for files are much more sophisticated than those that we use for hash tables. Instead, we use very sophisticated hashing algorithms called cryptographic hash functions and checksums. Alright, another property of hash functions is that they must absolutely be deterministic. This means that if h of x produces y, then h of x must always produce y and never another value. This is super critical because this will screw up our hash table completely if this happens. We do not want this. So an example of a non-deterministic hash function is something that introduces, say, a global variable or some kind of randomness. You don't want that. So in this particular hash function, the first time I run it, The hash value for 5 is 6, but then if I call it again, we've incremented the counter and now the hash value is 7. Uh-oh, not good. Something else about hash functions is we try very hard to make them uniform. To minimize the number of hash collisions, we'll get into why hash collisions are bad shortly, but a hash collision is when two objects, x and y, hash to the same value. That is, h of x equals h of y. And the reason we want it to be uniform is so that all the values of our hash function are hit, so that we can fill the table uniformly. So for example, the table we generated earlier, William and Kate, they have a hash collision. Uh-oh. Okay. So now we're able to answer a central question about the types of keys that we're allowed to put in our hash table. So what makes a key of type T hashable? Here's the answer. Since we're going to implement our hash table using these hash functions, we need those hash functions to be deterministic. And to enforce that behavior, you'll see a lot of programming languages enforce that the keys you use be immutable, meaning you can't change them. They're fixed, they're constants. So they're things like immutable strings, integers, but not things like sets or lists or things you can add or remove things from. They're immutable. And if we have that condition, and we have a hash function that is defined for all keys of type T, then we say that that type is hashable. Okay. Alright, so now let's get into the interesting details. How does the hash table work? Well, ideally, we want our hash function to have really quick insertion, lookup, and removal times. And remarkably, we can achieve all of that using the hash function as a way to index into a hash table. And a hash table is just a fancy word for an array. Think of it like that. Every time I say hash table, think array. So again, we use the hash function as a way to index into the hash table. So the hash function gives us an index to go look up inside the table. And yes, we can do this in constant time, given that we have a uniform hash function. Super essential. Okay, think of the hash table on the right as an indexable block of memory. So, as I said, an array. And we can access these entries with the hash function, h of x. So suppose we're going to be inserting integer string key value pairs into the table that are going to represent rankings of users to their usernames, say in an online programming competition, and this is the arbitrary hash function that we chose, x squared plus 3 mod 10. Alright, let's get started. So if I want to insert the key value pair, 3 byte eater. So in the contest, the user whose username is byte eater got a rank of 3, and we want to insert that into the hash table. Then what we do is we hash the key, which is 3, and we get h of 3 being 3 squared plus 3 mod 10, or 2. So in our hash table or array, at index 2, we're going to put the key be 3 and the value to be byte eater. Alright, now this next user, Will Fizet, which is usually what I call myself in online programming competitions, he is rank 1, and if we hash 1, then we get 4. So at index 4, then we're going to put the key and the value for William, or will.fizet. Next, if we want to insert Lauren, 425, who's got rank 32, again we hash 32, and we put her in the table where she goes. Then we can do the same thing for Ternary Wizard, who has rank 5, and insert Orange Knight, again by hashing the key, finding out where it goes. So as we keep doing this, we keep filling the table, but eventually we're bound to have a collision. Now, in the event that we want to do a lookup for a user that has a rank R, all we need to do is compute the hash value for R and then look inside our hash table to see where this user is. So say I want to find the user with rank 10, and then I hash 10, figure out its index is 3, and then I get the value, which is the orange knight, has rank 10. Great. However, how do we handle hash collisions? For example, users who have ranks 2 and 8 have the same value. This is problematic because we don't have another place to put them inside our table. They would index into the same position, yeah? And the answer is we use one of many hash collision resolution techniques to handle this. There are many, but the two most popular ones are separate chaining and open addressing. The idea behind separate chaining is that we deal with hash collisions by maintaining a data structure, usually a linked list, to hold all the different key value pairs which hash to some particular value. Open addressing is slightly different. It deals with hash collisions by probing and finding another place within the hash table offset from the place where we originally hashed to. So in open addressing, everything is kept inside one big array. In separate chaining, you have multiple auxiliary data structures. So the time complexity of the hash table is actually pretty remarkable. In fact, it's amazing. So on average, we can achieve constant time for insertion, removal, and search, but if you have a terrible hash function that's not uniform, then you can get linear time, which is really, really bad. Okay, let's talk about something super cool, and that is hash tables and separate chaining. Alright, let's dive right in. What is separate chaining? So separate chaining is just one of many hash collision resolution techniques. And how it works is when there's a hash collision, meaning two keys hash to the same value, we need to have some sort of way of handling that within our hash table so that's still functional. Well, what separate chaining does is it maintains an auxiliary data structure to essentially hold all the collisions. And so we can go back and look up inside that bucket or that data structure of values for the item we're looking for. And usually we use a linked list for this, but it's not limited to only linked lists. We can use arrays, binary trees, self-balancing trees, or even a hybrid approach. Okay, so suppose we have the following hash table, which is just a fancy name for an array of key value pairs of age and names. And we associate an arbitrary hash value that has been computed with some hash function. So those are our hash values. They don't really matter for now. We're just going to see how we can use separate chaining to handle the collisions. Okay, so on the left is our hash table, so our array. And I'm going to be inserting all of these key value pairs into this hash table via separate chaining, and you'll see how easy it is. Okay, so our first person is Will, his age is 21, and he hashed to 3. So we're going to put him in that slot 3. Leah, age 18, hashed to 4. Since she hashed to 4, we're going to put her at index 4. So the hash is a way to index into the array. Okay, Rick, age 61, hash 2. We're going to put him there. And Ray, age 25, hash 1. Okay, we're starting to get a little bit full in our hash table here, so we might get some collisions pretty soon. Okay, Lara, age 34, hash to 4, but we say, oh shoot, Leah is already there. What do we do? Well, in separate chaining, we just chain along. So essentially each position in the array is actually a linked list data structure. So we're going to scan through the linked list and see if Lara exists, and if Lara does not exist, then we're going to add Lara at the very end of the chain. Okay. So Ryan also hashed to 1, but then we look and Ryan is not equal to Ray, so we need to add a new entry at position 1. Now Lara, age 34, hashed to 4, so nope. And oh, Lara already existed in our hash table, so we're good. And she still has the same age, so we don't need to update it. So Finn, age 21, hashed to 3, so he's got a hash collision with Will, who had also hashed to 3. So what we're going to do is we're going to append Finn to the end of the linked list chain. So note that even though that Will and Finn both hashed to the same value, that is index 3, and they have the same age, we tell them apart because we store both the key and the value as an entry in our linked list block. So that's how we're able to tell them apart. Okay, now I want to insert Mark, whose age is 10 and who hashed to 4. So scan through the linked list at index 4 for Mark, and he's not found, so we have to append Mark at the very end. Alright, now let's have a look at how we can do lookups in this structure. So it's basically the same thing. So what we're going to do is, given a name, we want to find, well, what the person's age is. So suppose we have Ryan, and Ryan, when we hash him, we get 1. So we suspect that Ryan should be in bucket 1. When I say a bucket, I just mean whatever data structure we're using at index 1. In our case, the linked list. So I have to scan this linked list for Ryan. So we start Ray, no. So here we're comparing the key. So we're comparing the key Ryan to the key array. And there's not a match, so keep going. Compare Ryan to Ryan, there's a match. Okay, we found Ryan, and then inside that entry, say, oh, his age is 56. So return 56. Okay, let's do another one. Find the age of Mark, hash Mark. And since our hash functions are deterministic, we know that if there's a Mark, then it's going to be found in position 4. Okay, so we look into bucket 4, scan through. Oh, the last one is a Mark, so we return age 10. So it might happen that the value or the key you're looking for doesn't exist, and so it doesn't exist. You return null. Okay, so here's a good question. How do we maintain a constant time insertion and lookup time complexity if the hash table gets really full and I have some long linked list chains? Good question. And the answer is that once there's a lot of elements within your hash table, you'll actually want to create a new hash table with a larger capacity and rehash all your items and reinsert them into this new larger table, because tables are fixed size. Okay, and another good question, how do I remove key value pairs from my hash table with separate chaining? Well, the answer is basically the same procedure. You hash your key, and instead of doing a lookup, well, you would remove a particular entry in the linked list. That's it. Another question, can I use another data structure to model the bucket behavior of separate chaining? And yes, of course. And common data structures that are used instead of a linked list include arrays, binary trees, self-balancing trees. Java uses a hybrid approach in their hash map. So once they get to a certain chain length, they switch to a binary tree, or maybe a self-balanced binary tree, I'm not too sure. However, these alternative methods are a bit more memory intensive and complex to implement, which is why they may be less popular, but they might be a lot faster too. I haven't actually implemented them myself. Alright, it's time to have a look at some separate chaining source code for the hash table. So here I am on my GitHub repository, williamcesar/data-structures, and you can find the source code here under the hash table folder. Now I have multiple implementations of the hash table. Today we're going to be looking at the hash table with separate chaining, and in the later videos probably one of these three. I haven't figured out which one yet. So let's dive into the code. I have it here on my computer, so let's get going. Alright, so first things first, I have two classes. One of them called entry, the other one just separate chaining hash table. So let's have a look at the entry class first. And these entries represent individual items or key value pairs you would want to be inserting into the hash table. So in Java we have generics, so a generic key which has to be hashable and some value. So when I create an entry, I give it the key value pairs, and I also compute the hash code. So there's a built-in method in Java to compute the hash code for a particular object, and you can override it to specify the hash code for your particular object, which is really convenient. So compute the hash code and cache it. You absolutely want to cache it so you don't have to recompute this thing multiple times. It should be cheap to compute, but for something like a string, the hash code can take linear time to compute, which is not good. So here I have an equals method, which doesn't override the object equals method because I don't want to have to do any casting. First it checks if the hashes are not equal. If the hashes are not equal, we know from the first video that they are absolutely not equal, so we can return false. Otherwise, I compare the keys to each other. And that's about it for the entry class. Very, very simple, very basic. Now let's get into the meat of the thing, so the hash table itself. Okay, so my default hash table capacity is going to be 3, so it holds three items, and the load factor by default, if the user doesn't specify one, is going to be 0.75. So that's the maximum capacity I'm willing to tolerate. Then I have a few important instance variables we need to go over. So the maximum load factor. So once the load factor goes above this value, then I resize the table. So this is the capacity, so the actual maximum number of items that could, or how big the table size is rather. So the threshold, so this is computed to be the capacity times the max load factor, so it tells us, hey, you're above the threshold to resize, it's time to resize. Size is how many items are currently in the table. And this is the table itself. So it's an array of linked lists which themselves have entries. Pretty simple. So there's a few constructors, so you can construct a hash table just using the default settings with an initial capacity or with a capacity and a max load factor. So this is a designated constructor. Let's have a look. So just save what the max load factor is, compute the default capacity, and make sure you take the max of, say, the default capacity and the capacity, just so that, I don't know, you don't want the capacity to be too low. There might be weird things happening if the capacity is set to 1 or something like that. Then calculate the threshold, and then finally initialize the table. Pretty simple. Okay, let's have a look at all these methods right here. So size returns number of elements inside the hash table. Empty is the hash table empty. Okay, so this is the first really interesting method. It's called normalize index, and it's used when you want to convert a hash value into an index. And it says in the comments here, essentially this strips the negative sign and places the hash value in the domain 0 to capacity. Because hash values are integers, they could be anywhere in the domain of an integer, which is about minus 32 to the 31, sorry, to positive to the 31, around that. So what this does is a mask. It strips off the negative sign from the hash value, and then mod it by the capacity. So bring it into this domain so we can actually use it as a lookup index. Next up is clear, so we just want to clear everything out of the table. That's straightforward. Contains key and hash key are the same thing. So what we're going to do is compute, given a key, so we want to find out, does this key exist within the hash table? Alright, so what we're going to do is compute the key's hash, normalize it, and then that'll give us the bucket index. So which bucket should this key appear should it be in the hash table? Now I'm just going to seek to see if, I'm going to seek to find the entry. If the entry is not equal to null, then it exists. If it's equal to null, it doesn't exist. Simple. Okay, put, add, and insert are all common names for just putting something into the hash table or updating a value inside the hash table too. So we don't want to allow null keys. That's something we absolutely don't want. So just throw an exception there. Otherwise, we're going to create a new entry, find the bucket it belongs to, and then insert it using this method we'll get to. Okay, get. So given a key, I want to find the value associated with that key. Again, don't allow null keys. And this is going to be pretty routine all the time. We're always going to want to find which bucket this particular key belongs to. So get the bucket index. Okay, find the entry. Assuming it's not null, then this is the entry we want and return its value. If it is null, well, the key doesn't exist, so return null. Okay, suppose we want to remove a key now from the hash table. So key is not null, find the bucket index, and we're going to call it this private remove entry method, which is just down here. So given the bucket index, so which bucket does this key belong to? What we're going to do is we're going to seek for the entry inside the linked list structure, and if the entry is not null, then we're going to extract the actual linked list and remove it. So this is a built-in data type in Java, so just remove it from that linked list data structure, decrement the size, and return the entry value. That's all we have to do. Otherwise, it's, well, not there, so return null. So insert bucket insert entry. So given a particular bucket, we want to place this entry inside of it. Okay. So first, since we know the bucket index, we can go in our table and automatically get the linked list structure, which I call bucket. So if bucket is null, well, we have to create a new linked list. So we're essentially lazily allocating these linked list data structures, which is good because we don't want to use more memory than we need to. So next up, I find the entry that already exists. So this is in case we want to do an update, for instance. So if the existent entry is null, this means that we need to add a new entry to the end of the linked list. So add it to the end of the linked list, increment the size, and check if we're above the threshold, and if so, resize the table. And yeah, use null to indicate that there was no previous entry. Otherwise, we need to update that entry. So then just update the value in the existing entry and return the value. Alright. So seek entry, this is a method we've been using pretty much everywhere. And it finds and returns the particular entry at a given bucket index if it exists, otherwise just return null. You probably know what's going on by now, so extract the linked list at the particular bucket index, otherwise return null if it doesn't exist yet. Otherwise, seek through each of the entries in the linked list and compare the keys to the key we're after, and if there's a match, return that entry, otherwise return null. Okay, here's the last really complicated method called resize table. So this resizes the initial table, doubling this capacity of the table. So first we double the capacity. We recompute the new threshold because now we have a higher threshold because we've increased the capacity. Now create a new table with this new capacity. So this new table is bigger than the current table. Then go through the current table, look for linked list data structures which are not null. If you find one, loop through all its entries, calculate the bucket index, find the bucket, and essentially insert it into this new table. And after that, completely remove the old data that was in the old table. And at the end, set the table to be equal to the new table. Okay. And then these last two methods are just return all the keys and all the values within the hash table. Fairly simple. And then these last two methods are iterators and toString, which we don't need to go over. So that's essentially separate chaining in a nutshell. Fairly simple to implement with a linked list, much more difficult to implement with, say, a balanced binary tree or something like that. I'm pretty excited. We're going to be talking about the open addressing collision resolution technique for hash tables. So let's get going. First, let's just do a quick recap on hash tables so that everyone's on the same page. So the goal of the hash table is to construct a mapping from a set of keys to a set of values. And the keys need to be hashable. Now, what we do is we define a hash function on the keys to convert them into numbers. Then we use the number obtained through the hash function as a way to index into the array or the hash table. However, this isn't a foolproof method because from time to time we're going to have hash collisions. That is, two keys that hash to the same value. So we need a way to resolve this, and open addressing is a solution for that. Alright, so when we're going to be using the open addressing collision resolution technique, the one thing you need to keep in mind is the actual key value pairs themselves are going to be stored in the table itself. So as opposed to, say, an auxiliary data structure like in the separate chaining method we saw in the last video. So this means that we care a great deal about the size of the hash tables and how many elements are currently in the hash table. Because once there are too many elements inside the hash table, well, it's going to be really hard to find an open slot or a position to place our element. So just an important piece of terminology, we say that the load factor is the ratio between the number of items in the table and the size of the table. So this means we need to keep tabs on the load factor. Here's a neat chart from Wikipedia. So on the chart, what you can see are two different methods. One of them is chaining, that is separate chaining, and linear probing, an open addressing technique. And what you can see from the linear probing one is that once it gets to a certain threshold, it gets exponentially bad. So you don't want it to go anywhere near that, say, 0.8 mark. In fact, we're going to be keeping it a lot lower than that usually. And what this says is we always need to keep the load factor, which we denote by the Greek letter alpha, below a certain threshold. And we need to grow the size of our table once that threshold is met. Alright, so when we want to insert a key value pair into our hash table, here's what we do. We take the key, we use our hash function, define on our key, and we hash the value, and this gives us an original position inside the hash table for where the key should go. But suppose there's a hash collision, and there's already a key in that slot. Well, we can't have two keys in the same slot. That's not how arrays work. So what we do is we use a probing sequence, which I will define as p of x from now on, to tell us where to go next. So we hashed to the value h of k, the original position, and now we're going to probe along using this probing function in such a way that we're going to eventually find an open slot along the way. So as it turns out, there are actually an infinite amount of probing sequences to choose from. So here are a few of them. We have linear probing, which probes via a linear function. So given an input parameter x, so when we're probing, we start usually x at 0 or 1, and as we're unable to find free slots, then we just increment x by 1, and it works the same for all of these probing functions. For linear probing, we use a linear function. For quadratic probing, we use a quadratic function. And then there's double hashing, which is super neat actually. What we do is we define a secondary hash function on our key, find its value, and then use that inside the probing function. And the last one is the pseudo-random number generator probing function that we can use. So given a random number generator, we're going to seed it using the hash value of our key, which we know is deterministic, so it's always going to be the same thing. And then we can use that inside our probing function, which is pretty neat, and increment by x each time. And we know x increments by 1, so we're just getting the next number in the random number generator, and then the next one after that. Alright, so here's a general insertion method for open addressing. Suppose we have a table of size n, and here's how the algorithm goes. First, we initialize x to be 1. So x is a constant, a variable that we're going to use for the probing. And we're going to increment x each time we fail to hit a free position. Then we get the key hash just by hashing our key, and that is actually going to be the index where we're going to look in the table first. So while the table index is occupied, meaning it's not equal to null, we're going to say our new index is the key hash, or the original position we hashed to, plus the probing function mod n, so that we always land back inside the table, and then we're going to increment x, so that the next time we run this loop, well, we probe at a different position. And then eventually, we're going to find a free position. We always set up our probing function in such a way that we will always find we will always find a free slot, because we know that the load factor is being kept below a certain amount. Alright, so here's the big issue with open addressing. And it's that most probing sequences that we choose, modulo n, are going to end up producing some sort of cycle, shorter than the table size itself. So imagine your probing sequence just hops between 3 different values in cycles, and your table is of size 10, but you're only ever able to hit 3 slots because it's stuck in a cycle. And then all of those 3 slots are full. Well, you're stuck in an infinite loop. So this is very problematic and something we absolutely need to handle. Alright, so let's have a look at an example. So right here I have a hash table, and using open addressing, and it's got some key value pairs already inserted. And assume that the circle with the bar through it is the null token. Further assume that we're using the probing sequence p of x equals 4x. And suppose we want to insert a new key value pair into the table, and that the key hashes to 8. So that means we want to insert that key value pair at position 8, but oh, it's already occupied because there's key 5, value 5 already there. So what we do, well, we probe. So we compute p of 1, which is 4x at 1, so we get 8 plus 4 mod 12, well that's 0, so then we go to slot 0 and we see, oh, that is also occupied because key 1 and value 1 is already there. So then we compute p of 2, and then that gives us 16 mod 12, which is 4, and then, oh, that cell is already occupied, and then we keep probing, and as you see right now, we've entered a cycle. So we would keep probing and probing and probing, and we'd always be getting back to the same position. So although we have a probing function, it does not work in this particular situation. The probing function is flawed. So that's quite concerning, because not all probing functions are viable. They produce cycles which are shorter than the table size. How do we handle this? And in general, the consensus is that we don't handle this issue. Instead, we try to avoid it altogether by restricting the domain of probing functions that we choose to be those which produce a cycle of exactly length n. And those probing functions do exist. I have a little asterisk here, and it says there are a few exceptions, and this is true. There are some probing functions we can use which don't produce a full cycle but still work. And we're going to have a look at, I think, one of those in the quadratic probing video. Alright, so just to recap, techniques such as linear probing and quadratic probing and double hashing, they're all subject to this issue of the cycles. And what we need to do is we need to find probing functions which are very specific, that produce a cycle of length n to avoid not being able to insert an element and being stuck in an infinite loop. So this is a bit of an issue with the open addressing scheme, but it's something we can handle. Although notice that this isn't something you have to worry about if you're in the separate chaining world, just because we have that auxiliary data structure that just captures all our collisions. Okay, this is going to be a fun one. We're going to be talking about hash tables and the linear probing technique. To get started, let's recap how open addressing works. So in general, if we have a table of size n, here's how we do open addressing, no matter what your probing function is. So we start our variable x at 1. The key hash is just going to be whatever a hash function gives us for our key. And our first index we're going to check is going to be the original hash position. And while the table at the index not equal to null, meaning that position is already occupied, then we're going to offset the index by where the key hash is plus the probing function mod n. And every time we do this, we increment the variable x so that our probing function pushes us along one extra position. And then once we found a position, then we can insert the key value pair into the table at that position. Alright, so what is linear probing? So linear probing is simply a probing method which probes according to some linear formula. Specifically, the linear function p of x equals a of x plus b, and we have to make sure that a is not equal to 0, otherwise we're just adding a constant which does nothing. Now I have a small note right here which says that the constant b is obsolete. And if you know why, post in the comments and have a discussion with the others. And as we saw in the last video, there's a slight problem with this currently, and it's that some linear functions are unable to produce a full cycle of order n, and we might end up getting stuck in a cycle. Here's an example of that. If we picked our linear function to be p of x equals 3x, and say our key k hashed to 4, and for some reason our table size was 9, then we would end up with the following cycle occurring. assuming that positions 4, 7, and 1 are already taken by other key value pairs. So the fact that we're only probing at those 3 locations means we're unable to reach all the other buckets, which is really bad, and hence we're again stuck in an infinite loop. We cannot get stuck in this situation ever. So how do we avoid it? So that's the question. Which values of the constant a in p of x equals a of x produce a full cycle modulo n? It turns out that this happens when the constant a and n, the table size, are relatively prime to each other. So 2 numbers are relatively prime if their greatest common denominator is equal to 1. So that is a and n have a GCD of 1. And when that happens, the probing function will always be able to generate a complete cycle. And we will always be able to find an empty bucket. Awesome. Alright, here's an example with linear probing. So suppose we have an originally empty hash table and we want to insert some key value pairs. And we selected our probing function to be p of x equals 6x and our table size to be n equals 9. And then we also selected a max load factor of alpha equals about 2/3, and the threshold will then be 6. So we resize once we hit 6 elements. Okay, so based on the probing function we chose and the table size, are we likely to run into an infinite loop while inserting, based on what I told you in the last few slides? And the answer is yes. The greatest common denominator of 9 and 6 is equal to 3, which is not 1. So let's go ahead and attempt to insert some elements regardless. We may or may not hit any problems. Okay, so first let's insert, so I guess on the left I have some key value pairs I want to insert, and we're going to insert k1 first. So suppose that the hash value for k of 1 is equal to 2. Then we would say, alright, the hash of k1 plus the probing sequence at 0 mod 9 is equal to 2. So we're going to insert that key value pair at position 2. Alright, next one. So now suppose k of 2 is equal to 2 again. So we're going to try to insert this key value pair at position 2, but oh snap, we have a hash collision. So we're going to increment x and now try to offset at the probing function at 1 instead of probing function at 0. So that is, instead of inserting it now at 2, we're going to insert it at 8. Alright, so that went in because that slot was free. Now let's try inserting key 3. So key 3, suppose that hashes to 3, then we can insert at position 3 and there's no issue. Now notice that we're trying to reinsert k2, which already exists within our hash table, so instead of inserting it, we're actually going to be updating its value because it exists in the hash table. Alright, so from before we know that the hash value for k2 is 2, so then we look at position 2, and k2 is not there, and there's a hash collision, so we increment x, offset it by p of 1, and now we're able to find k2, and now we can update the value right there. Let's go to k5. Okay, so suppose k5 has a hash value of 8, so 8 is taken, so we're going to probe, and that leads us to index 5, so we're going to insert the key value pair there. Now let's try to insert k6. Suppose k6 hashes to 5, then let's probe 1, so now so 5 plus 6 mod 9 gives us 2. Okay, another hash collision, let's keep probing. So now 5 plus 12 mod 9 is equal to 8. All right, another hash collision, so we have to increment x and keep probing. And now we're back to 5. So we've hit a cycle. All right, so we're trapped in a cycle, but we kind of expected this to happen because we knew that we picked two numbers whose GCD was equal to 3 and not 1. So if we look at all the possible a values we could have selected instead of 6, we see that the ones that give a greatest common denominator of 1 with n the table size are 1, 2, 4, 5, 7, and 8, while any multiple of 3 would give us something else. So this comes to the realization that for our choice of p of x, if we choose p of x to be 1 times x, then the greatest common denominator of n and 1 is always going to be 1, no matter what our choice of the table size is, which is why p of x equals 1 times x is a very popular probing function choice. Alright, now suppose we have another hash table and we wish to insert more key value pairs, but this time we're actually going to pick a probing function that works so that we don't ever have any issues. So I'm going to pick the table size to be 12 and our probing function to be 5x. So no cycle should occur. Alright, so let's go with inserting the first guy. So suppose that k1 has a hash value of 10, then at index 10 we have to put k1 v1. Suppose k2 has a hash value of 8, then slot 8 is free, so let's pop those right in there. So now suppose k3 is equal to 10. Oh, hash collision with k1 in there, so we need to keep probing. Alright, so if we use our probing function, which is p of x equals 5x, so that'll give us 3 modulo n when we add it to the hash value. Moving on, insert k4. Now suppose the hash value for k4 is 10, then we have to keep probing. So then we hit k3, which we inserted last time, and then oh, we also hit k2, but we're able to pull out eventually when we hit the third probing value. However, now notice that we've actually reached the threshold of our table. If I go back a few slides, we can see that I picked alpha to be 0.35. So n, which is the table size, times alpha gave us 4. And we just finished inserting the fourth element, so it's time that we resize the table. So how we usually resize the table is via some exponential fashion, such as doubling or tripling or so on. But we need to double in such a way that the GCD of n and a still holds. So after doubling, n is equal to 24, and the GCD property is still good. Alpha is a constant, so it's still 3.5. So our new threshold is just going to be 8, and we don't change the probing function. Alright, so let's allocate a new chunk of memory for this new table. And now we need to place all the old elements in our old table into this new table using the new table size for n. Alright, so if we scan across all these elements, we start at 0, nothing there, move along. So from before, we knew that hash value for k4 was 10, so inside the new table, it's going to go at position 10. Alright, scan along, nothing here. From before, we know that k3 was 10, so it should go in position 10 in this new table, but we have a hash collision, so we have to keep probing. So if we add our probing function at 1, which is 5x, then we get 10 plus 5, which is 15. So we're going to insert it at position 15 in the new table. Keep probing, nothing here, nothing here, nothing here. So eventually we hit K2. So we know from before K2 is equal to 8. So we're going to insert at position 8. Now we know K1 is equal to 10. So we're going to try and insert at position 10. That's taken, so we have to probe. So the next position is also taken, so add 5 again. That gives us 20. So we're going to insert K1, V1 at 20. Alright. So now we throw away the old table and we keep this new table, and this is the new hash table we're working with. And we were at inserting K5. Now suppose K5 is equal to 2, and that spot is free. So we are good. So here's a frequently asked question. Sweet. I know how insertion works. Now how do I remove key value pairs from the hash table using open addressing? And my answer to this is that this topic is going to merit its own video, and we're going to do it after we see all the other open addressing techniques, because it's actually non-trivial. Alright, let's talk about hash tables and how quadratic probing works. Let's dive right in. So let's recall how we insert key value pairs into a table of size n using the open addressing collision resolution schema. So first we initialize a variable called x to be 1, which we're going to increment every time we're unable to find a free slot. Then we compute the key hash, and that's going to be our first index we're going to check. And we're going to loop while we're unable to find a free slot, meaning the table at that index is not equal to null, so it's already occupied. Every time that happens, we're going to offset the key hash using our probing function. Our probing function in our case is going to be a quadratic function. And then we also increment x, and eventually we will find an open slot to insert our key value pair. So what is the idea behind quadratic probing? So quadratic probing is simply probing according to a quadratic formula, or specifically when our probing function looks something like p of x equals ax squared plus bx plus c, and ab and c are all constants, and we don't want a equal to 0, otherwise we degrade to linear probing. But as we saw in the previous videos, not all quadratic functions are viable because they don't produce a cycle of order n, and we might get stuck in an infinite loop. So as it turns out, most randomly selected quadratic probing functions will end up producing a cycle. Here's an example. Suppose we chose our probing function to be p of x equals 2x squared plus 2. The key we wanted to insert hash to 4, and the current table size was 9. Then we would end up with a 2 cycle. So first time around we would probe at position 0, we would get 4, probe at position 1, we get 7. Suppose those two entries were full, and then we would end up in a cycle again. So our probing function is only ever able to hit the buckets 4 and 7, so it makes it impossible to reach all the other buckets 0, 1, 2, 3, 5, 6, and 8. So we're stuck in an infinite loop when 4 and 7 are already occupied. This is really, really bad. So the question then is, how do we pick a probing function which always works? The answer is there are numerous ways, but here are the 3 most popular ways I have found. So the first way is to select the probing function to be p of x equals x squared, and to keep the table size a prime number greater than 3, and make sure our load factor is always kept below 1/2, or less than or equal to 1/2. The other one is to say our probing function equals x squared plus x divided by 2, and make sure the table size is a power of 2. And the last and final one says that p of x should be the alternating sign of x squared, and keep the table size a prime number where n is congruent to 3 mod 4. For example, we could say that our table size was 23 because that's a prime number and it's congruent to 3 mod 4. So any of these will work, but as you see, they're very specific in how they work and what the table size should be, and that's a common theme in quadratic probing. So we're going to focus on the second one, where p of x equals x squared plus x divided by 2, and the table size is a power of 2. Alright, suppose we have an initially empty hash table and we want to insert some key value pair, and we're using the following quadratic probing function. P of x equals x squared plus x divided by 2, and the table size is a power of 2, so it's 8. And let's select the load factor to be 0.4, therefore the table threshold is going to be 3. So just to emphasize that the table size must absolutely be a power of 2, otherwise this will not work. Okay, so let's insert the first guy. So suppose that k1 hashes to 6, then we're going to insert k1 at position 6. Alright, next k2, suppose k2 is equal to 5, then we're going to insert it at 5, no collision there. Suppose k3 is then equal to 5, then we have a collision, so we need to handle that. So we're going to try probing at offset 1, so that brings us to 6. So we probe again, and that brings us to index 0, which is free, so we're going to insert k3 and v3 key value pairs there. Let's insert k4. Oh, but before we can do that, we've reached the table threshold, so we have to resize the table first. Okay, so let's allocate a new block of memory, and let's double the size of the table to keep it a power of 2. So our new table size is 16, the max load factor doesn't change, however our new threshold is 6, and the probing function doesn't change. So we need to place the entries in the old hash table into the new hash table. So from before, we know that k3 hashed to 5, so we're going to put it at index 5 because we don't have a collision there. Then no element at position 1, 2, 3, or 4. Then we go to position 5 and find k2 right there. So we know from before that k2 also hashed to 5. So we're going to try to put it at position 5, but there's a hash collision, so we probe 1. And then we get 5 plus 1 equals 6. So at position 6 we're going to insert k2. Now let's try and insert k1. And we know from before k1 hashed to 6, but we can't put it there because we have a collision, so we're going to probe along, so we're going to put it in position 7. Alright, and that does it for resizing the table. So let's keep going. We still have a few more elements to insert inside our table. So suppose that k4 equals 35,410. So when we mod that by 16, that gives us position 2. So we're going to say k4, v4 at position 2. So we've already seen k3, and we know its hash value is equal to 5. So since k3 is already in our hash table, we're going to be performing an update. So k3 plus the probing function at 0 gives us 5. So let's update value to be v5 instead of v3, which it was before. So suppose that the key k6 hashed to minus 6,413. So that hashes to 3 mod 16. So that slot is free, so we're just going to insert it. And the last one, k7, suppose it hashes to 2. Well, we have a collision right there, so let's probe along. So when we probe, our probing function gives us an offset of 1, that's also taken, so probe again. So now we are at position 5, but that's also taken, so keep probing again. So we probe for a 4th time to get an offset of 6, so that gives us 8, and that slot is free, so we're going to insert that there. Alright, let's talk about hash tables and the double hashing open addressing collision resolution technique. So just a quick recap for those of you who don't know how we do insertions into hash tables for open addressing. We start with a variable x initialized to 1. We compute the hash value of the key. We set that to be the first index that we're going to check in our hash table to see if it's not null. So the goal is to find an empty slot. So we're going to loop while we are still hitting spots where there are already keys, and every time that happens, we're going to offset our key hash using a probing function. In our case, it's going to be the double hashing probing function, and we're also going to increment our value of x so that we keep probing along further and further. Once we find a free slot, then we can insert our key value pair into the hash table. Okay, so what's the deal with double hashing? So double hashing is just a probing method like any other, but what's special about it is that we probe according to a constant multiple of another hash function. So specifically, our probing function looks something like this. We give it as input the key, which is a constant, and the variable x, and then we compute x times h sub 2 of k, where h2 of k is a secondary hash function. So here's an important note. h2 of k must hash the same type of keys as h1 of k. So if your key is a string, well, h2 of k must hash strings. If h1 of k is, hashes integers, then h2 of k must also hash integers. So here's a note I put at the bottom that notice that double hashing actually reduces to linear probing, except that the constant is unknown until runtime, because we dynamically compute it with h2 of k. So since double hashing reduces to linear probing at runtime, we may be stuck with the same issue we saw with linear probing, which is that we get stuck in an infinite cycle. So if p of x equals 3x, meaning our secondary hash function at runtime calculated a value of 3 for the constant, and say h1 of k was 4, and the table size was 9, then we might end up with the following cycle occurring. So the cycle produces values of 4, 7, and 1, which makes it impossible to reach any of the buckets 0, 2, 3, 5, 6, and 8. So if 4, 7, and 1 are already occupied, that means we're stuck in an infinite loop inside our hash table, and we're not able to insert our key value pair because we're not able to go anywhere else. So this is an issue we have to deal with. So to fix the issue of cycles with double hashing, here's one strategy. We're going to pick our table size to be a prime number, and we're going to compute a value called delta. So delta is just going to be h2 of k mod n, but occasionally delta might be 0. And if that's the case, then we're going to be guaranteed to be stuck in a cycle because we're not going to go anywhere when we probe because we're going to be multiplying by 0. So when this happens, just set delta to be equal to 1. Alright. So here's a justification why this works. So notice that delta is always going to be between 1 inclusive and n non-inclusive. So the greatest common denominator between delta and n is going to be 1, since n is a prime number. So therefore, with these conditions, we know that the probing sequence is guaranteed to have order n. So we're going to be able to hit every single slot in our hash table. So given that there's at least one free slot in the hash table, which there will be because we're keeping our load factor below a certain threshold, then we're going to be able to reach that slot. Okay, so here's our core question. How do we construct our secondary hash function? Suppose the keys we're using have type T. And whenever we use double hashing, then we need to construct h2 of k to hash keys that are also of type T. So it would be really nice if we had a systematic way of generating these new hash functions every time we need one, right? Because we might be dealing with multiple different data types of type T. So luckily for us in computer science, almost every object we ever create is constructed of the same fundamental building blocks, in particular integers, strings, real numbers, fixed length vectors, and so on. So we can use this to our advantage. Luckily, there are many well-known hash functions for these fundamental data types, and we can combine them when we want to construct our new hash function, h2 of k. Frequently when we compose hash functions, we select them from a pool of hash functions called universal hash functions, which generally operate on these fundamental data types, which is quite convenient. Alright, let's have a look at an example with double hashing. So suppose we have an originally empty hash table above, and we selected our probing function to be p of x equals x squared plus h sub 2 of k, which is what we need it to be, and our table size to be n equals 7. Notice that that's a prime number, and we set our max load factor to be alpha equals 0.75, so our threshold to resize is 5, so once we hit 5 elements, we need to grow the table size. Alright, so let's insert all of these key value pairs on the left into this hash table. So first key value pair is k1 and v1. Now suppose that the hash value for the first hash function of k1 is 67 and h2 of k1 is 34. Then first thing we do is we compute delta. So we compute h2 of k1 modulo 7, which is the table size, and we obtain 6. And then we compute where this key value pair should go, and it should go at position 4. So now k2, suppose h1 of k2 is 2 and h2 of k2 is negative 79. So delta is 5, but we're just going to insert at position 2 because there's no collisions. So h1 of k3 is 2 and h2 of k3 is 10. These are just arbitrary numbers I chose for these hash functions. So then delta would be 3 in this case because 10 mod 7 is 3. So we have a hash collision because we're trying to insert our k3 at index 2, but k2 is already there. So what we need to do is we need to probe. So we're going to compute the position to be our original hash function position, so h1 of k3 at position 2 plus 1 times our delta value mod 7, that gives us 5. So we're going to hop to position 5 right there. Alright, now let's insert k4. So suppose now that h1 of k4 is equal to 2 and h2 of k4 is equal to 7. So let's compute delta. So h2 of k4 modulo 7 is equal to 0 because 7 mod 7 is 0. So when this happens, we know that we need to set delta equal to 1 so that we don't get stuck in an infinite loop. So now h1 of k4 plus 0 times delta mod 7, that gives us 2. So we have a hash collision at the bucket for index 2. So we need to keep probing. So now we probe by multiplying by delta. That gives us index 3, and then we were able to insert. So now we're going to try insert K3, which is already in our hash table actually, but with a new value. So we're going to be performing an update this time. So suppose h1 of K3 is equal to 2. Actually, we should have known that from before. And h2 of K3 is 10. So we compute delta. So we have a collision. And we find K3, which was already in there, and update its value. Now suppose the first hash function for K6 is 3, and the secondary hash function of K6 is 23, then that gives us a delta value of 2. So when we try to insert it, it goes to position 3, so we need to probe. So we compute 1 times delta mod 7, that gives us 5. There's another collision, so then we compute the offset at 2 times delta mod 7, which gives us 0. And we find a free slot, so we're able to insert our key value pair there. So notice that we've actually inserted 5 elements, so it's time to resize and grow the table because we've reached the maximum threshold. So one strategy when we're trying to resize the table with double hashing, because we need to keep our table size to be a prime number, is to double the table size and then find the next prime number above this value. So in our case, when we double, we get 14, and the next prime number above 14 is 17. So 17 is going to be the new table size. So allocate a new table of size 17 and go through the elements in the old table and insert them into the new table. So from before, h1 of K6 is 3 and h2 of K6 is 23. So we compute delta, and we know we're going to put it at position 3 and there's no hash collision. Next up, nothing in position 1. In position 2 we have K2, so the hash value for K2 is 2 and the secondary hash value for K2 is negative 79 from before. So we compute delta to be 6. So we're going to insert that at position 2 with no collision. Next one, K4. So we know h1 of K4 is 2, and h2 of K4 would be 7. So we compute our delta value, and notice that our delta value now is not 0, which it was before, but 7 because our mod is 17. So delta is 7. So we have a hash collision here, but we need to keep probing. So compute the offset at 1 times delta, which gives us 9 mod 17. Next one, insert K1. Suppose h1 of K1 is 2 and h2 of K1 is 34. Then compute delta, and that gives us 0. So when delta is 0, set it to be 1. So now h1 of K1 plus 0 times delta gives us 2. So there's a collision there, so we need to keep probing. So now compute the offset at 1 times delta. There's still a collision. Keep incrementing the x value. So now 2 times delta, which is 4, and we found a free slot. So insert that key value pair there. And the last one, K3. So from before, h1 of K3 is 2 and h2 of K3 is 10. Delta is then 10. And we have a hash collision. So 1 times delta now gives us 12, and that slot is free. And we reached the end of the new table. So get rid of the old table and replace it with the new table. And let's finish inserting our last key value pair from before, which is K7. Now suppose K of 7 is equal to 15 and h2 of K7 is 3. Then our delta value is 3, and we're able to insert it at position 15. Alright, I know a lot of you have been anticipating the remove video for how we remove elements from a hash table using the open addressing scheme. So let's have a look first at what issues there are when we remove elements if we do it naively. I think this is valuable. So suppose that we have an originally empty hash table and we're using a linear probing function. So p of x is simply going to be equal to x. And we want to perform the following operations. We want to insert 3 keys, k1, k2, and k3, and then remove k2, and then get the value of k3 after. And for the sake of argument, let's assume that we have a hash collision between k1, k2, and k3, all equal to 1. This is a possible scenario. So let's insert them. So k1 hashes to 1, so we're going to insert it at position 1. So let's insert k2. So it has a hash collision with k1, which is already in the table, so we're going to linearly probe. So insert it in the next slot over. Let's insert k3. It also hashes to 1. So let's probe. Okay, another hash collision. So let's keep probing. And finally we insert it in position 3. Now we are going to remove k2 and we're going to use the naive removing method where we're just going to clear the contents of the bucket. To find k2, we hash k2, get 1, but k1 is not equal to k2, so we haven't found the element yet. So then we probe, and then we have found k2. So we're just going to remove it, like so. Alright, now let's query the table and obtain the value for k3. Let's see what happens. So when we hash k3, we get 1. And k1 is not equal to k3, so let's continue the search. And then we hit a null element. So what does this mean? So since the value in the bucket at index 2 is null, we're forced to conclude that k3 does not exist within the hash table, otherwise we would have encountered it before reaching the null position. That's how finding an element works inside a hash table. So this method is clearly flawed. The naive removing method doesn't work because k3 clearly exists within the hash table. We can see it there in index 3. So here's a solution to the removing. When we remove an element, we're going to place a unique marker called a tombstone instead of a null element to indicate that a specific key value pair has been deleted or removed. And when we're doing a search, we're just going to skip over the tombstones. So let's replace the deleted bucket with a tombstone like we should have done and see what happens when we now search for the key k3. Okay, so k3 hashes to 1. So k1 is not equal to k3, so keep probing. Alright, we hit a tombstone, so we know that that element was deleted, so keep probing. Alright, we have found k3, and we can now return its value v3 as our answer for the search. Awesome. Okay, so a quick question about tombstones. I have a lot of tombstones cluttering my hash table. How do I get rid of them? So the thing with tombstones is that we're actually going to count them as filled slots in the hash table. So they're going to increase the load factor, and they'll all be removed when we resize the hash table. But there's also another way to get rid of them, is that when we insert a new key value pair, then we can replace the buckets that have tombstones with a new key value pair. And I want to give you guys an example of how that is done. Alright, suppose this is our hash table of size 8, and we're using the quadratic probing function p of x equals x squared plus x divided by 2, and let's see how tombstones come into play doing this when we want to do a lookup. So suppose we want to insert the key K7 inside the hash table, and the hash value for K7 is 5. So we're trying to find the key K7. So K7 hash to 5, so we check there first. K7 is not equal to K4, so let's keep probing. So we probe quadratically, and we're just going to go to the next slot over, and that's position 6. Now, position 6 is special because it's the first position we encounter which has a tombstone in it. So we were going to want to store this position for later to perform an optimization. Okay, keep probing because we haven't found K7 yet. So when we probe at position 2, we go to position 1. Still no K7 because we have a tombstone, so we have to keep going. Alright, hit another tombstone. So let's keep probing. And aha, we have found our key K7. So we can return the value V7 now. However, we can do an optimization because we don't want to probe an additional 4 times to find K7 because we just hit a bunch of tombstones along the way. So an optimization we can do is to relocate the key value pair K7 V7 to the first position where there was a tombstone. So that next time we do a lookup, it'll be much faster. We call this lazy deletion or lazy relocation. Alright, so we replace the first tombstone there with K7 V7. Now we have 2 copies of that key value pair, so we're going to want to replace the old one with a null token. Okay. Alright, today we're going to be having a look at some source code for a hash table that uses open addressing as a collision resolution scheme. And you can find all of the source code on GitHub at williamfizet/data-structures. And then just go to the hash table folder to find a whole bunch of hash table implementations. I have 3 different open addressing implementations here. In particular, we have quadratic probing, linear probing, and double hashing. They're all very similar to each other, so I will only be looking at one right now, but if you're curious, you can go on GitHub and check them out for yourself. The one that's really different, or slightly more different, is the double hashing, but other than that, they are really essentially the same thing. So today I've decided that we're going to have a look at the quadratic probing file, so let's dive into the code. Alright, here we are inside the code for the hash table that uses quadratic probing. So let's dive right in. So I have a class called hashtable quadratic probing, and notice that it takes into generic types k and v. So this is the key type and this is the value type. So you're going to have to specify these when you instantiate an object, which is a hash table for quadratic probing. So I have a bunch of instance variables that we're going to need. The first is the load factor. So this is going to be like the maximum load factor that we're willing to tolerate. The current capacity of our hash table, the maximum threshold we're willing to tolerate, the modification count, this is for the iterator. Next, I have 2 instance variables that keep track of the total number of buckets being used and the key count, which tracks the number of unique keys that are currently inside the hash table. Now, since we're doing open addressing, we are storing these key value pairs directly inside an array. So instead of having one array with a wrapper class for an entry, I've decided just to allocate 2 different arrays, one for keys and one for values. It makes the code a lot easier and shorter, actually. Okay, this is just an instance variable we're going to be using, or rather setting, when we call the get method. So this is the tombstone I was talking about in the last video. This is the marker we're going to be using for deletions. So every time we delete an entry, we're going to mark it with a tombstone. And we know this tombstone object is unique. Alright, so these are just some default constants. So whenever you want to initialize a hash table without any parameters, you can use these constants. So this is the default load factor. I set it pretty low, but you can change it up as you like. So you can initialize it with a default capacity. And this is the designated constructor. So let's have a look. So the capacity can't be negative or 0. And I check if the user passes in some sort of weird load factor, because we don't want that. So then set the max value for the load factor, then calculate the capacity, and to ensure that the capacity is a power of 2, I need to essentially round up the capacity. So that's going to be with this method next to power. Essentially it finds the power of 2 that is just above this current number, or it'll also take the default capacity, which itself is a power of 2, so we don't have to worry about that. So either way, it's going to be a power of 2. Then we compute the threshold, which is just load factor times the capacity, and initialize our tables. Alright, so let's get rolling. So this is the quadratic probing function I chose. So p of x, so you give it the variable x, and then we compute x squared plus x divided by 2. So this is a really important method, the normalize index. So given a hash value, it essentially strips the negative sign and mods by the capacity, so it dumps our hash value inside the domain 0 to the capacity, non-inclusive. This is a clear method. This is pretty self-explanatory. Just clear the contents of the hash table and start fresh. Then some helper methods, size, get the key count, and check if our hash table is empty. Then put, add, and insert are essentially all the same method. So let's look at the insert method. This inserts a key value pair inside the hash table or updates a value if the key already exists. Alright, we don't want to allow null keys. If that happens, we throw an exception. If the number of buckets used is greater than or equal to the threshold we're tolerating, we're going to resize the table before doing anything else. Otherwise, we want to calculate the hash value from the key using the built-in hash code method, and you can override this for your particular object. Okay, now I need to explain what I, j, and x are. So I is going to be the current index we're at in the hash table, because we're going to be bouncing around. This I value is going to change a lot. Then j is the position of the first tombstone we encounter, if we encounter one. Otherwise it's -1. And we're going to be using this for an optimization. And then x is just the probe offset, which I've set to 1 initially. Okay, so this is a do-while loop. It's a little long, but it's pretty easy to understand. Alright, so first we check in the key table, have we hit a tombstone? If we have, and j is equal to -1, that means we haven't hit a tombstone yet, so save where we found this tombstone. Okay, so this next check checks if the key table has an entry that's not null, meaning there's a key inside of it. So we have to check if the key already exists within the hash table, so that's what this does. It compares the current key at index I with the key we're trying to insert, this key. And if j is equal to -1, meaning we haven't hit a tombstone, then just update the value. If we've hit a tombstone, then we want to do a swap with the tombstone and up the modification count, and always return like the old value that was there before, just in case you want to use it. Alright, next up, the current cell is null, so we can do an insertion. Oh, so j is equal to -1 means that we haven't seen a tombstone so far. So increment the number of used buckets and the key count, and then store our key value pair. Otherwise, we have seen a tombstone, and instead of inserting where at element I, where the null element is, insert it where the deleted token was found. So we're inserting it at J instead of I, so here we're inserting at I, but instead of inserting at J where the tombstone is. And we're going to return null because there was nothing there before. Okay, and if we do a loop, so we get through all these if statements and we haven't returned, that means that we need to keep probing. We had a hash collision and the cell we landed on already had something in it, so we need to probe. So we need to offset where we first originally hashed to plus the probing index, or the probe position, and increment x at the same time. So this will just hop to the next spot. And we do this while we haven't found an empty slot, and we will find an empty slot. Alright, so contains key and has key. Just check if a key exists within the hash table. And to do this, I'm being pretty lazy and I'm just calling the get method, and I'm setting an instance variable in there called contains flag, which gets set to true or false whether a key is inside our hash table or not, because the has key and the get method would have essentially the same code, so that's a bad code smell. Alright, so let's look at the get method since it's getting used in the has key method. So same kind of setup, find the original hash, index is equal to the hash, set j and x to what they were before. So essentially do all the same stuff, or mostly, except set the flag, so that's different. We set the flag to be true when we identify that the key is indeed inside the hash table, and here our else condition is just shorter. We return if we hit a null cell instead of inserting a new element, and set the contains flag to be false. Okay, so pretty easy. And the remove method is actually quite a bit shorter, interestingly. So same setup, check if the key is null, find the hash, set x to be equal to 1. Here we don't really care about tombstones too much, so we don't have a j position. So we're going to start the hash index and quadratically probe until we find a spot. So for every loop, we're going to increment I, or find a new offset position if this loop gets completed. So here's what we do. We ignore tombstones, so we just skip over those. So this happens if the key was not found in the hash table, we can return null. Otherwise, the key we want to remove is in the hash table. And we can do this check because we checked if it's null before, so we're not going to get a null pointer. So decrement the key count, up the modification count, extract the old value, and dump a tombstone here, and just wipe whatever value is in there. So this is where we set the tombstones in the remove method. And then just return the old value for good measure. Alright, and okay, these two methods are pretty self-explanatory. They just return all the keys and return all the values that are contained within our hash table. So the next really interesting method is this resize table method. So this gets called when we're inserting new elements and we need to grow the table size. And remember that in this particular quadratic probing implementation, we always need the capacity to be a power of 2. But since we know that the capacity is already a power of 2, multiplying by 2 will keep it a power of 2. So that's fine. So recompute the new threshold, allocate some new memory for a new table. I called it old table, but it's actually going to be the new table shortly. So here I perform a kind of interesting maneuver here. I swap the current table, that is the smaller table, with this new table, which I call old table, in order to be able to call the insert method down here. We'll get to that. So swap the key tables, swap the value tables, reset the key count and the bucket count. And the reason I called it old key table was because since the swap, well, the new table is actually the current pointer for what was the old table. That might sound confusing, but I'm using the table we had before to do insertions on, or the pointer to it. Alright, so loop through the old table values, and if we encounter a token or a pointer that's not null and not a tombstone, then we want to insert it. So because we're avoiding reinserting tombstones, we're getting rid of all the tombstones. So even though our table might have been cluttered with tombstones, we're just getting rid of all of them here. Alright, so that's that. The iterator, you can probably have a look at this yourself. It's just looping through all the keys and returning them one at a time. That's a pretty standard two-string method. So that's how you do quadratic probing with open addressing. Today I want to talk about the Fenwick tree, also sometimes called the binary index tree, and you'll see why very soon. This is one of my personal favorites because it's such a powerful data structure and it boasts efficiency, and it's really simple to code. So let's dive right in. So things I'm going to be covering in the Fenwick tree video series, just some standard stuff. So go over some motivation, why this data structure exists, analyze its time complexity, and then go into some implementation details. So in this video we'll get to the range query, and in later videos how to do point updates and how to construct the Fenwick tree in linear time. You can also do things like range updates, but I'm not going to be covering that in this series. At least not yet. Okay, so what is the motivation behind the Fenwick tree? So suppose we have an array of integer values and we want to query a range and find the sum of that range. Well, one thing we can do would be to start at the position and scan up to where we want to stop, and then sum all the individual values between that range. And that's fine, we can do this. However, it'll soon get pretty slow because we're doing linear queries, which is really bad. However, if we do something like compute all the prefix sums for the array A, then we can do queries in constant time, which is really good. So if we set the array P at index 0 to be 0, and then we go in our array A and add that element to the current prefix sum, we get 5, and then 5 plus minus 3 give us 2, and then 6 plus 2 is 8, and so on. So this is an elementary form of dynamic programming right here, calculating all the prefix sums. And then if we want to find the sum from, say, 2 to 7 non-inclusive, then we can get the difference between those two indices in the P array. And that's a constant time thing to compute the sum of the values between 2 and 7 non-inclusive, so that's really great. However, there's a slight flaw in this, which is what happens when we want to update a value in our original array A. Say we want to update index 4 to be 3. Well, now we have to recompute all the prefix sums. So this is really bad because recalculating all those prefix sums can take up to linear time. This is why the Fenwick tree was essentially created. So what is the Fenwick tree? So the Fenwick tree is a data structure that supports range queries on arrays and also point updates. Also range queries, but we won't be covering that in this video. So its construction is linear time, point updates are logarithmic, range sum queries, also logarithmic, range updates, logarithmic, but you can't say add elements to the array. You can't make the array bigger or entirely remove elements. Okay, so let's look at how we can do range queries on this thing. First thing you need to know is that unlike a regular array, a Fenwick tree, each cell is not responsible for itself, but rather for a range of other cells as well. So we're going to say that a cell is responsible for other cells depending on what the value of its least significant bit is in its binary representation. So on the left, I have a 1-based array. Fenwick trees are 1-based. That's very important. And on the side of that, I also put the binary representation of each of the numbers so you can clearly see what they look like in binary. So if we have, say, the index 12, its binary representation is 1100. So the least significant bit is that leftmost bit. So that is at position 3 in the binary representation. So that index is responsible for, we're going to say 2 to the power of the position minus 1, so 4 cells below itself. Similarly, 10 has a binary representation of 1010, and the least significant bit is at position 2, so it's responsible for 2 cells below itself. And 11 has the least significant bit at position 1, so it's only responsible for 1 cell itself. So here I've outlined the least significant bits, it's getting really hard to say, for all the odd numbers which are just responsible for themselves. So that's what the blue bar indicates. The blue bars don't represent value. They represent range of responsibility, and that's really important for you to keep in mind. So now all the cells which have a range of responsibility of 2, now the cells have a range of responsibility of 4. Notice that all these ranges of responsibilities are powers of 2. 8 is responsible for 8 cells, and I guess 16 for 16 cells. So now how do we do a range query on this now that we're not really working in a standard array, but rather this weird type of range of responsibilities? And the answer is we're going to calculate the prefix sum up to a certain index, and that's what's eventually going to allow us to do range queries. So let's figure out how to do prefix sums just like we did for a regular array, but on this Fenwick tree. So the idea is we're going to start at some index and cascade downwards until we reach 0. You'll soon see what I mean. So for example, let's find the prefix sum up to index 7. So we're calculating the prefix sum from index 1 to 7, inclusive. Usually everything in a Fenwick tree is inclusive. So if we look at where we are at 7, so we can get the value in the array at position 7, and then we want to cascade downwards. So the next guy below us is 6, and then 4. Notice that we're like hopping down. So we start 7 and then we move down to 6, and then from 6 we go down 2 levels because 6 has a range responsibility of 2, and then we're at 4, and 4 has a range responsibility of 4, so that brings us all the way down to 0, and we're always going to be able to go from where we are all the way down to 0. So the prefix sum for 7 is the array at index 7 plus the array index 6 plus the array index 4. Alright, now to find the prefix sum for index 11. So we always start at where we are, so that's 11. And then we're going to cascade down, so the cell directly below us is 10. And 10 is a range of responsibility of 2, so we're going to go down 2. So that's 8. And then 8 brings us all the way down directly to 0. Okay, cool. And one last one, let's find the prefix sum up to index 4. So 4, we start at 4. 4 is a range of responsibility of exactly 4, so that's already, we're back down to 0, so we can stop. Okay, let's pull this all together and try to do an interval sum between I and j. So let's calculate the interval sum between, say, 11 and 15. So the idea is we're going to calculate the prefix sum of 15 and 11. So we're going to calculate the prefix sum of 15, and then we're going to calculate the prefix sum up to 11. But notice that we're not going to calculate up to 11 inclusive, but exclusive, because we want the value at 11. Okay, so if we start at 15, then we cascade down until we hit 0. So 15 has a range of responsibility of 1, subtract 1 from 15, and then we get to 14. And 14 has a range of responsibility of 2, because the least significant bit on 14 is 2. Okay, now we go to 12, and then keep cascading down. So the prefix sum for 15 is the array at index 15 plus the array at 14 plus 12 plus 8. Alright, now the prefix sum for up to 11 non-inclusive, so we're going to start at 10. Then we want to cascade down until we hit 0. So 10 has a range of responsibility of 2, so subtract 2 from 10, we get to 8. Now from 8 has a range of responsibility of 8, so cascade down, so 8 minus 8, 0. So now the range sum is the sum of all the indices of 15 minus those of 10. And that's how we would calculate the range sum. So notice that in the worst case, we're querying a cell which has a binary representation which is all ones. And these are the numbers of the form like 2 to the n minus 1. So a power of 2 minus 1. So a power of 2 has a 1-bit set and all zeros, but when you subtract 1, then you get a whole bunch of 1s. So if you look at like 15, almost all of its bits are 1s, and those are the worst cases. So in the worst case, we might be asked to query, say, 15 and 7, both of which have a lot of 1s in them. So we're doing about 2 log base 2 of n operations. But in the average case, this is actually pretty good, and we're going to implement this in such a way that it's just going to be bit manipulation. So this is like super fast. So the range query algorithm is pretty much this. You see it's like literally no code. The range query from I to j, we have a Fenwick tree of size n. So I'm going to define a function called prefix sum, which does that cascading down operation. So we start at I, and while I is not equal to 0, we're going to sum up the values in our Fenwick tree, and we're going to remove the value of the least significant bit. And we're going to keep doing this until our value is 0, and then we can return the sum. So the range query then is just a difference between those prefix sums. So really neat little algorithm. I want to talk about Fenwick trees and point updates. So let's dive right in. But before we get to that, absolutely make sure you checked out the Fenwick tree range query video that I posted last. Just to get the context of how the Fenwick tree is set up and how we're doing operations on it. Okay, so just to refresh your brain on how we actually did a prefix sum and how we did those range queries. So what we did was we started at a value at some index, doesn't matter which, and then we continuously removed the least significant bit until we hit 0. So that's the cascading down effect that gave. So let's say we started at 13. Well, 13's least significant bit was 1, so we removed 1. And then we got 12, and then we found out that the least significant bit of 12 was 4, and so we removed 4, and then the least significant bit of 8 was 8, and then we reach 0. And once we reach 0, we know that we're done. So doing a point update is very analogous to this, but instead of removing, we're going to be adding the least significant bit, as you'll see. So for instance, if we want to add a value at index 9, then we have to find out all the cells which are responsible for 9. Because remember, cells are responsible for a range of responsibility. So if we start with 9, we find the least significant bit and add it to 9, and we get 10. So 10, find the least significant bit, has a value of 2. Then we add it to 10. Then find the least significant bit of 12, add it to 12. So that was 4, so now we're at 16. And then we would do the same thing, and then we're out of bounds, so we would know to stop. So if I draw a line outwards from 9, all the cells that I hit are the ones I have to update. So remember, those lines represent a range of responsibility. So the lines that I hit are the ones that I got when I added the least significant bits. Okay, so if we want to add some constant x at position 6 in the Fenwick tree, which cells do I need to modify? So we start with 6, and then we find the least significant bit of 6 and add it to 6, so we get 8. Now find the least significant bit of 8 and add it to 8, so we get 16. So if I draw a line out from 6, then indeed the cells that I do hit are 6, 8, and 16. So the required updates for our Fenwick tree are that we need to add x to position 6, 8, and 16. So the algorithm is really simple. So if we have a Fenwick tree stored in an array of size n, then while so I is the position we originally want to update, so while I is less than n, we're going to add x to the tree at position I and add on the value of the least significant bit of I. And that's it, where the function LSB is the least significant bit of I. And there are built-in functions to do that usually. And we're going to have a look at some source code. Alright, so that was point updates, and now we actually need to construct the Fenwick tree. Let's talk about Fenwick tree construction. We've already seen how to do range queries and point updates in the last 2 videos, but we haven't even seen how to construct the Fenwick tree yet. And the reason I've kept this for last is you can't understand the Fenwick tree construction without having previously understood how point updates work. Alright, so let's dive right in. So we could do the naive construction of a Fenwick tree. So if we're given an array of values A, and we want to transform this into a Fenwick tree, what we could do is initialize our Fenwick tree to be an array containing all zeros and add the values into the Fenwick tree one at a time using point updates to get a total time complexity of order n log n. However, we can do better. We can actually do this in linear time, so why bother with n log n? Alright, so in the linear construction, we're going to be given an array of values we wish to convert into the Fenwick tree, a legitimate Fenwick tree, not just the array of values themselves. And the idea is we're going to propagate the values throughout our Fenwick tree in place. And we're going to do this by updating the immediate cell that is responsible for us. Eventually, as we pass through the entire tree, everyone's going to be updated and we're going to have a fully functional Fenwick tree at the end of the day. So it kind of relies on this cascading idea. So you propagate something to the parent who's responsible for you, and then that parent propagate its value to its parent, and so on. So it's just kind of like almost delegating the value. So let's see how this works. Oh, one more thing before that. So if the current position is position I, then the immediate cell above us, which is responsible for us, so our parent, let's say that is J. And J is given by I plus the least significant bit of I. Alright? So if we start at 1, well, the least significant bit of 1 is 1, so the parent is at position 2. So notice that there was a 4 at position 2, but we're going to add to 4 the value at I, which is 3. So now position 2 has a value of 7. Now we want to update position 2. So find out which is responsible for position 2. So 2 plus the least significant bit of 2 is 4. So 4 is actually responsible for 2, or is immediately responsible for 2. So go to index 4 and add the 7. Then who's responsible for 3? Well, that's 4. So go to position 4 and add the value at index 3. Now, who's responsible for 4? Well, 8 is responsible for 4. So go to position 8 and add the value of 4. So now in position 8 we have 4. So now we're at 5, and then you see how we keep doing this, just updating our parent, the immediate cell responsible for us. So now 7 is updating 8. But now nobody, well, 8 doesn't have a parent because our Fenwick tree is too small. It only has 12 cells. But the parent that would be responsible for 8 is 16, and 16 is out of bounds, so we just ignore it. It's not relevant. So now we keep going. So I is 9, 9's least significant bit is 1, so J is 10, that's where the parent is. So keep propagating that value. 10's parent is 12, 11's parent also 12, and now we have the same sort of situation we had with 8, where we have an out of bounds situation, so we ignore it. So the values that are there right now are the values of the Fenwick tree. And with these values, we can do range queries and point updates, not with the original array that we had. So let's look at the construction algorithm itself in case you want to implement this. We will have a look at some source code in the next video, but if you're using another language that I'm not using, this could be helpful. So given an array of values we want to turn into a Fenwick tree, let's get the length, which is n, and I recommend you actually clone or make a deep copy of the values just so that you don't accidentally manipulate the values array while you're constructing your Fenwick tree. That could be problematic because we're doing all this stuff in place. So clone the values array and then start I at 1 and go up to n, and then compute j, so the parent, so which is I plus the least significant bit of I. Do an if statement to check if j is less than n. That might actually be less than or equal to n, actually, now I'm thinking about it, because everything is 1 based in a Fenwick tree. Yeah, I'm pretty sure that should be less than or equal to. Alright, let's have a look at some Fenwick tree source code. I'm here in my GitHub repository. You can find it at this link, which I'll put in the description below, at williamfize/data-structures. And the Fenwick tree source code is right here under the Fenwick tree folder. So let's dive right in. I have it here local on my computer in my text editor. Alright, so this source code is provided to you in Java, but it's really easy to translate it to any language you're working in. So I create a Fenwick tree class which has two constructors. One that will create an empty Fenwick tree for a given size and then you populate it yourself. And another one which you give it an array of values like we saw in the last video and constructs the Fenwick tree in a linear time. So this is probably the constructor you want to use and not the other one, but I give you the option to use either or. So one thing that you guys should know is that the values array that you pass in, this thing needs to be 1 based. In the last video I was hesitant on whether or not you had to go less than or equal to the length of the array, and that's going to depend on whether your array is 1 based or 0 based. Usually everything in a Fenwick tree is 1 based, in which case it would be less than if you're using this as a length. Alright, but other than that, so this is just the construction algorithm we saw. So just propagate the value to the parent, so that's right here, and ignore it if it's out of bounds. So pretty simple stuff. So this is probably one of the most interesting methods. It's the least significant bit method, and it's going to return the value of the least significant bit for some integer I. So this bit magic right here essentially isolates and returns the least significant bit value. Something that's a bit more readable is this right here, which uses Java's built-in method to find the least significant bit. However, using a raw bit manipulation like this without an additional function call will be faster. Okay, so the prefix sums, this is something we covered in the first video, which allows you to compute the prefix sum from 1 to I, both inclusive. And all this is being done 1 based. So this would do the cascading down that we talked about. So start with a sum equal to 0 and add the values at the indices you hit along the way while you're cascading down. And this line 55, is equivalent to I minus equal the least significant bit of I, which is a lot more readable than this crazy bit manipulation, which essentially just clears that bit. But you want to use as much bit manipulation as you can to keep your Fenwick tree fast, even though it's already really fast. But the more bit manipulation you use, the less operation or machine level operations you're going to do, and so your program is going to be so much faster. Okay, if you want to find the sum between I and j inclusive, then we can call the prefix sum method right here and just essentially get the differences. So that's easy. So adding, so this is if you want to do a point update. At position I and add k to it. So k can be positive or negative, that doesn't really matter. So what you're going to do is, for I, you're going to update everyone who's responsible for you. So all the ranges that are responsible for you. And for each of those, you're going to add the constant k. And then you're going to propagate up to your parent by saying I equals I plus the least significant bit, and you're going to do that until you're still within the tree at some valid index. And this additional method I added for fun is if you want to set the index I to be equal to k. This might sometimes be useful, so just get the value at I, so I to I, and then call the add method. So pretty simple stuff. Now as you see, this is what 80-ish lines, and half of it is comments. So this is a really simple and yet extremely fast data structure. An interesting topic I want to talk about today is the suffix array. This is an incredibly powerful data structure to have in your toolbox when you're doing some string processing. Suffix arrays are a relatively new data structure, appearing around the early 90s due to the heavy memory consumption needs of suffix trees. Let's start with the basics and talk about just what a suffix is. For our purposes, a suffix is a non-empty substring at the end of a string. For example, if we ask ourselves what all the possible suffixes of the string horse are, we are able to come up with 5 unique suffixes. And they are E, SE, RSE, and so on. Now we can answer the question, what is a suffix array? The answer is a suffix array is the array containing all the sorted suffixes of a string. Let's see an example of this. Suppose you want to find the suffix array for the word camel. On the left, I constructed a table with all the suffixes of camel and the indices of where that particular suffix started in the string camel. Then, on the right-hand side, I sorted all the suffixes in lexicographic order in a table. The actual suffix array is the array of sorted indices highlighted in orange. We do not need to actually store the suffixes themselves if we know where the suffix begins in the original string. This is an ingenious idea, and it provides us with a compressed representation of the sorted suffixes without actually needing to physically store the suffixes themselves. All we need is the original string and the array of associated indices. In summary, a suffix array is an array of indices which store the sorted suffixes of a string. Furthermore, for a bit of history on the suffix array, it is a data structure originally designed to be a space-efficient alternative to a suffix tree, which in turn is itself meant to be a compressed version of another data structure called a trie. As a side note, even though the suffix array is very different from the suffix tree, suffix arrays can do just about virtually anything the suffix tree can, with some additional auxiliary information such as a longest common prefix array, which will be the topic of our next video. In this video, we're going to talk about perhaps the most important piece of information associated with the suffix array, and that is the longest common prefix array, also known as the LCP array. The LCP array is an array where each index stores how many characters two sorted suffixes have in common with each other. Let's have a closer look. Perhaps the best way to show what the LCP array is to do an example. In the following example, we'll find what the LCP array is for the string ABABBAB. The first thing we'll want to do is construct the suffix array for our string to find out what all the sorted suffixes are. Notice that the very first entry that we placed in our LCP array that is, the middle column, is 0. This is because this index is undefined, so we'll ignore it for now. To begin constructing our LCP array, let's begin by looking at the first two suffixes and seeing how many characters they have in common with each other. We notice that this is 2, so we place 2 in the first index of our LCP array. Now we move on to the next two suffixes. Notice that they also have an LCP value of 2. And the next two don't have anything in common, so we place a 0. And the next two only have 1 character in common, then 3 characters in common, and lastly, only 1 character in common. So the result is the following LCP array, highlighted in purple. In summary, the LCP array is an array which tracks how many characters two sorted suffixes have in common with each other. Although very simple, you'd be surprised how much information can be derived from such a simple construction. Another thing worth noting is that the very first index in our LCP array was undefined. Since we store the LCP array as an integer array by convention, we usually set this first index to be 0 so that it doesn't interfere with any operations we might want to perform on the LCP array, and this is fine for most purposes. Lastly, we saw what the LCP array was, but not how to construct it very efficiently. There are other algorithms than the one I showed you to construct the LCP array, which run in a much better time complexity. That is, in n log n time and even in linear time. In this video, I want to discuss a neat application of suffix arrays and LCP arrays, and that is finding and counting unique substrings. There are a variety of interesting problems in computer science, especially bioinformatics, that require you to find all the unique substrings of a string. The naive algorithm has a terrible time complexity of n squared, which requires a lot of space. The idea is to generate all the substrings of the string and dump them inside a set. A superior approach is to use the information stored inside the LCP array. This provides not only a quick, but also a space-efficient solution. I'm not saying that this is the canonical way of finding all unique substrings, because there exist other notable algorithms, such as Rabin-Karp in combination with Bloom filters. Let's now look at an example of how to find unique substrings. Let's now look at an example of how to find all the unique substrings of the string AZAZA. For every string, there are exactly n times n plus 1 over 2 substrings. The proof of this I will leave as an exercise to the listener, but it's really not that hard to derive. Now notice that all the substrings here, there are a few duplicate ones. I have highlighted the repeated substrings. There are exactly 6 of them and 9 unique ones. Now let's use the information inside the LCP array to figure out which of those substrings really were the duplicate ones. In the table on the right, I generated the LCP array for the string AZAZA. Remember what the LCP array represents. It represents that two adjacent suffixes of the original string share a certain amount of characters with each other. So, if the LCP value at a certain index is, say, 5, then there are 5 characters in common between those two suffixes. In other words, there are 5 repeated substrings between those two suffixes, since they come from the same larger string. So if we inspect the first LCP position at index 1, we see that it has a value of 1. We know that the repeated string is the first character, being A. So we know that A is a repeated substring. The next LCP value is 3, so there are 3 repeated substrings between AZA and AZAZA, namely A, AZ, and AZA. The next interesting LCP value is 2 for the last 2 suffixes, so there are 2 repeated substrings here we can eliminate, Z and ZA. We can then come up with an interesting way of counting all unique substrings. We know how many substrings there are, and that is n times n plus 1 over 2, and we also know the number of duplicate strings, that is the sum of all the LCP values. If this doesn't make immediate sense, try out a few examples and play around with it. If we go back to the example we just did with the string AZAZA and we set n equal to 5, which is the length of the string, then we can get the correct answer of 9 by punching n equals 5 and then removing all the repeated substring values summed up in the LCP array. Alright, so if you're looking for a programming challenge concerning counting substrings, like I mentioned here, check out the link to the Caddis Online Judge for some practice. I also included some source code for the suffix array and LCP array available on GitHub at github.com/williamfizet/data-structures. There is a really neat problem called the longest common substring problem, or its generalization, the k-common substring problem, which is really what I want to focus on today. First, let's state the problem and then discuss multiple ways of solving it. Suppose we have n strings. How do we find the longest common substring shared between at least k of them, with k being anywhere from 2 to n, the number of strings? As an example, consider the 3 strings S1, S2, and S3 with the value of k equal to 2, meaning that we want a minimum of 2 strings from our pool of 3 strings to share the longest common substring between them. In this situation, the longest common substring is BCA, but note that the longest common substring is not required to be unique because there can be multiple. The traditional approach to solving this problem is to employ a technique called dynamic programming, which can solve the problem in a time complexity equal to the product of the string lengths. Obviously, this method can get unwieldy very quickly, and you should avoid using it whenever possible. A far superior approach, and the way to solve this problem, is to use a suffix array, which can find the solution in linear time proportional to the sum of the string lengths. So, how do we do this? How do we use a suffix array to solve the longest common substring problem? Let's consider the 3 strings we saw earlier, S1, S2, and S3. What we will first want to do is concatenate them all together into a larger string, which I will call T, which is short for text. However, when doing this, we must be careful and place unique sentinel values between our strings. We need to do this for multiple reasons, but the main one being that we must avoid any intermingling of suffixes when we construct the suffix array. Additionally, I would like to note that these sentinel values need to be lexicographically less than any of the characters contained in any of our strings. So in the ASCII table, the pound sign, the dollar sign, and the percent sign are all less than any alphabetic character contained within S1, S2, and S3, so we're good in doing the concatenation. Once we have the string T, we are able to construct the suffix array for T. This procedure can be accomplished in linear time with a linear suffix array construction algorithm. You will notice that On this slide, I am displaying both the LCP array values on the leftmost column and the sorted suffixes of T as they would appear in the suffix array on the right column. I also gave each suffix a certain color to match it with the original string it belongs to. In this slide, you can see that the suffixes starting with sentinel values got sorted to the top because they were lexicographically less than all the characters in the string, and this is to be expected. For our purposes, we want to ignore them because we injected them into the string T ourselves. So back to the central problem. How do we find the longest common substring of K strings, given that we now have the suffix array and the LCP array constructed? The answer is we're going to look for K strings, each of different colors whom share the largest LCP value. Let's do an example with K equals 3. Since K equals 3 and we have 3 strings, this means that we need 1 string of each color. We can achieve a maximum of 2 if we select the following 3 adjacent suffixes. Notice that each of them is a different color, meaning that they came from different original strings, and that the minimum LCP value in the selected window is 2. Note that we must ignore the first entry in the window. This means that the longest common substring solution is the string CA of length 2, which is shared amongst all 3 of S1, S2, and S3. Let's do another example, but this time let's change the value of K to be equal to 2. Since K equals 2, we want to have 2 suffixes of different colors and the maximum longest common prefix value between them. In this case, there is a unique solution, which is the string BCA, with a length of 3 shared between S1 and S2, but not S3. So far, we've covered only some trivial cases. Things get much messier when not all the different colors you need are exactly adjacent with each other. A trick we will use to overcome this will be to use a sliding window technique to capture the correct amount of suffix colors. Here's what we'll do. At each step, we'll adjust the bottom or the top endpoint so that the window contains exactly K suffixes of different colors. Once we have a valid window with the correct amount of colors, we'll want to query the minimum LCP value for that window range. In the picture below, you can see that this value is 2 because the minimum value in the LCP array for that window is 2. Again, ignore the first entry, which is 5. Since the minimum value for that window is 2, all the suffixes in that window do share the prefix AG, which has length of 2, as we would expect. Here are some more details on how we are actually going to perform the query to obtain the minimum LCP value on the current window we are considering. Turns out that this is a pretty popular problem and it can be solved in a variety of ways. Since we're dealing with a sliding window and not just any arbitrary range query, we can use a linear solution from the minimum sliding range query problem to obtain the value we want. Alternatively, I would recommend using a minimum range query data structure, such as a segment tree, to perform logarithmic range queries on the LCP array. This is theoretically a little slower, but it is much easier to implement, in my opinion. So to implement the sliding window, we will also need an additional data structure to keep track of the colors in our window. I recommend using a hash table for this task. On the bottom left, I drew a table to indicate how much of each color we are capturing in the current window. A valid window will require at least K or more columns to have a value greater than 0. In the example that will follow, let's suppose that k equals 3, meaning all 3 colors will need to be present in our window for a valid query to occur. By a query, I mean querying the LCP array for the minimum value in the current window, and then possibly updating the best longest common substring value found so far. Right now, you can see that our window is missing some blue. So our rule when we're missing a certain color is to expand the window down, and when we already meet the criteria, we shrink the window down. So let's expand our window downwards to capture some blue. Now we have enough blue and enough of each color to do a valid query. When we perform the query, we would see that the longest common substring for the window we are in will have length 3, representing the string AAG. Now, since we have enough of each color, we can then reduce the window size. I removed one green suffix, and we still have at least one of each color, so we can again perform a query to find out that we get the same result as last time. Now I shrank the window even more, and now we don't have enough green, so we cannot perform a valid query here. What we need to do is expand the window downwards until we hit a green suffix. Luckily, there was a green suffix right there, and we can perform a query to attempt to update the best longest common substring value found so far. In this window, the longest common substring is only of length 1, so the longest common substring for this window is the string A, which is not as long as the longest common substring we found before, which was AAG of length 3, so we can ignore this one and keep searching. Now we shrink the interval and we're short one color, and that is red. Let's expand downwards until we reach a red suffix. So we expand and find a blue suffix. This is not what we wanted, so let's keep searching. Then expand and find a green suffix, and keep doing this until a red suffix is reached. This video is getting a little long, so I'm going to break it up here, and in the next video we'll look at a full example of this method being applied. However, in the meantime, if you're looking for a challenge regarding the longest common substring problem, make sure to check out the Lifeforms problem on the Caddis website. And if you're looking for an implementation of the longest common substring algorithm as I just described, make sure to check out my algorithms repository at github.com/williamfizet/algorithms. We're going to finish where we left off in the last video. In this video, I want to do a full example solving the longest common substring problem with a suffix array. For this example, we're going to have 4 strings, S1, S2, S3, and S4. I have also selected the value of k to be equal to 2, meaning that we want a minimum of 2 strings of our pool of 4 to share the longest common substring between them. I have also provided you with a concatenated text we'll be working with, as well as the solution at the bottom of the screen in case you want to pause the video and figure it out for yourself. The first step in finding the longest common substring between a set of our 4 strings is to build the suffix array and the LCP array, which I have displayed on the right side and the left side respectively. While I will be conducting the longest common substring algorithm, notice the variables on the left as they change. The window LCP and the window LCS values will track the longest common prefix and the longest common substring values for the current window, and the LCS length and the LCS set will track the best values so far. So let's get started. Initially, our window starts at the top, and we want the window to contain 2 different colors So our rule is to expand downwards when we do not meet this criteria. As I expand down, the suffix is green, so we still only have one color. I expand down again and still one more green suffix. I expand downwards again and now we arrive at a blue suffix. And here we are able to perform a range query for our window. However, our query isn't fruitful because the window longest common prefix value is 0. So there's no longest common substring here. When we satisfy the window color criteria like we do now, we decrease the window size. I decrease the window size by 1 and still nothing interesting. I decrease the window size again, and this time look what we found. The current window contains a longest common prefix length of 2, so we obtain the longest common substring BC and add it to our solution set. Now we keep shrinking the interval size because we meet the color requirement. Our window size is now too small because K is 2, so we need 2 different color strings, so we expand once more. Now something interesting has happened because we find an LCP value of 3 which is larger than our current best value, so we update the solution set to have the string BCD instead of just BC, which is 1 character longer. Now we get to shrink the window size. The window is now too small, so we expand the LCP value of 0 here, so that is no good. So shrink the window size. Now expand to meet the color requirement. We get an LCP value of 1, but that doesn't beat our current best, which is 3. So shrink the window. Now we need to meet the color requirement, so expand. We have only blue strings, so keep expanding. An LCP value of 1 for this window range. So that's no good, so shrink. Now we have an LCP value of 2. We're getting closer to our best, but still not good enough, so we have to shrink and let it go. Now expand. Now something interesting is going on here. We have a window LCP value of 3, which is equal to our best so far. So instead of saying that CDE, our newfound longest common substring value, beats BCD, which is of the same length, we keep both in the solution set. Alright, so now let's shrink our window interval because we meet the color requirement. Now expand it. We still need one more color. Expand again. Our LCP window value is 0. So shrink and shrink again. Now expand. LCP value of 1 here. That's not good enough. So smaller. Expand. LCP value of 2. Okay, we might be getting closer, but we meet the color requirement, so shrink. Now expand to meet the color requirement. These two strings have an LCP value of 0. So shrink. Now expand. Now shrink. Now we've reached the end and found our solution to the longest common substring problem with 4 strings and a K value of 2. As I was doing the window expanding and shrinking, I wanted you to notice that each time the window either expanded or shrank, I only ever moved one of the endpoints downwards, and they were always going downwards. So we know that the number of windows has to be linear in proportion to the number of suffixes that we have. And the number of suffixes that we have is the length of our text, T. So we come to the conclusion that there must be a linear amount of windows that we must consider, which is really good because we want our time complexity be quick. Today's topic is going to be on an efficient way to solve the longest repeated substring problem. The longest repeated substring problem is another one of these fairly common problems in computer science. Lots of problems can actually be reduced to this problem, so it's important that we have an efficient way of solving it. The naive approach requires n² time and lots of space. What we want to do instead is use the information stored inside the longest common prefix array to yield a faster and also space-efficient solution. Let's do an example. What is the longest repeated substring of the string abracadabra? Feel free to pause the video and figure it out yourself. The answer is the substring abra, which is the longest substring that appears at least twice in the string, so we call it the longest repeated substring. Here you can see the first instance of abra on the left. And now you can see the second repeated instance of abra on the right. Although these substrings are disjoint and do not overlap, in general, this is permitted for the longest repeated substring. Now let's solve the problem using a suffix array and an LCP array, which I have generated on the right hand side. I'll give you a moment to pause the video and inspect the LCP array in case you notice anything special in relation to the longest repeated substring, now that you already know what the answer is. Effectively, what we're looking for in the LCP array is the maximum value. Intuitively, we want to do this because we know that the suffixes are already sorted. So if two adjacent suffixes have a large longest common prefix value, then they share a good amount of characters with each other. We also know that if the LCP value at a certain index is greater than 0, then the string shared between the two adjacent suffixes is guaranteed to be repeated because it is common between two suffixes, each of which start at different locations in the string. So here again is abracadabra. Since our LCP value was 4, we know that the first 4 characters from the suffix abracadabra forms one part of the repeated substring. Next, we know that the suffix above it, which shares the LCP value of 4, also shares 4 characters present in that longest repeated substring. Now I want to look at another interesting case. Can you find the longest repeated substring of the string ABABBAABAA? Well, if you did, you would find out that you not only got one longest repeated substring, but 2 longest repeated substrings, since there can be ties. In a case like this, you're not looking for a single largest value, but all largest values that might exist. For the first maximum, you can see that we'll want the first 3 characters from the suffix ABABBAABAA, and for the second maximum, we'll want the first 3 characters from the suffix BAABAA. Visually, for this first longest repeated substring, we have ABA, which appears at the start, and then ABA again closer to the end. The other repeated substring is found using the second largest common prefix value, and its first occurrence is found here, and the second one just next to it. That is all for repeated substrings. Pretty easy once the suffix array and the LCP array have already been constructed. Here is a practice problem on Caddis if you want to tackle a longest repeated substring problem which requires you to have an efficient solution. Today I'm going to introduce probably one of the most important types of trees in computer science, which are balanced binary search trees. Balanced binary search trees are very different from the traditional binary search tree because they not only conform to the binary search tree invariant, but they are also balanced. What I mean by balanced is that they are self-adjusting to maintain a logarithmic height in proportion to the number of nodes they hold. This is very important because it keeps operations such as insertion and deletion extremely fast, because the tree is much more squashed. In terms of complexity, a binary search tree has average logarithmic operations, which is quite good. However, the worst case still remains linear because the tree could degrade into a chain for some inputs. One such input is a sequence of increasing numbers. To avoid this linear complexity, we've invented balanced binary search trees in which the worst case is logarithmic for all operations, which makes them very appealing. Central to how nearly all balanced binary search tree implementations keep themselves balanced is the concept of tree rotations, which is going to be the main topic of this video. Later, we'll actually look at some specific types of balanced binary search trees to see how these rotations come into play. So, the secret ingredient to most balanced binary search tree implementations is the combination of two things. One, a clever tree invariant, and tree rotations. A tree invariant is simply a property or a rule that you impose on your tree, such that it must be met at the end of every operation. To ensure that the invariant is always satisfied, a series of tree rotations are normally applied. We'll get back to this concept of invariants in a later video, so don't worry about them so much for now. Right now we're going to look at how tree rotations work. Suppose our invariant is not satisfied, and to fix it we need to do a right rotation about node A. Assuming node A has a left child B, we can perform a right rotation to put B where node A was and push node A down to become B's right child. When I first learned about this in my undergrad, I was mind blown, literally. I thought it was absurd, or even to the point of being illegal, that we should be allowed to do this and just move around nodes in a tree. But what I've realized since is that a transformation like this is totally legitimate, since we're not breaking the binary search tree invariant in any way. If you inspect the left tree, you'll discover that in terms of ordering and placement, node D is less than node B is less than E is less than A is less than C. Then you inspect the right tree and remark that, well, this is also true. A bit more detail on why performing tree rotations is a valid operation. First, you have to remember that all balanced binary search trees are binary search trees, meaning that the binary search tree invariant holds. So for every node n, the values in the left subtree are less than the value of n, and the values in the right subtree are all greater than the value of n. So in this sense, it doesn't matter what the tree structure itself looks like. All that fundamentally matters is that the binary search tree invariant holds. This means we are free to shuffle, transform, or even rotate the values and nodes in our tree as we please, as long as the binary search tree invariant remains satisfied. Now let's look at how these rotations are done in great detail. For simplicity, since the rotations are symmetric, I will only do the right rotation, and you should be able to figure out the left rotation on your own. First, have a look at the tree on the right. Notice that there are directed edges pointing downwards, and another node P above A, which may or may not exist. This is why there is a dotted line on that edge. If node A does have a parent node P, then it is important that we take it into account when doing the rotation. In either case, we start with a pointer reference to node A. This is the orange arrow. Then we'll want a pointer to node B. After that, set A's left pointer to point to B's right child. Then change B's right pointer to point to node A, and we've successfully done a right rotation. If we rearrange the nodes, this is what we would end up with. However, notice that there's a slight problem. If node A had a parent node, then either the parent's left or right pointer would still be referencing A. This is problematic since B is A's successor after the rotation. So we change the link to now point to B. This step is usually done on the recursive callback using the return value of the right rotate function. We just finished looking at the case where each node has a reference to the left and the right child nodes. But in some balanced binary search tree implementations, it's more convenient for nodes to also have a reference to the parent node. This complicates tree rotations because now, instead of updating 3 pointers, we need to update 6 pointers. Let's have a look. In this case, where we also have a parent link, every node is, in a sense, doubly linked. We start off with a pointer referencing A, and the first thing we'll want to do is also reference node B and node P, so we don't lose them as we shuffle around pointers. Next, we'll adjust the left subtree of A to make A's left pointer reference B's right subtree. Of course, throughout this example, assume B is not null. If you're paranoid, you can add an extra if statement to check for this condition. However, it would be a mistake to assume B's right subtree is not null. We actually have to check against this before setting B's right child's parent to reference A. Next, let's make A the right subtree of B, so set B's right pointer to reference A. Now make A's parent pointer reference B. The last thing we need to do is adjust the reference to the parent node P, so make B's parent pointer reference P. And now the very last thing I promise is to make P's left or right pointer reference the successor node B. Notice that we need to check if P is not null because it might not exist. This would be the case for the root node. If we readjust the tree, you will see that we correctly did a right rotation. There are a lot of steps in doing this right rotation, and it's a very error-prone process, which is why I wanted to do it in such detail. Today we're going to look at how to insert nodes into an AVL tree in great detail. We'll be making use of the tree rotation technique we looked at in the last video, so if you didn't watch that, simply roll back one video. Alright, before we get too far, I should mention what an AVL tree is. An AVL tree is one of many types of balanced binary search trees, which allow for logarithmic insertion, deletion, and search operations. Something really special about the AVL tree is that it was the first type of balanced binary search tree to be discovered. Then, soon after, a whole bunch of other types of balanced binary search trees started to emerge, including the 2-3 tree, the AA tree, the scapegoat tree, and the AVL tree's main rival, the red-black tree. What you need to know about next is the property that keeps the AVL tree balanced, and this is the balance factor. Simply put, the balance factor of a node is the difference between the height of the right subtree and the left subtree. I'm pretty sure the balance factor can also be defined as the left subtree height minus the right subtree height, but don't quote me on this. It would also screw up a lot of what I'm about to say, and may also be the reason why you find many inconsistent ideas about what way to do tree rotations on various Google search results pages. So for consistency, let's keep the balance factor right subtree height minus left subtree height. For clarity, because people get this wrong or define it differently, the height of node x is calculated as the number of edges between x and the furthest leaf. So if your tree only has one node, the tree has height 0, not height 1, because there are no edges. The invariant on the AVL tree that keeps it balanced is forcing the balance factor of every node to be either -1, 0, or +1. If the balance factor of a node is anything else, we need to resolve that with tree rotations. In terms of information we need to store in each node to actually make the AVL tree work, what we'll need is the actual value the node stores. This value must be comparable so we know how to insert it and in what position it goes in the tree. Then we'll also need the balance factor and height of the node as well as the left and the right child pointers. As the algorithm executes, we'll need to update these values, so keep that in mind. So a slide or so back, I said that the balance factor of a node must always be -1, 0, or +1. A natural question to ask is, how do we handle the case where this is not true? The answer is that if this is not true, then the balance factor must either be +2 or -2, which we can easily handle with tree rotations. The rotations we need to perform, depending on the structure of the tree, can be broken down into 4 distinct cases. The first such case is when the tree is what we call left heavy, and there are 2 left child nodes. This is an easy case to fix because all we need to do is perform a right rotation about the yellow node to balance. The next case is the left-right case, where you have a left child, but then that node has a right child. To fix this, you do a left rotation about the left child, so the green one on the leftmost image. What happens then is that this transforms into the left-left case we just saw, which we can resolve with a right rotation to balance. The third case is the right-right case, which is symmetric to the left-left case. So instead of doing a right rotation, we do a left rotation about the green node. Last but not least is the right-left case, which is symmetric to the left-right case. For this case, you would perform a right rotation about the yellow node on the leftmost image to transform this case into the right-right case, and then do a left rotation about the green node in the middle image. Next, I want to show you some pseudocode for inserting nodes into an AVL tree because it's not all that obvious or easy. This first method is the public-facing method for the insert method, which returns true or false depending on whether the value was successfully inserted or not. For simplicity, we're going to ban duplicate values in our AVL tree. So if the value already exists or the value is null, this method would return false. If the node is not null and it doesn't already exist in the tree, we call our private recursive insert method, where we pass in a pointer to the root node and the value we want to insert. The private recursive method is also simple. If we hit the base case, a null node, we simply return a new instance of the node with the value we want to insert. Otherwise, we get the comparator value with the value we're trying to insert against the current node to determine if we should go in the left or the right subtree. After that, on the recursive callback, we call the update method, which updates the balance factor and height values for this node. And lastly, we rebalance the tree with the balance method. Now, let's take a look at the update and balance method and what they're actually doing. The update method updates the balance factor and height values of our node. So to calculate the height of the node, we get the maximum height of the left and the right subtrees and then add 1. Notice that I initialize the left and the right subtree heights to be -1. This is because it will cancel out with a +1 with a max function in the case where the node has no subtrees, giving the correct height of 0 for leaf nodes. Lastly, I update the balance factor for this node by finding the difference between the right subtree and the left subtree heights. The balance method is slightly more involved, but not too crazy. Here we check if our balance factor has an illegal value of -2 or +2. If the balance factor is a -2, then we know that the node is left heavy. Then we dig further into the left subtree to determine if we're dealing with a left-left case or a left-right case. We do a similar thing if the balance factor is +2, except we're dealing with the right-right or the right-left case. If the balance factor is not +2 or -2, then we know that the balance factor is going to be either +1, 0, or -1, and in either of those cases, we don't need to do anything. Inside the 4 cases we might run into, notice that all we do here are calls to the left rotation and right rotation methods that we saw in the last video. Also notice that the left-right and right-left cases call the left-left and right-right case methods respectively, since they reduce to those cases after a first rotation. In the last video, we looked at this right rotation method, but since we're dealing with an AVL tree in this video, we actually need to augment that method to update the height and balance factor values for the nodes we're moving around when we do rotations. This is a subtle detail you must not forget, otherwise your height and balance factor values will be inconsistent. The left rotation case is symmetric to this one, so you should be able to figure it out pretty easily. In this video, we're going to look at how to remove elements from an AVL tree. And what you'll discover is that removing elements from an AVL tree is almost identical to removing elements from a regular binary search tree. So for the majority of this video, we're going to actually be looking at how to remove elements from a binary search tree and at the very end augment that algorithm for AVL trees specifically. So let's get started. So just for review, I want to look at how to remove nodes in a binary search tree in detail. So we can generally break it up into 2 steps, finding and replacing. In the find phase, you find the element you want to remove from the tree, if it exists, and then replace it with a successor node. The successor node is necessary for us to maintain the binary search tree invariant. More details on the find phase. This is when we're searching for the element in the tree to see if it exists, and basically 4 things can happen. First is we hit a null node, in which case we know that the value we're looking for doesn't exist. Our comparator returns a value of 0, meaning we found the node we want to remove. The comparator value is less than 0, so the value we're looking for, if it exists, is going to be found in the left subtree, or the comparator value is greater than 0, in which case the value, if it exists, is in the right subtree. So let's do an example of finding nodes in a binary search tree. Suppose we're looking for 14. Well, we should have a reference to the root node, so this is where we start. So we compare 20 and 14, and we know 14 is less than 20, so we go in the left subtree. We know 14 is greater than 10, so we go in the right subtree. We know 14 is less than 15, so we go in the left subtree. 14 is greater than 12, so the right subtree. And finally there, we found it, the node we were looking for. Now let's see what happens with a node that doesn't exist. So let's try and find 26. So again, we start at the root node, then we go to the right subtree because 26 is greater than 20. Then we go to the left subtree because 26 is less than 31. Then once we're at 25, we would go to the right subtree and then discover that 26 does not exist in the tree. So once we find the node, assuming it exists, we need to replace that node with its successor. The motivation for this is that if we just remove the node without finding a successor, then there'd be a gap in the tree. And when we're looking for a successor node, one of four cases will happen. Either we're a leaf node, in which case there are no subtrees. The node to remove has no left subtree, the node to remove has no right subtree, or the node to remove has both a left subtree and a right subtree. We'll see how to handle all these cases. In the first case, where the node to remove is a leaf node, we can simply remove it without any side effects. The successor node in this case would be simply a null node. So suppose we want to remove node 8 from this tree. The first thing we'd do is find out where 8 is in the tree. So we'd go down the tree and then we'd find node 8. Then we discover that, oh, it's a leaf node, so we can just remove it, like so. Alright, now for cases 2 and 3, where there's only a left or a right subtree, in these cases, the successor node is the immediate child of that left or right subtree. The reason the successor is the immediate node down from the node we're removing is that it is the next node which is either greater than it in the case of a right subtree or less than it in the case of a left subtree. Let's do an example. Suppose we want to remove node 9. The first thing we do is find where node 9 is in the tree. So start at the root and go to the right subtree and then find the node we want to remove, which is 9. And then we inspect 9 and discover that it only has a left subtree. So the successor node is its immediate child on the left, so 7. So what we do is we get a reference to 7 and then get ready to remove 9. And then we remove 9 and then make 7 the successor by linking it back up to 5. And if we rebalance the tree, that's what it looks like. And node 9 has been removed. So the last case is when the node we're trying to remove has both a left subtree and a right subtree. So the question in this case is, in which subtree will we find the successor of the node we're trying to remove? And surprisingly, or not surprisingly, the answer is both. The successor can either be the largest value in the left subtree or the smallest value in the right subtree. Once the successor node has been found in either that left or right subtree, we replace the value of the node to remove with a value in the successor node. However, the story doesn't end there. We must not forget to remove the duplicate value of the successor node that still exists in the tree. One common strategy to resolve this is to recursively call the function again, but with the value to remove as the value in the successor node. Let's see an example because this isn't completely trivial. Let's remove node 7 from this tree, which is the root node. So we would start at the root node and discover that in fact, this is the node we want to remove, and notice that it has two non-empty subtrees, so we must choose a successor. To choose a successor, we either pick the smallest value in the right subtree or the largest value in the left subtree. Let's find the smallest value in the right subtree. And to do this, you would go to the right once and then dig as far left as possible. So now that we found the successor node 11, we would copy its value into the node we're trying to remove, which is the root node 7. Notice that now there are two instances of 11 in our tree, and we want unique values in our tree. So to remove the 11 that is currently highlighted, we would recursively call our remove method, but on 11 this time. And luckily for us, this will always result in a case 1, 2, or 3 removal. So to remove 11, we notice that it only has a right subtree, so its successor is its immediate right child. So we stage the removal and get ready to remove 11. Then we remove 11 and then hook 14 back up to 18. And if we rebalance the tree, then we can see that the duplicate 11 value is gone. Alright, the moment we've been waiting for. How do we augment the binary search tree removal algorithm for AVL trees? The solution is simple. You only need to add 2 lines of code to ensure that the tree remains balanced and that the balance factor and height values remain up to date. On the recursive callback, you invoke the update and balance methods you saw in the insert video, which ensure that when the node is removed from the AVL tree, that the tree remains balanced. It's as easy as that. Today we're going to have a look at some of the source code for the AVL tree. The link to the source code I'm going to present in this video can be found on GitHub at github.com/williamfrizzell/data-structures. Make sure you have watched the last 3 videos on the AVL tree about tree rotations, insertions, and removals in AVL trees before continuing so you can understand the source code I'm presenting. I don't normally do this, but I'm going to present a live demo of the AVL tree in action. So I'm here in my GitHub repository. I'm just compiling some of the Java code for the AVL tree, and then I'm going to run it. And you see that it generated a random tree with some values. And notice that the tree is relatively well balanced for the number of nodes that are in it. So I randomly inserted some nodes, and you might expect the tree to be a bit more sloppy if it were just a simple binary search tree, but the AVL tree really keeps the tree quite rigid. So I think we're ready to dive into the source code now. Here we are in the source code of a recursive AVL tree implementation in the Java programming language. So let's get started. If you look at the class definition for the AVL tree, you'll notice that this class takes a generic type argument, which is of type T, which extends a comparable. And this generic type I'm defining basically says that the types of values we're going to be inserting inside the tree need to be comparable in a sense, meaning we need to be able to insert them and know how to insert them. So if you look inside the subclass node, which I've created, you can see that the value we're actually storing inside the node is of type T, so it's a comparable. And that's very important. The other instance variables I'm storing inside the node subclass for this AVL tree is, of course, the balance factor as an integer, the height of the node, because we want to be able to query the height of a node in constant time, so I'm storing it inside every node. And then, of course, there's going to be the left and the right child pointers right here. And notice that this node class implements the tree printable node interface, and that's just an interface I have somewhere in this folder that allows me to display the tree I did on the terminal. So this isn't quite a requirement if you're actually building an AVL tree, and nor are these overrides. Those are also for being able to display the tree in the terminal, which is really handy for debugging actually. All right, so instance variables at the AVL tree class level, we have the root node. This should really be private, although I'm using it for testing, so I'm leaving it package private. I'm also keeping track of the number of nodes inside the tree, inside this node count variable. Something else I'm also using for testing is this height function, although it's really good to just sanity check yourself to make sure that your AVL tree height is relatively low. Then there are these methods like size and isEmpty, which are pretty self-explanatory. This is the display method I call to actually print the tree in the terminal. This is a contains method to check if a certain value already exists inside the tree. So this is the public facing method, which calls the private method, and I give it the root as the initial node to start off with. So to check if a node exists inside a tree, if we hit the base case, then we know that that value does not exist. Otherwise, we compare the current value to the value inside the node. So that returns a comparator value of either a value less than 0, which means that if the value does exist, it'll be found in the left subtree, or comparator is greater than 0, meaning the value, if it exists, is in the right subtree. Otherwise, that means that the comparator value is equal to 0, and that means we found the node inside the tree, so we can return true. So we're trying to insert this value variable. If it's null, we don't want anything to do with it, so we just return false. And we return a Boolean for the insert method to indicate whether an insertion was successful or not. So if the value does not already exist inside the tree, then we're going to call the private insert method and then assign its value to the root and also increment the node count, because we know we're going to successfully insert something if we're inside this block. And at the same time, we're going to return true. All right, let's have a look at the private insert method. So if we reach the base case, meaning we traverse all the way down our tree and the value of node is null, then we know this is the position where we need to insert that new node. So create a new node and give it the value. Otherwise, we're searching for the insertion position. So again, invoke the comparator function, then do value.compareTo node.value. This .compareTo comes from the comparable interface at the class level. So that's why we're allowed to invoke .compareTo on a generic type here and another generic type there. So again, if comparator is less than 0, then insert in the left subtree. Otherwise, insert in the right subtree. And here is the extra 2 lines you need to add for the AVL tree, which is calling the update method to update the balance factor and the height value for this node, and also rebalance the tree if necessary. Well, rebalance the tree at this node. All right, so let's look at the update method. So this is to update the balance factor and height of a node. So here are 2 variables that grab the height of the left subtree and the right subtree. Then I update the height for this node. So that's always 1 plus the maximum of either the left subtree or the right subtree height. Then once we have the appropriate values for left and right, we can, of course, update the balance factor, which is the difference between the right and the left subtree heights. Okay, so we've done the update. Now we can call the balance method. And inside the balance method, we're looking to readjust nodes whose balance factors are either -2 or +2. In the case of a -2, this means that our tree is left heavy. And inside the left heavy case, we can run into the left case or the left right case. And inside the right heavy case, we have the right case and the right left case. And to identify those subcases, you just check the balance factor, but on either node.left or node.right, respectively. And if the balance factor of the node is not -2 or +2, then we know that the balance factor is either 0, +1, or -1, which is fine, and we don't have to touch anything. We don't have to rebalance the tree if either one of these is true. So we just simply return the node. So now we can look at the individual cases themselves. So like the left-left case will just perform a right rotation. The left-right case will do an initial left rotation and then call the left-left case. So we're reusing methods we already wrote here, since this case degrades to that case after one rotation. And a similar thing happens for the right-right case and the right-left case. We get to call the right-right case after one right rotation over here. Then here are the notorious left rotation and right rotation methods. For the AVL tree, it's very important that we call these two update methods to update the height and balance factor values after that we've rotated about this node, because those values will undoubtedly change. And it's also important that this is the order you do them in. You can't do them in inverse order, because you have to update the child node first to get the correct balance factor and height values for the parent. Okay, now we're at the remove method. So in this remove method, we want to remove this element, or I should have called it value rather, but still. So if the element is null, well, we know it doesn't exist in the tree, so just return false. Otherwise, make sure that value exists in the tree and then remove it by calling the private remove method. Then decrease the node count and simply return true on the remove method to indicate that the removal was successful. So let's look at this private remove method where all the action is happening. So if we hit the base case and just return null, then we get our comparator value, and we do what we always do. We check if the comparator is less than 0, and if so, we dig into the left subtree, and we know that the value we're looking for is smaller than the current value. And then we recursively call the remove method, but passing down node.left. So we're just decreasing the region we're searching, and then pass in the element as well. Otherwise, do the same thing, but for the right. So recurse down the right subtree. Otherwise, if this is not true and that is not true, then we know that the comparator value is equal to 0, meaning we found the node we wanted to remove. And we know from the slides that this is where the 4 cases come up. If node.left is equal to null, then we know that we want to return node.right, or if node.right is null, meaning the right subtree is null, then return node.left. Okay, and then the final tricky case where we're trying to remove a node who still has both subtrees. So the left subtree is there and the right subtree is there, but we still want to remove that node. And we can either pick the smallest value. Well, the successor can either be the smallest value in the right subtree or the largest value in the left subtree. And I'm using a heuristic right here to actually determine which one I want to do, just because I think it's a good heuristic. And here's what it is. If the height of the left subtree is greater, I want to remove nodes from that subtree. But otherwise, if the right subtree has a larger height, then I want to remove nodes from that subtree. So that's the heuristic I'm using to choose which subtree I remove from. And I just made up this heuristic, but I think in general it'll work pretty well. So what we do, let's say there or the left subtree has a larger height, then what I'm going to do is I'm going to find the successor value by going down the left subtree once and then digging all the way to the right to find the max value, and then swapping that value into the current node. And then this is the recursive part. We recurse on removing the successor value instead of the element we passed in, or rather the element we passed in becomes the successor value. So we've removed the element, but now we also have to remove the successor value because we don't want duplicate values inside our tree. Then we basically do the same thing, but on the other side, if the condition goes the other way. Here's what I was mentioning in the last video, where you want to call the update and rebalance method on the callback of this remove method so that the tree remains balanced even though we're removing nodes. And these are the find min and find max method I was calling right up here, which just digs left or digs right depending on the case. And here's just an iterator to traverse the tree. I don't think I need to go over this. And here's another method for testing, which validates the binary search tree invariant, also not particularly important. And this is what I was calling in the main function that will just randomly insert values inside the tree and then display it. So when I invoked this file on the terminal, this is what executed. So that is an AVL tree. It's pretty cool data structure, and I quite enjoyed writing it up. Today's data structure is the indexed priority queue. This is going to prove to be a very useful data structure that you wished you would have known a long time ago. So just before we get started, this video builds off concepts from the previous priority queue videos, which simply go over the basics. Strictly speaking, you can probably get by without watching all those videos, as I'll be doing a quick recap. But for those of you who want to know priority queues in full detail, please check out the description for links to those. So what exactly is an indexed priority queue? Well, it's a traditional priority queue variant which, on top of having all the regular priority queue operations, also supports quick updates and deletions of key value pairs. One of the big problems that the index priority queue solves is being able to quickly look up and dynamically change the values in your priority queue on the fly, which is often very useful. Let's look at an example. Suppose a hospital has a waiting room with n people, which need different levels of attention. Each person in the waiting room has a certain condition that needs to be dealt with. For instance, Mary is in labor, so she has a priority of 9. Akarsh has a paper cut. He has a priority of 1. James has an arrow in his leg. He has a priority of 7. Naida's stomach hurts. She gets a priority of 3. Richard has a fractured wrist, so his priority is 5. And lastly, Leia also has a stomach that hurts. We want to process these patients by highest priority first. This means the hospital would serve Mary first, followed by James. However, then something happens. Suppose Naida's stomach condition worsens and she starts vomiting. Her priority needs to get updated to 6. Because of this, Naida gets served next, once they're finished with James. During this time, Richard gets impatient and leaves. He goes to another clinic down the street, so he no longer needs to be accounted for. Further, suppose that Akarsh goes to take a drink of water, slips on the floor, and as a result cracks his head and needs immediate attention, so we increase his priority to 10. Once Naida is dealt with, Akarsh should be next. And lastly, this is followed by Leia. As we saw in the hospital example, it is very important to be able to dynamically update the priority of certain people. The index priority queue is a data structure which lets us do this efficiently. The first step to using an index priority queue is to assign index values to all the keys, thus forming a bidirectional mapping. If we use an index priority queue to track who should get served next in our hospital, we need to assign each person a unique key index value between 0 and n non-inclusive. Note that this mapping is intended to be bidirectional, so I would advise using a bidirectional hash table to be able to flip back and forth between the key and its key index. Basically, any operation on the index priority queue will require the associated key index of a particular key. So you're probably wondering why I'm saying that we need to map keys to indices in the domain 0 to n non-inclusive. The reason for this is that typically priority queues are implemented as heaps, which under the hood are actually arrays. So we want to facilitate being able to index into those arrays. This will become apparent shortly. I will say though that often, and I mean very often, the keys themselves are already integers in the range 0 to n. So there's no need to actually construct this bidirectional mapping. It's already there implicitly. However, it is handy to be able to support any type of key, such as names or general objects. We can think of an index priority queue as an abstract data type with certain operations we want it to support. Here are about a dozen or so operations we want our index priority queue to support. These are deleting keys, getting the value associated with a key, checking if a key exists in the priority queue, getting the key index with the smallest value, getting the smallest value in the index priority queue, being able to insert and update key value pairs, and finally, the specialized update operations, increase and decrease key, which I'll talk about at the end. For all these operations, you need the key index associated with a particular key that you're dealing with. Throughout these slides, I will be denoting the key index simply as the variable ki to distinguish it from other index values, so keep your eye out for that. An index priority queue can be implemented in several ways. Some ways with really good time complexities using specialized heap structures. However, we're going to cover the binary heap implementation for simplicity. You will notice that the time complexity for all these operations are either constant or logarithmic, which is really good. In a traditional priority queue, the remove and update operations are linear because we are not maintaining a mapping to the position of where our values exist within the heap. Before we dive into the index priority queue per se, I want to spend a few slides giving a refresher on the traditional priority queue data structure, which only supports values, not key value pairs like the index priority queue. Still, both data structures are very similar and most people would consider them the same, although there are key differences in my opinion. Recall that a very common way to represent a binary heap is with an array, since every node is indexed sequentially. If we were to represent the following binary heap as an array, we would get this array of values. If we know the index of node I, we can figure out what its left and right child nodes are by using simple formulas. The left child is 2 times I plus 1, and the right child is 2 times I plus 2, assuming zero-based indices. As an example, what are the children of the node at index 4? Well, we can just plug I into the two formulas I just gave you to obtain the indices 9 and 10. Of course, you can always run the math backwards and figure out what the parent of a given node is. Both of these are especially useful if you're either walking up or down the tree. Whenever you want to insert a new value into the priority queue, you insert the new value at the insertion position at the bottom right of the binary tree. Suppose we want to insert the value 8. This would violate the heap invariant, so we need to bubble up the value until the invariant is met. So swap nodes 5 and 12. The heap invariant is still not satisfied, so swap again. Swap nodes 2 and 5, and now the tree is balanced. Now let's review how removals are done. In a traditional priority queue, to remove items, search for the element you want to remove and then swap it with the last node. Perform the removal and finally bubble up or down the swapped value. For this example, suppose we want to remove the node that has the value 5. We don't know where the node with value 5 is within the priority queue, so we have to search for it. This is one of the major differences between the priority queue and the index priority queue. So start at node 0 and process each node sequentially until a node with a value of 5 is found, if any. So we found a node with a value 5. To actually remove it from the heap, swap it with the rightmost bottom node. Once this is done, remove node 5 from the tree. Now the purple node we swapped into 5's position may not satisfy the heap invariant, so we need to either move it up or down the tree. In this case, since the purple node has the value of 1, which is smaller than its children, and we're dealing with a max heap, we'll want to move the node down. That was a quick recap on just about everything you need to know about a traditional priority queue. Now let's talk about implementing an indexed priority queue with a binary heap. For the following examples, suppose we're dealing with n people with different priorities that we need to serve. Perhaps we're prioritizing people for a queue at a hospital, a waiting line at a restaurant, or who knows what. The main thing is we'll assume that the values can dynamically change and that we always want to serve the person with the lowest priority. To figure out who to serve next, we'll use a min-indexed priority queue to sort by lowest value first. The first step, as mentioned before, is to assign each person a unique index value between 0 and n non-inclusive. These are the key index values in the second column beside each person's name. Then I'm going to give each person an initial value to place inside the index priority queue. These values will be maintained by the index priority queue once inserted. Note that the values can be any comparable value you want, not only integers as shown here. This means we can have strings, objects, or whatever type of data we want. If I was to build a min-indexed priority queue out of the key value pairs I had on the last slide, this is the heap I would get. Remember that unlike the previous example, we're sorting by smallest value first, since we're dealing with a min heap. If I want to access the value for a given key k, first you need to figure out what its key index is, and then do a lookup in the values array maintained by the index priority queue. Here's a good question. What value does the key Bella have in the index priority queue? Well, first, find Bella's key index value, which is 1. Then index into the values array at position 1 to find the corresponding value for the key in the index priority queue. So Bella has a value of 15. Awesome. Now we know how to get the value for a particular key in the index priority queue. But how do we get the index of the node for a particular key? To do that, we'll need to maintain some additional information, namely a position map we can use to tell us the index of a node in the heap for any given key index. For convenience, I will store the position map as an array called PM inside the priority queue. As an example, let's find out which node represents the key Dylan. First, find the key index for Dylan, which happens to be 3. Then look up index 3 in the position map to tell you where Dylan is in the heap. It looks like Dylan is at the node at the index 7, highlighted in orange. Now here's a follow-up question. Where is George in the heap? I'll give you a quick moment to figure that out before I give you the answer. Alright, so with just about every operation, the first step is to find the key index for the key we care about, which is George. Then use the key index to do a lookup inside the position map and find out the node for George, which happens to be node 1. Great. Now we know how to look up the node for a given key, but how do we find the key for a given node? This inverse lookup will prove to be a very useful operation. Say you want to know which key is associated with the root node at index 0. Well, you need to be able to do an inverse lookup to figure that out. To do the inverse lookup from node indices to keys, we'll need to maintain an inverse lookup table. I will denote this lookup table as IM, short for inverse map. Let's see if we can figure out which person is represented in the node at index 2. To do that, simply do a lookup in the inverse map at index 2. This gives us information about which key index is associated with that node. Knowing the key index enables us to retrieve the actual key by doing a lookup in our bidirectional hash table. In this case, the node at position 2 represents the key Anna. Here's a follow-up question to make sure you're still paying attention. Which key is being represented in the node at index position 3? Same as before, find the key index through the inverse map. Then with the key index, figure out the actual key from the bidirectional hash table. We can then conclude that the node at position 3 represents the key Isaac. What we just covered was how an index priority queue is structured internally, and what all the moving parts are. Now we want to actually do some useful operations with this index priority queue, such as inserting new key value pairs, removing key value pairs based on a key, and also updating the value associated with a key. These are all possible and are actually very similar to how you would do it with a regular priority queue. Insertion is nearly the same, except that we have to update the position map PM and the inverse map IM to reflect the movement of the key value pairs. Suppose we want to insert the key Mary with a value of 2 into the priority queue. What we first have to do is assign Mary a unique key index value. Then we're going to insert the new key value pair at the insertion position. Notice that upon insertion, we updated our arrays at index 12 to reflect that the new value was in fact inserted. Currently, the heap invariant is not satisfied since the new node at index 12 has a value less than the one at node 5. To resolve this, we're going to swap the newly inserted value upwards until the heap invariant is satisfied. Swapping nodes, we need to update the position map and the inverse map by swapping the values of the two nodes we're exchanging. The values array does not need to be touched, since it gets indexed by the key index value that we get from the map and not the node index per se. It turns out that the heap invariant is still not satisfied, so we need to keep swapping upwards. Let's have a look at some pseudocode for insertions. In this snippet, the user calling this function needs to provide a valid key index, ki, as well as a non-null value they want to insert. The first thing I do is store the value associated with the key inside the values array. Then I update the position map and the inverse map to reflect the fact that a new key value pair has been inserted into the priority queue. Finally, I move the node up the heap until the heap invariant is satisfied. Let's take a closer look at this swim method to see how that happens. Here we are looking at the swim method. You'll notice that it has two supporting functions, swap and less. Swap simply exchanges two nodes based on index, and less determines if node I has a value less than node j. The logic for the swim function is fairly simple. It begins by finding the index of the parent node and walking up the tree. For every iteration, we walk up one layer in the tree. If the index of the current node is not the root node and the value of the current node is less than the parent node, remember that we're dealing with a min heap and want small values to be as high up as possible in our heap. To actually issue a node exchange, simply call the swap function and provide the index of the current node and the parent node, and then update the current node and the parent node index values. I also want to talk about swapping and how that actually occurs, because it's slightly different than a traditional priority queue. In this swap method, we're not actually moving around the values in the array. We're only swapping around the index values. Remember that the values array is indexed by the key index, not the node index. So effectively, the values array can remain constant while we update the inverse map and the position map. First, we update the positions of where key index values are found in the index priority queue. Remember what the position map is. It is the position of which node index a given key index is found at. So we can do a straightforward swap by indexing into the inverse map to find the key index values and swap indices I and j. Followed by this, simply update the key index values associated with nodes I and j in the inverse map. To do this, this is just a simple, straightforward exchange. Next up, I want to talk about polling and removing elements from an indexed priority queue. Polling is still a logarithmic operation. However, removing is improved from a linear time complexity to a logarithmic time complexity, since node position lookups are now constant time, but repositioning the nodes after a removal to satisfy the heap invariant is still logarithmic. So let's jump into an example. Suppose we want to poll the root node. This is something we often want to do since it'll give us the key value pair with the lowest value in the heap. The first step is to exchange the root node with the bottom right node. As we do that, remember to swap the index values. Now we can remove the red node from the tree. As we remove the value, let's make sure we store the key value pair we're removing so we can return it from our function later. Then clean up the removed node. Finally, restore the heap invariant by moving the swapped purple node down. Since the left and the right child nodes have an equal value of 2, let's default to selecting the left one. Let's do a slightly more involved removal by removing a specific key from the index priority queue. In this example, let's remove the key Laura. The first thing we want to do is get the key index for Laura, which is the key we're working with. So in this case, the key index is equal to 11. Once we know the key index, we can use that information to locate the node within the heap by looking inside the position map. Then swap the node we want to remove. That is the node which contains the key value pair for Laura, and exchange it with the bottom rightmost node. Store the key value pair before the actual removal. Clean up the removed node, and finally restore the heap invariant by moving the swapped purple node up or down. We're going to make the purple node move down because it has a large value. Alright, let's look at some pseudocode for removing key value pairs. The code is also very short, only 5 lines of implementation and 3 lines of cleanup. The first thing to do is exchange the position of the node we want to remove and the bottom rightmost node, which is always at the index position SZ, short for size, of the heap. Once we've exchanged the nodes, the rightmost node is now in the position where the node we want to remove was, so we need to move it either up or down the heap to satisfy the heap invariant. We don't know which it will be, so we try to move the node up and down, hence sink and swim. Lastly, I just clean up the values associated with the node we want to remove. You can also return the key value pair being removed, but I didn't do that here. Let's take a quick look at the sync method so we understand how that works. To sync a node, we want to select the child with the smallest value and defaulting to the left child if there's a tie. In this next block, I tried to update the smallest child to be the right child. But first, I need to check if the right child node index is within the size of the heap and its value is actually less than the one of the left node. The stopping condition is if we're outside the size of the heap or we cannot sync the current node any further. Lastly, we want to make sure we swap the current node with whatever was the node with the smallest value. Lastly, we want to make sure we swap the current node with whichever was the node with the smallest value. The last core operation we want to do on an index priority queue is key value pair updates. Similar to removals, updates in a min-indexed binary heap also take logarithmic time due to the constant time lookup to find out where the node is and the logarithmic time to adjust where the key value pair should appear in the heap. Suppose we want to update the value of the key Carly to now have a value of 1. Like every operation, find the key index for the key we want to work with. The key index for Carly happens to be 2. Then we can use that key index value to update the values array with the new value. Of course, the heap invariant may not be satisfied, so we need to move the node either up or down until it is. The pseudocode for updating the value of a key is super simple. Simply update the value in the values array and move the node either up or down the heap. It's that easy. Alright, so there was nothing too special about updates, but the part I really wanted to get to was increase and decrease key. In many applications, such as Dijkstra's or Prim's algorithm, it's often useful to be able to update a given key to make its value either always smaller or always larger. In the event that a worse value is given to the index priority queue, it should not be updated. In such situations, it is often useful to define a more restrictive form of update operation called increase key or decrease key respectively, depending on whether you want to increase the value associated with a key or always try and decrease the value associated with a key. Both of these operations are very simple. They simply consist of doing an if statement before performing an update operation, which either increases or decreases the value associated with a key. So bottom line, these two functions are just convenience methods that wrap a get operation with an if statement to update a value. Today we're going to look at some source code for an indexed priority queue. So just before we get started, make sure you watch my video on the indexed priority queue, where I go over the implementation details and why an indexed priority queue is an important data structure. All the source code for this video can be found on my data structures repository at github.com/williamfizet/datastructures. The link can be found in the description below. Here we are in the source code for a min-indexed binary heap. This source code is presented in the Java programming language. To get started, notice that our min-indexed binary heap requires that we pass in a type of object which is comparable. This is so we can order our key value pairs within the heap. You'll also notice that I'm extending a min-indexed d-array heap. This is just to be more generic. And all I do in the constructor is simply initialize this heap to have at most 2 children for each node, while a d-array heap supports in general d children. So let's look at the d-array heap implementation where all the fun stuff is happening. So let's just go over, I guess, all the instance variables. So sz is just the number of elements in the heap, n is a constant representing the maximum number of elements in the heap. D is the degree of each node. So for the binary heap, this number is 2. The 2 arrays, child and parent, track the child and parent indices for each node, so we don't have to compute them dynamically. PM and IM are the position map and the inverse maps, which we're going to use to track the key indices for our keys. And lastly is the values array, which is the array that contains the values associated with certain keys. Note that it's very important to notice that this array is indexed by the key indices and not by the nodes indices per se. So in the constructor, we give a degree and a certain maximum size for our heap. Then we just initialize whatever value for the degree and the maximum size of the heap. Then I initialize all our arrays and I compute what the child and the parent indices should be. And I also initialize the position map and inverse map to have all -1 values. Then we have a few straightforward methods such as size is empty, contains. So you'll notice that for contains, we don't pass in the key for our key value pair, instead we pass in the key index. And we're going to do this for all our methods. So I just have a few convenience bounds checking methods that you'll see again throughout these videos, such as key has to be in the bounds or throw. So this just makes sure that the key index is valid. And after this check is done, we can check, does that key exist within our heap by looking inside the position map and checking that the value is not equal to -1. Then we have things like peak min key index, which gets the key index for the node at top of the heap, and similarly pole min key index, and also peak min value and pole min value. The reason these are separate is because sometimes we want to just look at the value at the top of the heap but not necessarily remove it. The pole version will actually remove it. Now let's look at insert. So to insert a key value pair, we need to make sure that that key value pair does not already exist in the heap, otherwise we're going to throw an exception. Then I simply validate if the value is not null, and if it is, we throw an exception. Otherwise, we simply update our indices for the position map and the inverse map. Then we assign the values array to have the value we passed in, and then we swim up that node, which we know will be at position size, and we also increment the size variable so that our heap is one element larger. Then value of, pretty straightforward, just do a lookup inside the values array. Then delete is slightly more interesting. We make sure the key exists, then we get the index of where that key exists within the heap. We swap the index of the node and the last node in the heap. Then we reposition the new node we swapped into i's position to go either up the heap or down the heap. We capture the value in the position for the key index so that we can return it later. We clean up the node we want to delete, and finally we return that value. Update is also pretty easy. Just make sure that the key exists and the value is not null. Then we get the index for the node, then we capture the old value, update the new value, then move it within the heap, and finally return the old value. So increase and decrease are just short for decrease key and increase key. We're dealing with a min d-ary heap here, so make sure you take that into account when looking at the logic. So we make sure the key exists and it's not null. Then if the value is less than the value already in the heap at the values array at the key index, we can update it and also swim it down. Notice that I didn't call the update method here because we know we're going to swim down. In the update method, we sync and we swim, so we do both operations. We don't know which way the node will go, whether it's going to bubble up or bubble down, but in the decrease key method, we do. Same thing for the increase key method, except I switched the order for the less comparator so that the values array is in the first position and the value being passed in is on the right. These are just the sync and the swim methods I talked about in the slides. We can go over quickly. So to sync node I, we get the minimum child of node I. Since we're working with a d-ary heap, we need to search all the children of a node, find the one with the least value. This is going to be node J, and then we swap I and J, make sure that I is equal to the value of j, and then we find the minimum child again, and then repeat this until we can't sync the node anymore. Same thing for swim, except that we need to find the parent of node I, which we can just do a lookup in the parents array at index I, swap with the parent, and keep doing this until I is less than the parent. MinChild just looks at all the children of node I and finds the one with a minimum value and returns its index. Also pretty straightforward. Swap, we covered this in the slides. Basically swap the indices in the position map and the inverse map for nodes I and j. Then we have the less function, which simply compares the values for nodes I and j. And other convenience methods, just because I didn't want to include all the logic of throwing exceptions everywhere, I just kind of wrap them in helper functions. And this is just for tests to make sure that our heap is indeed a min heap. So that's all there is to an indexed the-ary heap. I hope there wasn't too much to ingest, and thank you for watching. Please give this video a thumbs up if you learned something, and subscribe for more mathematics and computer science videos. Thank you.